Introductory Note and Introduction to the Outline of Science, Volume 1, by J. Arthur Thomson. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by James Christopher, jxchristopher@yahoo.com. The Outline of Science, Volume 1, by J. Arthur Thomson. Introductory Note and Introduction. Introductory Note by Professor J. Arthur Thomson. Was it not the great philosopher and mathematician Leibniz who said that the more knowledge advances, the more it becomes possible to condense it into little books? Now, this Outline of Science is certainly not a little book, and yet it illustrates part of the meaning of Leibniz's wise saying. For here within reasonable compass there is a library of little books, an outline of many sciences. It will be profitable to the student in proportion to the discrimination with which it is used. For it is not in the least meant to be in the nature of an encyclopedia, giving condensed and comprehensive articles with a big full stop at the end of each. Nor is it a collection of primers, beginning at the very beginning of each subject and working methodically onwards. That is not the idea. What, then, is the aim of this book? It is to give the intelligent student citizen, otherwise called the man in the street, a bunch of intellectual keys by which to open doors, which have been hitherto shut to him, partially because he got no glimpse of the treasure behind the doors, and partially because the portals were made forbidding by an unnecessary display of technicalities. Laying aside conventional modes of treatment, and seeking rather to open up the subject as one might on a walk with a friend, the work offers the student what might be called informal introductions to the various departments of knowledge. To put it another way, the articles are meant to be clues, which the reader may follow till he has left his starting point very far behind. Perhaps when he has gone far on his own, he will not be ungrateful to the simple book of instructions to travelers, which this Outline of Science is intended to be. The simple bibliographies appended to the various articles will be enough to indicate first books. Each article is meant to be an invitation to an intellectual adventure, and the short list of books are merely finger-posts for the beginning of the journey. We confess to being greatly encouraged by the reception that has been given to the English serial issue of the Outline of Science. It has been very hearty, we might say almost enthusiastic, for we agree with Professor John Dewey that the future of our civilization depends upon the widening spread and deepening hold of the scientific habit of mind. And we hope that this is what the Outline of Science makes for. Information is all to the good. Interesting information is better still. The best of all is the education of the scientific habit of mind. Another modern philosopher, Professor L.T. Hobhouse, has declared the evolutionist's mundane goal is the mastery of the human mind of the conditions, internal as well as external, of its life and growth. Under the influence of this conviction, the Outline of Science has been written. For life is not for science, but science for life. And even more than science, to our way of thinking, is the individual development of the scientific way of looking at things. Science is our legacy. We must use it, if it is to be our very own. Introduction. There is abundant evidence of widened and deepened interest in modern science. How could it be otherwise when we think of the magnitude and the eventfulness of recent advances? But the interest of the general public would be even greater than it is if the makers of new knowledge were more willing to expound their discoveries in ways that could be understanded of the people. No one objects very much to technicalities in a game or on board a yacht, and they are clearly necessary for terse and precise scientific description. It is certain, however, that they can be reduced to a minimum without sacrificing accuracy, when the object in view is to explain the gist of the matter. So, this Outline of Science is meant for the general reader, who lacks both time and opportunity for special study, and yet would take an intelligent interest in the progress of science which is making the world always new. The story of the triumphs of modern science is one of which man may well be proud. Science reads the secret of the distant star, and anatomizes the atom, foretells the date of the comet's return, and predicts the kinds of chickens that will hatch from a dozen eggs, discovers the laws of the wind that bloweth where it listeth, and reduces to order the disorder of disease. Science is always setting forth on Columbus voyages, discovering new worlds and conquering them by understanding. For knowledge means foresight, and foresight means power. The idea of evolution has influenced all the sciences, forcing us to think of everything as with a history behind it. For we have traveled far since Darwin's day. The solar system, the earth, the mountain ranges and the great deeps, the rocks and the crystals, the plants and animals, man himself and his social institutions, all must be seen as the outcome of a long process of becoming. There are some 80-odd chemical elements on the earth today, and it is now much more than a suggestion that these are the outcome of an inorganic evolution, element giving rise to element, going back and back to some primeval stuff, from which they were all originally derived, infinitely long ago. No idea has been so powerful a tool in the fashioning of new knowledge as this simple but profound idea of evolution, that the present is the child of the past and the parent of the future. And with the picture of a continuity of evolution from nebula to social systems comes a promise of an increasing control, a promise that man will become not only a more accurate student, but a more complete master of his world. It is characteristic of modern science that the whole world is seen to be more vital than before. Everywhere there has been a passage from the static to the dynamic. Thus the new revelations of the constitution of matter, which we owe to the discoveries of men like Professor J. Thomson, Professor Sir Ernest Rutherford, and Professor Frederick Soddy, have shown the very dust to have a complexity and an activity heretofore unimagined. Such phrases as dead matter and inert matter have gone by the board. The new theory of the atom amounts almost to a new conception of the universe. It bids fair to reveal to us many of nature's hidden secrets. The atom is no longer the indivisible particle of matter it was once understood to be. We know now that there is an atom within the atom, that what we thought was elementary can be disassociated and broken up. The present-day theories of the atom and the constitution of matter are the outcome of the comparatively recent discovery of such things as radium, the X-rays, and the wonderful revelations of such instruments as the spectroscope and other highly perfected scientific instruments. The advent of the electron theory has thrown a flood of light on what before was hidden or only dimly guessed at. It has given us a new conception of the framework of the universe. We are beginning to know and realize of what matter is made and what electric phenomena mean. We can glimpse the vast stores of energy locked up in matter. The new knowledge has much to tell us about the origin of phenomena, not only of our own planet, but of other planets, of the stars and the sun. New light is thrown on the source of the sun's heat. We can make more than guesses as to its probable age. The great question of today is there one primordial substance from which all the varying forms of matter have been evolved? But the discovery of electrons is only one of the revolutionary changes which gives modern science an entrancing interest. As in chemistry and physics, so in the science of living creatures there has been recent advances that have changed the whole prospect. A good instance is afforded by the discovery of the hormones, or chemical messengers, which are produced by ductless glands such as the thyroid and suprarenal, and the pituitary, and are distributed throughout the body by the blood. The work of physiologists like Professor Starling and Professor Bayliss has shown that these chemical messengers regulate what may be called the pace of the body, and bring about that regulated harmony and smoothness of working which we all know as health. It is not too much to say that the discovery of hormones has changed the whole of physiology. Our knowledge of the human body far surpasses that of the past generation. The persistent patience of microscopists and technical improvements like the ultramicroscope have greatly increased our knowledge of the invisible world of life. To the bacteria of a past generation have been added a multiple of microscopic animal microbes, such as that which cause sleeping sickness. The life histories and the weird ways of many important parasites have been unraveled. And here again, knowledge means mastery. To a degree which has almost surpassed expectations, there has been a revelation of the intricacy of the stones and mortar of the house of life, and the microscopic study of germ cells has wonderfully supplemented the epoch-making experimental study of heredity, which began with Mendel. It goes without saying that no one can call himself educated who does not understand the central and simple ideas of Mendelism and other new departures in biology. The procession of life through the ages, and the factors in the sublime movement, the peopling of the earth by plants and animals, and the linking of life to life in subtle interrelations, such as those between flowers and their insect visitors, the life histories of individual types, and the extraordinary results of a new inquiry called experimental embryology, these also are among the subjects with which this outline will deal. The behavior of animals is another fascinating study, leading to a provisional picture of the dawn of mind. Indeed, no branch of science surpasses in interest that which deals with the ways and habits, the truly wonderful devices, adaptations, and instincts of insects, birds, and mammals. We no longer deny a degree of intelligence to some members of the animal world. Even the line between intelligence and reason is sometimes difficult to find. Fresh contacts between physiology and the study of man's mental life, precise studies of the ways of children and wild peoples, and new methods like those of the psychoanalyst must also receive the attention they deserve, for they are giving us a new psychology, and the claims of physical research must also be recognized by the open-minded. The general aim of the outline is to give the reader a clear and concise view of the essentials of present-day science, so that he may follow with intelligence the modern advance, and share appreciatively in man's continued conquest of his kingdom. J. Arthur Thomson. End of Introductory Note and Introduction.
Recording by James Christopher, jxchristopher@yahoo.com.
Section 1 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 1. Part 1. The Romance of the Heavens. The Scale of the Universe. The Solar System. 1. The story of the triumphs of modern science naturally opens with astronomy. The picture of the universe which the astronomer offers to us is imperfect. The lines he traces are often faint and uncertain. There are many problems which have been solved. There are just as many about which there is doubt, and notwithstanding our great increase in knowledge, there remain just as many which are entirely unsolved. The problem of the structure and duration of the universe, said the great astronomer Simon Newcomb, is the most far-reaching with which the mind has to deal. Its solution may be regarded as the ultimate object of stellar astronomy. The possibility of reaching, which has occupied the minds of thinkers since the beginning of civilization. Before our time, the problem could be considered only from the imaginative or the speculative point of view. Although we can today attack it to a limited extent by the scientific methods, it must be admitted that we have scarcely taken more than the first step toward the actual solution. What is the duration of the universe in time? Is it fitted to last forever in its present form, or does it contain within itself the seeds of dissolution? Must it, in the course of time, in we know not how many millions of ages, be transformed into something very different from what it now is? This question is intimately associated with the question whether the stars form a system. If they do, we may suppose that system to be permanent in its general features. If not, we must look further for our conclusions. The heavenly bodies. The heavenly bodies fall into two very distinct classes so far as their relation to our earth is concerned. The one class, a very small one, comprises a sort of colony of which the earth is a member. These bodies are called planets, or wanderers. There are 8 of them, including the earth, and they all circle round the sun. Their names, in the order of their distance from the sun, are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and of these Mercury, the nearest to the sun, is rarely seen by the naked eye. Uranus is practically invisible, and Neptune quite so. These 8 planets, together with the sun, constitute, as we have said, a sort of little colony. This colony is called the solar system. The second class of heavenly bodies are those which lie outside the solar system. Every one of those glittering points we see on a starlit night is at an immensely greater distance from us than is any member of the solar system. Yet the members of this little colony of ours, judged by terrestrial standards, are at enormous distances from one another. If a shell were shot in a straight line from one side of Neptune's orbit to the other, it would take 500 years to complete its journey. Yet this distance, the greatest in the solar system as now known, excepting the far swing of some of the comets, is insignificant compared to the distances of the stars. One of the nearest stars to the earth that we know of is Alpha Centauri, estimated to be some 25 millions of miles away. Sirius, the brightest star in the firmament, is double this distance from the earth. We must imagine the colony of planets to which we belong as a compact little family swimming in an immense void. At distances which would take our shell not hundreds but millions of years to traverse, we reach the stars, or rather a star, for the distances between stars are as great as the distances between the nearest of them and our sun. The earth, the planet on which we live, is a mighty globe bounded by a crust of rock many miles in thickness. The great volumes of water which we call our oceans lie in the deeper hollows of the crust. Above the surface, an ocean of invisible gas, the atmosphere, rises to a height of about 300 miles, getting thinner and thinner as it ascends. Except when the winds rise to a high speed, we seem to live in a very tranquil world. At night, when the glare of the sun passes out of our atmosphere, the stars and planets seem to move across the heavens with a stately and solemn slowness. It was one of the first discoveries of modern astronomy that this movement is only apparent. The apparent creeping of the stars across the heavens at night is accounted for by the fact that the earth turns upon its axis once in every 24 hours. When we remember the size of the earth, we see that this implies a prodigious speed. In addition to this, the earth revolves round the sun at a speed of more than 1,000 miles a minute. Its path round the sun, year in, year out, measures about 580 million miles. The earth is held closely to this path by the gravitational pull of the sun, which has a mass 333,432 times that of the earth. If at any moment the sun ceased to exert this pull, the earth would instantly fly off into space straight in the direction in which it was moving at the time, that is to say, at a tangent. This tendency to fly off at a tangent is continuous. It is the balance between it and the sun's pull which keeps the earth to her almost circular orbit. In the same way, the 7 other planets are held to their orbits. Circling round the earth, in the same way as the earth circles round the sun, is our moon. Sometimes the moon passes directly between us and the sun, and cuts off the light from us. We then have a total or partial eclipse of the sun. At other times, the earth passes directly between the sun and the moon, and causes an eclipse of the moon. The great ball of the earth naturally trails a mighty shadow across space, and the moon is eclipsed when it passes into this. The other 7 planets, 5 of which have moons of their own, circle round the sun as the earth does. The sun's mass is immensely larger than that of all the planets put together, and all of them would be drawn into it and perish if they did not travel rapidly round it in gigantic orbits. So the 8 planets, spinning round on their axes, follow their fixed paths round the sun. The planets are secondary bodies, but they are most important because they are the only globes in which there can be life as we know life. If we could be transported in some magical way to an immense distance in space above the sun, we should see our solar system as it is drawn in the accompanying diagram, except that the planets would be mere specks, faintly visible in the light which they receive from the sun. If we moved still farther away, trillions of miles away, the planets would fade entirely out of view, and the sun would shrink into a point of fire, a star. And here you begin to realize the nature of the universe. The sun is a star. The stars are suns. Our sun looks big simply because of its comparative nearness to us. The universe is a stupendous collection of millions of stars or suns, many of which may have planetary families like ours. 2. The scale of the universe. How many stars are there? A glance at a photograph of star clouds will tell at once that it is quite impossible to count them. The fine photograph reproduced in Figure 2 represents a very small patch of that pale white belt, the Milky Way, which spans the sky at night. It is true that this is a particularly rich area of the Milky Way, but the entire belt of light has been resolved in this way into masses or clouds of stars. Astronomers have counted the stars in typical districts here and there, and from these partial counts we get some idea of the total number of stars. There are estimated to be between 2,000 and 3,000 million stars. Yet these stars are separated by inconceivable distances from each other, and it is one of the greatest triumphs of modern astronomy to have mastered, so far, the scale of the universe. For several centuries astronomers have known the relative distances from each other of the sun and the planets. If they could discover the actual distance of any one planet from any other, they could at once tell all the distances within the solar system. The sun is, on the latest measurements, at an average distance of 92,830,000 miles from the earth. For as the orbit of the earth is not a true circle, this distance varies. This means that in 6 months from now the earth will be right at the opposite side of its path round the sun, or 185 million miles away from where it is now. Viewed or photographed from two positions so wide apart, the nearest stars show a tiny shift against the background of the most distant stars, and that is enough for the mathematician. He can calculate the distance of any star near enough to show this shift. We have found that the nearest star to the earth, a recently discovered star, is 25 trillion miles away. Only 30 stars are known to be within 100 trillion miles of us. This way of measuring does not, however, take us very far away in the heavens. There are only a few hundred stars within 500 trillion miles of the earth, and at that distance the shift of a star against the background, parallax, the astronomer calls it, is so minute that figures are very uncertain. At this point the astronomer takes up a new method. He learns the different types of stars, and then he is able to deduce more or less accurately the distance of a star of a known type from its faintness. He, of course, has instruments for gauging their light. As a result of 20 years' work in this field, it is now known that the more distant stars of the Milky Way are at least 100,000 trillion miles away from the sun. Our sun is in a more or less central region of the universe, or a few hundred trillion miles from the actual center. The remainder of the stars, which are all outside our solar system, are spread out, apparently in an enormous disk-like collection, so vast that even a ray of light, which travels at the rate of 186,000 miles a second, would take 50,000 years to travel from one end of it to the other. This, then, is what we call our universe. Are there other universes? Why do we say our universe? Why not the universe? It is now believed by many of our most distinguished astronomers that our colossal family of stars is only one of many universes. By a universe, an astronomer means any collection of stars which are close enough to control each other's movements by gravitation, and it is clear that there might be many universes, in this sense, separated from each other by profound abysses of space. Probably there are. For a long time we have been familiar with certain strange objects in the heavens which are called spiral nebulae. We shall see at a later stage what a nebula is, and we shall see that some astronomers regard these spiral nebulae as worlds in the making. But some of the most eminent astronomers believe that they are separate universes, island universes they call them, or great collections of millions of stars like our universe. There are certain peculiarities in the structure of the Milky Way which lead these astronomers to think that our universe may be a spiral nebula, and that the other spiral nebula are other universes. Vast as is the solar system, then, it is excessively minute in comparison with the stellar system, the universe of the stars, which is on a scale far transcending anything the human mind can apprehend. The solar system. The sun. 1. But now let us turn to the solar system and consider the members of our own little colony. Within the solar system there are a large number of problems that interest us. What is the size, mass, and distance of each of the planets? What satellites, like our moon, do they possess? What are their temperatures? And those other sporadic members of our system, comets and meteors, what are they? What are their movements? How do they originate? And the sun itself, what is its composition? What is the source of its heat? How did it originate? Is it running down? These last questions introduce us to a branch of astronomy which is concerned with the physical constitution of the stars, a study which, not so very many years ago, may well have appeared inconceivable. But the spectroscope enables us to answer even these questions, and the answer opens up questions of yet greater interest. We find that the stars can be arranged in an order of development, that there are stars at all stages of their life history. The main lines of the evolution of the stellar universe can be worked out. In the sun and stars we have furnaces with temperatures enormously high. It is in such conditions that substances are resolved into their simplest forms, and it is thus we are enabled to obtain a knowledge of the most primitive forms of matter. It is in this direction that the spectroscope, which we shall refer to immediately, has helped us so much. It is to this wonderful instrument that we owe our knowledge of the composition of the sun and stars, as we shall see. That the spectroscope will detect the millionth of a milligram of matter, and on that account has discovered new elements, commands our admiration. But when we find in addition that it will detect the nature of forms of matter trillions of miles away, and moreover that it will measure the velocities with which these forms of matter are moving with an absurdly small % of possible error, we can easily acquiesce in the statement that it is the greatest instrument ever devised by the brain and hand of man. Such are some of the questions with which modern astronomy deals. To answer them requires the employment of instruments of almost incredible refinement and exactitude, and also the full resources of mathematical genius. Whether astronomy be judged from the point of view of the phenomena studied, the vast masses, the immense distances, the eons of time, or whether it be judged as a monument of human ingenuity, patience, and the rarest type of genius, it is certainly one of the grandest, as it is also one of the oldest of the sciences. The Solar System. In the solar system we include all those bodies dependent on the sun which circulate around it at various distances, deriving their light and heat from the sun, the planets and their moons, certain comets, and a multitude of meteors. In other words, all bodies whose movements in space are determined by the gravitational pull of the sun. The Sun. Thanks to our wonderful modern instruments and the ingenious methods used by astronomers, we have today a remarkable knowledge of the sun. Look at the figure of the sun in the frontispiece. The picture represents an eclipse of the sun. The dark body of the moon has screened the sun's shining disk and taken the glare out of our eyes. We see a silvery halo surrounding the great orb on every side. It is the sun's atmosphere, or crown, corona, stretching for millions of miles into space in the form of a soft, silvery-looking light. Probably much of its light is sunlight reflected from particles of dust, although the spectroscope shows an element in the corona that has not so far been detected anywhere else in the universe, and which in consequence has been named chromium. We next notice in the illustration that at the base of the halo there are red flames peeping out from the edges of the hidden disk. When one remembers that the sun is 866,000 miles in diameter, one hardly needs to be told that these flames are really gigantic. We shall see what they are presently. Regions of the sun. The astronomer has divided the sun into definite concentric regions or layers. These layers envelop the nucleus or central body of the sun, somewhat as the atmosphere envelops our earth. It is through these vapor layers that the bright white body of the sun is seen. Of the innermost region, the heart or nucleus of the sun, we know almost nothing. The central body or nucleus is surrounded by a brilliantly luminous envelope or layer of vaporous matter, which is what we see when we look at the sun, and which the astronomer calls the photosphere. Above, that is, overlying the photosphere, there is a second layer of glowing gases, which is known as the reversing layer. This layer is cooler than the underlying photosphere. It forms a veil of smoke-like haze, and is of from 500 to 1,000 miles in thickness. A third layer, or envelope, immediately lying over the last one, is the region known as the chromosphere. The chromosphere extends from 5,000 to 10,000 miles in thickness, a sea of red tumultuous surging fire. Chief among the glowing gases is the vapor of hydrogen. The intense white heat of the photosphere beneath shines through this layer, overpowering its brilliant redness. From the uppermost portion of the chromosphere, great fiery tongues of glowing hydrogen and calcium vapor shoot out for many thousands of miles, driven outward by some prodigious expulsive force. It is these red prominences which are such a notable feature in the picture of the eclipse of the sun already referred to. During the solar eclipse of 1919, one of these red flames rose in less than 7 hours from a height of 130,000 miles to more than 500,000 miles above the sun's surface. This immense column of red-hot gas, 4 or 5 times the thickness of the earth, was soaring upward at the rate of 60,000 miles an hour. These flaming jets or prominences shooting out from the chromosphere are not to be seen every day by the naked eye. The dazzling light of the sun obscures them, gigantic as they are. They can be observed, however, by the spectroscope any day, and they are visible to us for a very short time during an eclipse of the sun. Some extraordinary outbursts have been witnessed. Thus, the late Professor Young described one on September 7, 1871, when he had been examining a prominence by the spectroscope. It had remained unchanged since noon of the previous day, a long, low, quiet-looking cloud, not very dense or brilliant, or in any way remarkable except for its size. At 12:30 p.m. the Professor left the spectroscope for a short time, and on returning half an hour later to his observations, he was astonished to find the gigantic sun flame shattered to pieces. The solar atmosphere was filled with flying debris, and some of these portions reached a height of 100,000 miles above the solar surface. Moving with a velocity which, even at the distance of 93,000,000 miles, was almost perceptible to the eye, these fragments doubled their height in 10 minutes. On January 30, 1885, another distinguished solar observer, the late Professor Tacchini of Rome, observed one of the greatest prominences ever seen by man. Its height was no less than 142,000 miles, 18 times the diameter of the earth. Another mighty flame was so vast that, supposing the 8 large planets of the solar system ranged one on top of the other, the prominence would still tower above them. The fourth and uppermost layer or region is that of the corona, of immense extent and fading away into the surrounding sky. This we have already referred to. It is through these several transparent layers that we see the white-like body of the sun. 2. The surface of the sun. Here let us return to and see what more we know about the photosphere, the sun's surface. It is from the photosphere that we have gained most of our knowledge of the composition of the sun, which is believed not to be a solid body. Examination of the photosphere shows that the outer surface is never at rest. Small bright cloudlets come and go in rapid succession, giving the surface, through contrast in luminosity, a granular appearance. Of course, to be visible at all at 92,830,000 miles, the cloudlets cannot be small. They imply enormous activity in the photosphere. If we might speak picturesquely, the sun's surface resembles a boiling ocean of white-hot metal vapors. We have today a wonderful instrument, which will be described later, which dilutes, as it were, the general glare of the sun, and enables us to observe these fiery eruptions at any hour. The oceans of red-hot gas and white-hot metal vapor at the sun's surface are constantly driven by great storms. Some unimaginable energy streams out from the body or muscles of the sun and blows its outer layers into gigantic shreds, as it were. The actual temperature at the sun's surface, or what appears to us to be the surface, the photosphere, is of course unknown, but careful calculation suggests that it is from 5,000 degrees Celsius to 7,000 degrees Celsius. The interior is vastly hotter. We can form no conception of such temperatures as must exist there. Not even the most obdurate solid could resist such temperatures, but would be converted almost instantaneously into gas. But it would not be gas as we know gases on the earth. The enormous pressures that exist on the sun must convert even gases into thick, treacly fluids. We can only infer this state of matter. It is beyond our power to reproduce it. Sunspots. It is in the brilliant photosphere that the dark areas known as sunspots appear. Some of these dark spots, they are dark only by contrast with the photosphere surrounding them, are of enormous size, covering many thousands of square miles of surface. What they are, we cannot positively say. They look like great cavities in the sun's surface. Some think they are giant whirlpools. Certainly they seem to be great whirling streams of glowing gases with vapors above them and immense upward and downward currents within them. Round the edges of the sunspots rise great tongues of flame. Perhaps the most popularly known fact about sunspots is that they are somehow connected with what we call magnetic storms on earth. These magnetic storms manifest themselves in interruptions of our telegraphic and telephonic communications, in violent disturbances of the mariner's compass, and in exceptional auroral displays. The connection between the two sets of phenomena cannot be doubted, even although at times there may be a great spot on the sun without any corresponding magnetic storm effects on the earth. A surprising fact about sunspots is that they show definite periodic variations in number. The best defined period is one of about 11 years. During this period the spots increase to a maximum in number and then diminish to a minimum, the variation being more or less regular. Now this can only mean one thing. To be periodic, the spots must have some deep-seated connection with the fundamental facts of the sun's structure and activities. Looked at from this point of view, their importance becomes great. The aurora borealis. The aurora borealis is one of the most beautiful spectacles in the sky. The colors and shape change every instant. Sometimes a fan-like cluster of rays, at other times long golden draperies gliding one over the other. Blue, green, yellow, red, and white combine to give a glorious display of color. The theory of its origin is still, in part, obscure, but there can be no doubt that the aurora is related to the magnetic phenomena of the earth, and therefore is connected with the electrical influence of the sun. It is from the study of sunspots that we have learned that the sun's surface does not appear to rotate all at the same speed. The equatorial regions are rotating quicker than the regions farther north or south. A point 45 degrees from the equator seems to take about 2½ days longer to complete one rotation than a point on the equator. This of course confirms our belief that the sun cannot be a solid body. What is its composition? We know that there are present in a gaseous state such well-known elements as sodium, iron, copper, zinc, and magnesium. Indeed, we know that there is practically every element in the sun that we know to be in the earth. How do we know? It is from the photosphere, as has been said, that we have won most of our knowledge of the sun. The instrument used for this purpose is the spectroscope, and before proceeding to deal further with the sun and the source of its energy, it will be better to describe this instrument. A wonderful instrument and what it reveals. The spectroscope is an instrument for analyzing light. So important is it in the revelations it has given us that it will be best to describe it fully. Every substance to be examined must first be made to glow, made luminous, and as nearly everything in the heavens is luminous, the instrument has a great range in astronomy. And when we speak of analyzing light, we mean that the light may be broken up into waves of different lengths. What we call light is a series of minute waves in ether, and these waves are, measuring them from crest to crest, so to say, of various lengths. Each wavelength corresponds to a color of the rainbow. The shortest waves gives us a sensation of violet color, and the largest waves cause a sensation of red. The rainbow, in fact, is a sort of natural spectrum. The meaning of the rainbow is that the moisture-laden air has sorted out these waves in the sun's light according to their length. Now the simplest form of spectroscope is a glass prism, a triangular-shaped piece of glass. If white light, sunlight for example, passes through a glass prism, we see a series of rainbow-tinted colors. Anyone can notice this effect when sunlight is shining through any kind of cut glass, the stopper of a wine decanter, for instance. If, instead of catching with the eye the colored lights as they emerge from the glass prism, we allow them to fall on a screen, we shall find that they pass, by continuous gradations, from red at the one end of the screen, through orange, yellow, green, blue, and indigo, to violet at the other end. In other words, what we call white light is composed of rays of these several colors. They go to make up the effect which we call white. And now, just as water can be split up into its two elements, oxygen and hydrogen, so sunlight can be broken up into its primary colors, which are those we have just mentioned. This range of colors, produced by the spectroscope, we call the solar spectrum, and these are, from the spectroscopic point of view, primary colors. Each shade of color has its definite position in the spectrum. That is to say, the light of each shade of color, corresponding to its wavelength, is reflected through a certain fixed angle on passing through the glass prism. Every possible kind of light has its definite position, and is denoted by a number which gives the wavelength of the vibrations constituting that particular kind of light. Now, other kinds of light besides sunlight can be analyzed. Light from any substance which has been made incandescent may be observed with the spectroscope in the same way, and each element can be thus separated. It is found that each substance, in the same conditions of pressure and so forth, gives a constant spectrum of its own. Each metal displays its own distinctive color. It is obvious, therefore, that the spectrum provides the means for identifying a particular substance. It was by this method that we discovered in the sun the presence of such well-known elements as sodium, iron, copper, zinc, and magnesium. Every chemical element known, then, has a distinctive spectrum of its own when it is raised to incandescence, and this distinctive spectrum is as reliable a means of identification for the element as a human face is for its owner. Whether it is a substance glowing in the laboratory or in a remote star makes no difference to the spectroscope. If the light of any substance reaches it, that substance will be recognized and identified by the characteristic set of waves. The spectrum of a glowing mass of gas will consist in a number of bright lines of various colors, and at various intervals, corresponding to each kind of gas, there will be a peculiar and distinctive arrangement of bright lines. But if the light from such a mass of glowing gas be made to pass through a cool mass of the same gas, it will be found that dark lines replace the bright lines in the spectrum. The reason for this being that the cool gas absorbs the rays of light emitted by the hot gas. Experiments of this kind enable us to reach the important general statement that every gas, when cold, absorbs the same rays of light which it emits when hot. Crossing the solar spectrum are hundreds and hundreds of dark lines. These could not at first be explained, because this fact of discriminative absorption was not known. We understand now. The sun's white light comes from the photosphere, but between us and the photosphere there is, as we have seen, another solar envelope of relatively cooler vapors, the reversing layer. Each constituent element in this outer envelope stops its own kind of light, that is, the kind of light made by incandescent atoms of the same element in the photosphere. The stoppages register themselves in the solar spectrum as dark lines placed exactly where the corresponding bright lines would have been. The explanation once attained, dark lines became as significant as bright lines. The secret of the sun's composition was out. We have found practically every element in the sun that we know to be in the earth. We have identified an element in the sun before we were able to isolate it on the earth. We have been able even to point to the coolest places on the sun, the centers of sunspots, where alone the temperature seems to have fallen sufficiently low to allow chemical compounds to form. It is thus we have been able to determine what the stars, comets, or nebulae are made of. A unique discovery. In 1868, Sir Norman Lockyer determined a light coming from the prominences of the sun which was not given by any substance known on earth, and attributed this to an unknown gas which he called helium, from the Greek helios, the sun. In 1895, Sir William Ramsay discovered in certain minerals the same gas identified by the spectroscope. We can say, therefore, that this gas was discovered in the sun nearly 30 years before it was found on earth. This discovery of the long-lost air is as thrilling a chapter in the detective story of science as any in the sensational stories of the day, and make us feel quite certain that our methods really tell us of what elements sun and stars are built up. The light from the corona of the sun, as we have mentioned, indicates a gas still unknown on earth, which has been christened coronium. Measuring the speed of light. But this is not all. Soon a new use was found for the spectroscope. We found that we could measure with it the most difficult of all speeds to measure, speed in the line of sight. Movement at right angles to the direction in which one is looking is, if there is sufficient of it, easy to detect, and if the distance of the moving body is known, easy to measure. But movement in the line of vision is both difficult to detect and difficult to measure. Yet, even at the enormous distances with which astronomers have to deal, the spectroscope can detect such movement and furnish data for its measurement. If a luminous body containing, say, sodium, is moving rapidly towards the spectroscope, it will be found that the sodium lines in the spectrum have moved slightly from their usual definite positions towards the violet end of the spectrum, the amount of the change of position increasing with the speed of the luminous body. If the body is moving away from the spectroscope, the shifting of the spectral lines will be in the opposite direction, towards the red end of the spectrum. In this way we have discovered and measured measurements that otherwise would probably not have revealed themselves unmistakably to us for thousands of years. In the same way we have watched and measured the speed of tremendous movements on the sun, and so gained proof that the vast disturbances we should expect there actually do occur. Is the sun dying? 3. Now let us return to our consideration of the sun. To us on the earth the most patent and most astonishing fact about the sun is its tremendous energy. Heat and light in amazing quantities pour from it without ceasing. Where does this energy come from? Enormous jets of red glowing gases can be seen shooting outwards from the sun, like flames from a fire, for thousands of miles. Does this argue fire, as we know fire on the earth? On this point the scientist is sure. The sun is not burning, and combustion is not the source of its heat. Combustion is a chemical reaction between atoms. The conditions that make it possible are known and the results are predictable and measurable. But no chemical reaction of the nature of combustion as we know it will explain the sun's energy, nor indeed will any ordinary chemical reaction of any kind. If the sun were composed of combustible material throughout, and the conditions of combustion as we understand them were always present, the sun would burn itself out in some thousands of years, with marked changes in its heat and light production as the process advanced. There is no evidence of such changes. There is, instead, strong evidence that the sun has been emitting light and heat in prodigious quantities, not for thousands, but for millions of years. Every addition to our knowledge that throws light on the sun's age seems to make for increase rather than decrease of its years. This makes the wonder of its energy greater. And we cannot avoid the issue of the source of the energy by saying merely that the sun is gradually radiating away an energy that originated in some unknown manner, away back at the beginning of things. Reliable calculations show that the years required for the mere cooling of a globe like the sun could not possibly run to millions. In other words, the sun's energy must be subject to continuous and more or less steady renewal. However it may have acquired its enormous energy in the past, it must have some source of energy in the present. The best explanation that we have today of this continuous accretion of energy is that it is due to shrinkage of the sun's bulk under the force of gravity. Gravity is one of the most mysterious forces of nature, but it is an obvious fact that bodies behave as if they attracted one another, and Newton worked out the law of this attraction. We may say, without trying to go too deeply into things, that every particle of matter attracts every other throughout the universe. If the diameter of the sun were to shrink by 1 mile all around, this would mean that all the millions of tons in the outer 1 mile thickness would have a straight drop of 1 mile towards the center. And that is not all, because obviously the layers below this outer mile would also drop inwards, each to a less degree than the one above it. What a tremendous movement of matter, however slowly it might take place, and what a tremendous energy would be involved! Astronomers calculate that the above shrinkage of 1 mile all around would require 50 years for its completion, assuming reasonably that there is close and continuous relationship between loss of heat by radiation and shrinkage. Even if this were true, we need not feel over-anxious on this theory. Before the sun became too cold to support life, many millions of years would be required. It was suggested at one time that falls of meteoric matter into the sun would account for the sun's heat. This position is hardly tenable now. The mere bulk of the meteoric matter required by the hypothesis, apart from other reasons, is against it. There is undoubtedly an enormous amount of meteoric matter moving about within the bounds of the solar system, but most of it seems to be following definite routes round the sun like the planets. The stray erratic quantities destined to meet their doom by collision with the sun can hardly be sufficient to account for the sun's heat. Recent study of radioactive bodies has suggested another factor that may be working powerfully along with the force of gravitation to maintain the sun's store of heat. In radioactive bodies, certain atoms seem to be undergoing disintegration. These atoms appear to be splitting up into very minute and primitive constituents. But since matter may be split up into such constituents, may it not be built up from them? The question is whether these radioactive elements are undergoing disintegration or formation in the sun. If they are undergoing disintegration, and the sun itself is undoubtedly radioactive, then we have another source of heat for the sun that will last indefinitely. The planets. Life in other worlds? 1. It is quite clear that there cannot be life on the stars. Nothing solid or even liquid can exist in such furnaces as they are. Life exists only on planets, and even on these its possibilities are limited. Whether all the stars, or how many of them, have planetary families like our sun, we cannot positively say. If they have, such planets would be too faint and small to be visible tens of trillions of miles away. Some astronomers think that our sun may be exceptional in having planets, but their reasons are speculative and unconvincing. Probably a large proportion, at least, of the stars have planets, and we may therefore survey the globes of our own solar system and in a general way extend the results to the rest of the universe. In considering the possibility of life as we know it, we may at once rule out the most distant planets from the sun, Uranus and Neptune. They are probably intrinsically too hot. We may also pass over the nearest planet to the sun, Mercury. We have reason to believe that it turns on its axis in the same period as it revolves round the sun, and it must therefore always present the same side to the sun. This means that the heat on the sunlit side of Mercury is above boiling point, while the cold on the other side must be between 200 and 300 degrees below freezing point. The planet Venus. The planet Venus, the bright globe which is known to all as the morning and evening star, seems at first sight more promising as regards the possibility of life. It is of nearly the same size as the earth, and it has a good atmosphere, but there are many astronomers who believe that, like Mercury, it always presents the same face to the sun, and it would therefore have the same disadvantage, a broiling heat on the sunny side and the cold of space on the opposite side. We are not sure. The surface of Venus is so bright, the light of the sun is reflected to us by such dense masses of cloud and dust, that it is difficult to trace any permanent markings on it, and thus ascertain how long it takes to rotate on its axis. Many astronomers believe that they have succeeded, and that the planet always turns the same face to the sun. If it does, we can hardly conceive of life on its surface, in spite of the cloud screen. We turn to Mars, and we must first make it clear why there is so much speculation about life on Mars, and why it is supposed that, if there is life on Mars, it must be more advanced than life on the earth. End of section 1.
Section 2 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by J.C. Guan. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 2. Part 1. The Romance of the Heavens. Continued. Is there life on Mars? The basis of this belief is that if, as we saw, all the globes in our solar system are masses of metal that are cooling down, the smaller will have cooled down before the larger, and will be further ahead in their development. Now Mars is very much smaller than the earth, and must have cooled at its surface millions of years before the earth did. Hence, if a story of life began on Mars at all, it began long before the story of life on the earth. We cannot guess what sort of life forms would be evolved in a different world, but we can confidently say that they would tend toward increasing intelligence, and thus we are disposed to look for highly intelligent beings on Mars. But this argument supposes that the conditions of life, namely air and water, are found on Mars, and it is disputed whether they are found there in sufficient quantity. The late Professor Percival Lowell, who made a lifelong study of Mars, maintained that there are hundreds of straight lines drawn across the surface of the planet, and he claimed that they are beds of vegetation, marking the sites of great channels, or pipes, by means of which the Martians draw water from the polar ocean. Professor W.H. Pickering, another high authority, thinks that the lines are long, narrow marshes fed by moist winds from the poles. There are certainly white polar caps on Mars. They seem to melt in the spring, and the dark fringe around them grows broader. Other astronomers, however, say that they find no trace of water vapor in the atmosphere of Mars, and they think that the polar caps may be simply thin sheets of hoarfrost or frozen gas. They point out that, as the atmosphere of Mars is certainly scanty, and the distance from the sun is so great, it may be too cold for the fluid water to exist on the planet. If one asks why our wonderful instruments cannot settle these points, one must be reminded that Mars is never nearer than 34 million miles from the earth, and only approaches this distance once in 15 or 17 years. The image of Mars on the photographic negative taken in a big telescope is very small. Astronomers rely to a great extent on the eye, which is more sensitive than the photographic plate. But it is easy to have differences of opinion as to what the eye sees, and so there is a good deal of controversy. In August 1924 the planet will again be well placed for observation, and we may learn more about it. Already a few of the much disputed lines, which people wrongly call canals, have been traced on photographs. Astronomers who are skeptical about life on Mars are often not fully aware of the extraordinary adaptability of life. There was a time when the climate of the whole earth, from pole to pole, was semi-tropical for millions of years. No animal could then endure the least cold, yet now we have plenty of arctic plants and animals. If the cold came slowly on Mars, as we have reason to suppose, the population could be gradually adapted to it. On the whole, it is possible that there is advanced life on Mars, and it is not impossible, in spite of the very great difficulties of a code of communication, that our elder brothers may yet flash across space the solution of many of our problems. Part 2. Jupiter and Saturn. Next to Mars, going outward from the sun, is Jupiter. Between Mars and Jupiter, however, there are more than 300 million miles of space, and the older astronomers wondered why this was not occupied by a planet. We now know that it contains about 900 planetoids, or small globes, of from 5 to 500 miles in diameter. It was at one time thought that a planet might have burst into these fragments, a theory which is not mathematically satisfactory. Or it may be that the material which is gathered in them was prevented by the nearness of the great bulk of Jupiter from uniting into one globe. For Jupiter is a giant planet, and its gravitational influence must extend far over space. It is 1,300 times as large as the Earth, and has 9 moons, 4 of which are large in attendance on it. It is interesting to note that the outermost moons of Jupiter and Saturn revolve round these planets in a direction contrary to the usual direction taken by moons round planets, and by planets round the sun. But there is no life on Jupiter. The surface, which we see in photographs, is a mass of cloud or steam, which always envelops the body of the planet. It is apparently red hot. A red tinge is seen sometimes at the edges of its cloud belts, and a large red region, the red spot, 33,000 miles in length, has been visible on it for half a century. There may be a liquid or solid core to the planet, but as a whole it is a mass of seething vapors whirling round on its axis once in every 10 hours. As in the case of the sun, however, different latitudes appear to rotate at different rates. The interior of Jupiter is very hot, but the planet is not self-luminous. The planets Venus and Jupiter shine very brightly, but they have no light of their own. They reflect the sunlight. Saturn is in the same interesting condition. The surface is steam, and Saturn is so far away from the sun that the vaporization of its oceans must necessarily be due to its own internal heat. It is too hot for water to settle on its surface. Like Jupiter, the great globe turns on its axis once in 10 hours, a prodigious speed, and must be a swirling, seething mass of metallic vapors and gases. It is instructive to compare Jupiter and Saturn in this respect with the sun. They are smaller globes, and have cooled down more than the central fire. Saturn is a beautiful object in the telescope because it has 10 moons, to include one which is disputed, and a wonderful system of rings round it. The so-called rings are a mighty swarm of meteorites, pieces of iron and stone of all sorts and sizes, which reflect the light of the sun to us. This ocean of matter is some miles deep, and stretches from a few thousand miles from the surface of the planet to 172,000 miles out in space. Some astronomers think that this is volcanic material which has been shot out of the planet. Others regard it as stuff which would have combined to form an 11th moon but was prevented by the nearness of Saturn itself. There is no evidence of life on Saturn. The Moon. Mars and Venus are therefore the only planets, besides the Earth, on which we may look for life, and in the case of Venus the possibility is very faint. But what about the moons which attend the planets? They range in size from the little 10 miles wide moons of Mars to Titan, a moon of Saturn, and Ganymede, a satellite of Jupiter, which are about 3,000 miles in diameter. May there not be life on some of the larger of these moons? We will take our own moon as a type of the class. A dead world. The moon is so very much nearer to us than any other heavenly body that we have a remarkable knowledge of it. In Fig. 14 you have a photograph taken in one of our largest telescopes of part of its surface. In a sense, such a telescope brings the moon to within about 50 miles of us. We should see a city like London as a dark, sprawling blotch on the globe. We could just detect a Zeppelin or a diplodocus as a moving speck against the surface. But we find none of these things. It is true that a few astronomers believe that they see signs of some sort of feeble life or movement on the moon. Professor Pickering thinks that he can trace some volcanic activity. He believes that there are areas of vegetation, probably of a low order, and that the soil of the moon may retain a certain amount of water in it. He speaks of a very thin atmosphere, and of occasional light falls of snow. He has succeeded in persuading some careful observers that there probably are slight changes of some kind taking place on the moon. But there are many things that point to absence of air on the moon. Even the photographs we reproduce tell the same story. The edges of the shadows are all hard and black. If there had been an appreciable atmosphere, it would have scattered the sun's light onto the edges and produced a gradual shading off, such as we see on the earth. This relative absence of air must give rise to some surprising effects. There will be no sounds on the moon, because sounds are merely air waves. Even a meteor shattering itself to a violent end against the surface of the moon would make no noise. Nor would it herald its coming by glowing into a shooting star, as it would on entering the earth's atmosphere. There will be no floating dust, no scent, no twilight, no blue sky, no twinkling of the stars. The sky will be always black, and the stars will be clearly visible by day as by night. The sun's wonderful corona, which no man on earth, even by seizing every opportunity during eclipses, can hope to see for more than 2 hours in all a long lifetime, will be visible all day. So will the great red flames of the sun. Of course, there will be no life, and no landscape effects and scenery effects due to vegetation. The moon takes approximately 27 of our days to turn once on its axis. So for 14 days there is continuous night, when the temperature must sink away down towards the absolute cold of space. This will be followed without an instant of twilight by full daylight. For another 14 days the sun's rays will bear straight down, with no diffusion or absorption of their heat or light on the way. It does not follow, however, that the temperature of the moon's surface must rise enormously. It may not even rise to the temperature of melting ice. Seeing there is no air, there can be no check on radiation. The heat that the moon gets will radiate away immediately. We know that amongst the coldest places on the earth are the tops of very high mountains, the points that have reared themselves nearest to the sun but furthest out of the sheltering blanket of the earth's atmosphere. The actual temperature of the moon's surface by day is a moot point. It may be below the freezing point or above the boiling point of water. The mountains of the moon. The lack of air is considered by many astronomers to furnish the explanation of the enormous number of craters which pit the moon's surface. There are about 100,000 of these strange rings, and it is now believed by many that they are spots where very large meteorites, or even planetoids, splashed into the moon when its surface was still soft. Other astronomers think that they are the remains of gigantic bubbles, which were raised in the moon's skin, when the globe was still molten, by volcanic gases from below. A few astronomers think that they are, as is popularly supposed, the craters of extinct volcanoes. Our craters on the earth are generally deep cups, whereas these ring formations on the moon are more like very shallow and broad saucers. Clavius, the largest of them, is 123 miles across the interior, yet its encircling rampart is not a mile high. The mountains on the moon rise to a great height, and are extraordinarily gaunt and rugged. They are like fountains of lava, rising in places to 26,000 and 27,000 feet. The lunar Apennines have 3,000 steep and weird peaks. Our terrestrial mountains are continually worn down by the frost acting on moisture, and by ice and water, but there are none of these agencies operating on the moon. Its mountains are comparatively everlasting hills. The moon is interesting to us, precisely because it is a dead world. It seems to show how the earth, or any cooling metal globe, will evolve in the remote future. We do not know if there was ever life on the moon, but in any case it cannot have proceeded far in development. At the most we can imagine some strange lowly forms of vegetation lingering here and there in pools of heavy gas, expanding during the blaze of the sun's long day, and frozen rigid during the long night. Meteors and comets. We may conclude our survey of the solar system with a word about shooting stars, or meteors, and comets. There are few now who do not know that the streak of fire which suddenly lights the sky overhead at night means that a piece of stone or iron has entered our atmosphere from outer space, and has been burned up by friction. It was travelling at perhaps 20 or 30 miles a second. At 70 or 80 miles above our heads it began to glow, and at that height the air is thick enough to offer serious friction and raise it to a white heat. By the time the meteor reached about 20 miles or so from the earth's surface, it was entirely dissipated, as a rule in fiery vapor. Millions of meteorites. It is estimated that between 10 and 100 million meteorites enter our atmosphere and are cremated every day. Most of them weigh only an ounce or two, and are invisible. Some of them weigh a ton or more, but even against these large masses the air acts as a kind of torpedo net. They generally burst into fragments and fall without doing damage. It is clear that empty space is, at least within the limits of our solar system, full of these things. They swarm like fishes in the seas. Like the fishes, moreover, they may be either solitary or gregarious. The solitary bit of cosmic rubbish is the meteorite, which we have just examined. A social group of meteorites is the essential part of a comet. The nucleus, or bright central part, of the head of a comet consists of a swarm, sometimes thousands of miles wide, of these pieces of iron or stone. This swarm has come under the sun's gravitational influence, and is forced to travel round it. From some dark region of space it has moved slowly into our system. It is not then a comet, for it has no tail, but as the crowded meteors approach the sun, the speed increases. They give off fine vapor-like matter, and a fierce flood of light from the sun sweeps this vapor out in an ever-lengthening tail. Whatever way the comet is travelling, the tail always points away from the sun. A great comet. The vapory tail often grows to an enormous length as the comet approaches the sun. The great comet of 1843 had a tail 200 million miles long. It is, however, composed of the thinnest vapors imaginable. Twice during the 19th century the earth passed through the tail of a comet, and nothing was felt. The vapors of the tail are, in fact, so attenuated that we can hardly imagine them to be white hot. They may be lit by some electrical force. However that may be, the comet dashes round the sun, often at 300 or 400 miles a second, then may pass gradually out of our system once more. It may be 1,000 years, or it may be 50 years, before the monarch of the system will summon it again to make its fiery journey round his throne. The Stellar Universe. Part 1. The immensity of the stellar universe, as we have seen, is beyond our apprehension. The sun is nothing more than a very ordinary star, perhaps an insignificant one. There are stars enormously greater than the sun. One such, Betelgeuse, has recently been measured, and its diameter is more than 300 times that of the sun. The evolution of stars. The proof of the similarity between our sun and the stars has come to us through the spectroscope. The elements that we find by its means in the sun are also found in the same way in the stars. Matter, says the spectroscope, is essentially the same everywhere, in the earth and the sun, in the comet that visits us once in 1,000 years, in the star whose distance is incalculable, and in the great clouds of fire mist that we call nebulae. In considering the evolution of the stars, let us keep 2 points clearly in mind. The starting point, the nebula, is no figment of the scientific imagination. Hundreds of thousands of nebulae, besides even vaster irregular stretches of nebulous matter, exist in the heavens. But the stages of the evolution of this stuff into stars are very largely a matter of speculation. Possibly there is more than one line of evolution, and the various theories may be reconciled. And this applies also to the theories of the various stages through which the stars themselves pass on their way to extinction. The light of about 250,000 stars has been analyzed in the spectroscope, and it is found that they fall into about a dozen classes, which generally correspond to stages in their evolution. The age of stars. In its main lines, the spectrum of a star corresponds to its color, and we may roughly group the stars into red, yellow, and white. This is also the order of increasing temperature, the red stars being the coolest, and the white stars the hottest. We might therefore imagine that the white stars are the youngest, and that as they grow older and cooler they become yellowish, then red, and finally become invisible, just as a cooling white-hot iron would do. But a very interesting recent research shows that there are 2 kinds of red stars. Some of them are amongst the oldest stars, and some are amongst the youngest. The facts appear to be that when a star is first formed it is not very hot. It is an immense mass of diffuse gas glowing with a dull red heat. It contracts under the mutual gravitation of its particles, and as it does so it grows hotter. It acquires a yellowish tinge. As it continues to contract it grows hotter and hotter, until its temperature reaches a maximum as a white star. At this point the contraction process does not stop, but the heating process does. Further contraction is now accompanied by cooling, and the star goes through its color changes again, but this time in the inverse order. It contracts and cools to a yellow, and finally to red. But when it again becomes a red star, it is enormously denser and smaller than when it began as a red star. Consequently, the red stars are divided into two classes, called, appropriately, giants and dwarfs. This theory, which we owe to an American astronomer, H.N. Russell, has been successful in explaining a variety of phenomena, and there is consequently good reason to suppose it to be true. But the question as to how the red giant stars are formed has received less satisfactory and precise answers. The most commonly accepted theory is the nebular theory. The nebular theory, Part II. Nebulae are dim, luminous cloud-like patches in the heavens, more like wisps of smoke in some cases than anything else. Both photography and the telescope show that they are very numerous, hundreds of thousands being already known and the number being continually added to. They are not small. Most of them are immensely large. Actual dimensions cannot be given, because to estimate these we must first know definitely the distance of the nebulae from the earth. The distances of some nebulae are known approximately, and we can therefore form some idea of size in these cases. The results are staggering. The mere visible surface of some nebulae is so large that the whole stretch of the solar system would be too small to form a convenient unit for measuring it. A ray of light would require to travel for years to cross from side to side of such a nebula. Its immensity is inconceivable to the human mind. There appear to be two types of nebula, and there is evidence suggesting that the one type is only an earlier form of the other, but this again we do not know. The more primitive nebulae would seem to be composed of gas in an extremely rarefied form. It is difficult to convey an adequate idea of the rarity of nebular gases. The residual gases in a vacuum tube are dense by comparison. A cubic inch of air at ordinary pressure would contain more matter than is contained in millions of cubic inches of the gases of nebulae. The light of even the faintest stars does not seem to be dimmed by passing through a gaseous nebula, although we cannot be sure on this point. The most remarkable physical fact about these gases is that they are luminous. Whence they derive their luminosity we do not know. It hardly seems possible to believe that extremely thin gases exposed to the terrific cold of space can be so hot as to be luminous, and can retain their heat and their luminosity indefinitely. A cold luminosity due to electrification, like that of the aurora borealis, would seem to fit the case better. Now the nebular theory is that out of the great fire mists, such as we have described, stars are born. We do not know whether gravitation is the only or even the main force at work in a nebula, but it is supposed that under the action of gravity the far-flung fire mists would begin to condense round centres of greatest density, heat being evolved in the process. Of course, the condensation would be enormously slow, although the sudden eruption of a swarm of meteors or some solid body might hasten matters greatly by providing large, ready-made centres of condensation. Spiral nebulae. It is then supposed that the contracting mass of gas would begin to rotate and throw off gigantic streamers, which would, in their turn, form centres of condensation. The whole structure would thus form a spiral, having a dense region at its centre, and knots or lumps of condensed matter along its spiral arms. Besides the formless gaseous nebulae, there are hundreds of thousands of spiral nebulae, such as we have just mentioned, in the heavens. They are at all stages of development, and they are visible to us at all angles. That is to say, some of them face directly towards us, others are edge-on, and some are in intermediate positions. It appears, therefore, that we have here a striking confirmation of the nebular hypothesis. But we must not go so fast. There is some controversy as to the nature of these spiral nebulae. Some eminent astronomers think they are other stellar universes, comparable in size with our own. In any case, they are vast structures, and if they represent stars in process of condensation, they must be giving birth to huge agglomerations of stars, to star clusters at least. These vast and enigmatic objects do not throw much light on the origin of our own solar system. The nebular hypothesis, which was invented by Laplace to explain the origin of our solar system, has not yet met with universal acceptance. The explanation offers grave difficulties, and it is best, while the subject is still being closely investigated, to hold all opinions with reserve. It may be taken as probable, however, that the universe has developed from masses of incandescent gas. The Birth and Death of Stars. Part 3. Variable, new, and dark stars. Dying suns. Many astronomers believe that in variable stars we have another star, following that of the dullest red star, in the dying of suns. The light of these stars varies periodically in so many days, weeks, or years. It is interesting to speculate that they are slowly dying suns, in which the molten interior periodically bursts through the shell of thick vapours that is gathering round them. What we saw about our sun seems to point to some such stage in the future. That is, however, not the received opinion about variable stars. It may be that they are stars which periodically pass through a great swarm of meteors, or a region of space that is rich in cosmic dust of some sort, when of course a great illumination would take place. One class of these variable stars, which takes its name from the star Algol, is of special interest. Every third night Algol has its light reduced for several hours. Modern astronomy has discovered that in this case there are really two stars, circulating round a common centre, and that every third night the fainter of the two comes directly between us and its companion, and causes an eclipse. This was until recently regarded as a most interesting case in which a dead star revealed itself to us by passing before the light of another star. But astronomers have in recent years invented something, the selenium cell, which is even more sensitive than the photographic plate, and on this the supposed dead star registers itself as very much alive. Algol is, however, interesting in another way. The pair of stars which we have discovered in it are hundreds of trillions of miles away from the earth, yet we know their masses and their distances from each other. The Death and Birth of Stars. We have no positive knowledge of dead stars, which is not surprising when we reflect that a dead star means an invisible star. But when we see so many individual stars tending toward death, when we behold a vast population of all conceivable ages, we presume that there are many already dead. On the other hand, there is no reason to suppose that the universe as a whole is running down. Some writers have maintained this, but their argument implies that we know a great deal more about the universe than we actually do. The scientific man does not know whether the universe is finite or infinite, temporal or eternal, and he declines to speculate where there are no facts to guide him. He knows only that the great gaseous nebula promise myriads of worlds in the future, and he concedes the possibility that new nebulae may be forming in the ether of space. The last, and not the least interesting subject we have to notice, is the birth of a new star. This is an event which astronomers now announce every few years, and it is a far more portentous event than the reader imagines when it is reported in his daily paper. The story is much the same in all cases. We say that the star appeared in 1901, but you begin to realize the magnitude of the event when you learn that this distant blaze had really occurred about the time of the death of Luther. the light of the conflagration had been speeding toward us across space at 186,000 miles a second, yet it has taken nearly 3 centuries to reach us. To be visible at all to us at that distance, the fiery outbreak must have been stupendous. If a mass of petroleum 10 times the size of the earth were suddenly fired, it would not be seen at such a distance. The new star had increased its light many hundredfold in a few days. There is a considerable fascination about the speculation that in such cases we see the resurrection of a dead world, a means of renewing the population of the universe. What happens is that in some region of the sky where no star, or only a very faint star, had been registered on our charts, we almost suddenly perceive a bright star. In a few days it may rise to the highest brilliancy. By the spectroscope we learn that this distant blaze means a prodigious outpour of white-hot hydrogen at hundreds of miles a second. But the star sinks again after a few months, and we then find a nebula round it on every side. It is natural to suppose that a dead or dying sun has somehow been reconverted in whole or in part into a nebula. A few astronomers think that it may have partially collided with another star, or approached too closely to another, with the result we described in an earlier page. The general opinion now is that a faint or dead star had rushed into one of those regions of space in which there are immense stretches of nebulous matter, and been, at least in part, vaporized by the friction. But the difficulties are considerable, and some astronomers prefer to think that the blazing star may merely have lit up a dark nebula which already existed. It is one of those problems on which speculation is most tempting, but positive knowledge is still very incomplete. We may be content, even proud, that already we can take a conflagration that has occurred more than 1,000 trillion miles away and analyze it positively into an outflame of glowing hydrogen gas at so many miles a second. The shape of our universe. Part 4. Our universe, a spiral nebula. What is the shape of our universe, and what are its dimensions? This is a tremendous question to ask. It is like asking an intelligent insect, living on a single leaf in the midst of a great Brazilian forest, to say what is the shape and size of the forest. Yet immense ingenuity has proved equal to giving an answer even to this question, and by a method exactly similar to that which would be adopted by the insect. Suppose, for instance, that the forest was shaped as an elongated oval, and the insect lived on a tree near the center of the oval. If the trees were approximately equally spaced from one another, they would appear much denser along the length of the oval than across its width. This is the simple consideration that has guided astronomers in determining the shape of our stellar universe. There is one direction in the heavens along which the stars appear denser than in the directions at right angles to it. That direction is the direction in which we look towards the Milky Way. If we count the number of stars visible all over the heavens, we find they become more and more numerous as we approach the Milky Way. As we go further and further from the Milky Way, the stars thin out until they reach a maximum sparseness in directions at right angles to the plane of the Milky Way. We may consider the Milky Way to form, as it were, the equator of our system, and the line at right angles to point to the north and south poles. Our system, in fact, is shaped something like a lens, and our sun is situated near the center of this lens. In the remoter part of this lens, near its edge, or possibly outside it altogether, lies the great series of star clouds which make up the Milky Way. All the stars are in motion within this system, but the very remarkable discovery has been made that these motions are not entirely random. The great majority of the stars whose motions can be measured fall into two groups drifting past one another in opposite directions. The velocity of one stream relative to the other is about 25 miles per second. The stars forming these two groups are thoroughly well mixed. It is not a case of an inner stream going one way and an outer stream the other. But there are not quite as many stars going one way as the other. For every two stars in one stream there are three in the other. Now, as we have said, some eminent astronomers hold that the spiral nebulae are universes like our own. These spirals present features which, in the light of what we have just said about our system, are very remarkable. The nebula in Coma Berenices is a spiral edge-on to us, and it has precisely the lance-shaped middle and the general flattened shape that we have found in our own system. The nebula in Canis Venatici is a spiral facing towards us, and its shape irresistibly suggests motions along the spiral arms. This motion, whether it is towards or away from the central, lance-shaped portion, would cause a double streaming motion in that central portion of the kind we have found in our own system. Again, and altogether apart from these considerations, there are good reasons for supposing our Milky Way to possess a double-armed spiral structure, and the great patches of dark, absorbing matter which are known to exist in the Milky Way would give very much the mottled appearance we notice in the arms, which we see edge-on, of the nebula in Coma Berenices. The hypothesis, therefore, that our universe is a spiral nebula has much to be said for it. If it be accepted, it greatly increases our estimate of the size of the material universe. For our central, lance-shaped system is calculated to extend towards the Milky Way for more than 20,000 times a million miles, and about a third of this distance towards what we have called the poles. If, as we suppose, each spiral nebula is an independent stellar universe comparable in size with our own, then, since there are hundreds of thousands of spiral nebulae, we see that the size of the whole material universe is indeed beyond our comprehension. Astronomical Instruments. Part I. The Telescope. The instruments used in modern astronomy are almost the finest triumphs of mechanical skill in the world. In a great modern observatory the different instruments are to be counted by the score, but there are two which stand out preeminent as the fundamental instruments of modern astronomy. These instruments are the telescope and the spectroscope, and without them astronomy, as we know it, could not exist. There is still some dispute as to where and when the first telescope was constructed. As an astronomical instrument, however, it dates from the time of the great Italian scientist Galileo, which, with a very small and imperfect telescope of his own invention, first observed the spots on the sun, the mountains of the moon, and the chief four satellites of Jupiter. A good pair of modern binoculars is superior to this early instrument of Galileo's, and the history of telescope construction, from that primitive instrument to the modern giant recently erected on Mount Wilson, California, is an exciting chapter in human progress. But the early instruments have only an historic interest. The era of modern telescopes began in the 19th century. During the last century, telescope construction underwent an unprecedented development. An immense amount of interest was taken in the construction of large telescopes, and the different countries of the world entered on an exciting race to produce the most powerful possible instruments. Besides this rivalry of different countries, there was a rivalry of methods. The telescope developed along two different lines, and each of these two types has its partisans at the present day. These types are known as refractors and reflectors, and it is necessary to mention briefly the principles employed in each. The refractor is the ordinary, familiar type of telescope. It consists essentially of a large lens at one end of a tube and a small lens, called the eyepiece, at the other. The function of the large lens is to act as a sort of gigantic eye. It collects a large amount of light, an amount proportional to its size, and brings this light to a focus within the tube of the telescope. It thus produces a small but bright image, and the eyepiece magnifies this image. In the reflector, instead of a large lens at the top of the tube, a large mirror is placed at the bottom. This mirror is so shaped as to reflect the light that falls on it to a focus, whence the light is again led to an eyepiece. Thus the refractor and the reflector differ chiefly in their manner of gathering light. The powerfulness of the telescope depends on the size of the light gatherer. A telescope with a lens 4 inches in diameter is 4 times as powerful as the one with a lens of 2 inches in diameter, for the amount of light gathered obviously depends on the area of the lens, and the area varies as the square of the diameter. The largest telescopes at present in existence are reflectors. It is much easier to construct a very large mirror than to construct a very large lens. It is also cheaper. A mirror is more likely to get out of order than is a lens, however, and any irregularity in the shape of a mirror produces a greater distorting effect than in a lens. A refractor is also more convenient to handle than is a reflector. For these reasons, great refractors are still made, but the largest of them, the great Yerkes refractor, is much smaller than the greatest reflector, the one on Mount Wilson, California. The lens of the Yerkes refractor measures 3 feet 4 inches in diameter, whereas the Mount Wilson reflector has a diameter of no less than 8 feet 4 inches. But there is a device whereby the power of these giant instruments, great as it is, can be still further heightened. That device is the simple one of allowing the photographic plate to take the place of the human eye. Nowadays an astronomer seldom spends the night with his eye glued to the great telescope. He puts a photographic plate there. The photographic plate has this advantage over the eye, that it builds up impressions. However long we stare at an object too faint to be seen, we shall never see it. With the photographic plate, however, faint impressions go on accumulating. As hour after hour passes, the star which was too faint to make a perceptible impression on the plate goes on affecting it until finally it makes an impression which can be made visible. In this way the photographic plate reveals to us phenomena in the heavens which cannot be seen through the most powerful telescopes. Telescopes of the kind we have been discussing, telescopes for exploring the heavens, are mounted equatorially. That is to say, they are mounted on an inclined pillar parallel to the axis of the earth, so that, by rotating round this pillar, the telescope is enabled to follow the apparent motion of a star due to the rotation of the earth. This motion is effected by clockwork, so that, once adjusted on the star, and the clockwork started, the telescope remains adjusted on that star for any length of time that is desired. But a great official observatory, such as Greenwich Observatory or the observatory at Paris, has also transit instruments, or telescopes smaller than the equatorials and without the same facility of movement, but which, by a number of exquisite refinements, are more adapted to accurate measurements. It is these instruments which are chiefly used in the compilation of the nautical almanac. They do not follow the apparent motion of the stars. stars are allowed to drift across the field of vision, and as each star crosses a small group of parallel wires in the eyepiece, its precise time of passage is recorded. Owing to their relative fixity of position, these instruments can be constructed to record the positions of stars with much greater accuracy than is possible to the more general and flexible mounting of equatorials. The recording of transit is comparatively dry work. The spectacular element is entirely absent. Stars are treated merely as mathematical points. But these observations furnish the very basis of modern mathematical astronomy, and without them such publications as the Nautical Almanac and the Connaissance du Temps would be robbed of the greater part of their importance. Part II. The Spectroscope. We have already learnt something of the principles of the spectroscope, the instrument which, by making it possible to learn the actual constitution of the stars, has added a vast new domain to astronomy. In the simplest form of this instrument, the analyzing portion consists of a single prism. Unless the prism is very large, however, only a small degree of dispersion is obtained. It is obviously desirable for accurate analytical work that the dispersion, that is, the separation of the different parts of the spectrum, should be as great as possible. The dispersion can be increased by using a large number of prisms, the light emerging from the first prism, entering the second, and so on. In this way, each prism produces its own dispersive effect, and when a number of prisms are employed, the final dispersion is considerable. A considerable amount of light is absorbed in this way, however, so that, unless our primary source of light is very strong, the final spectrum will be very feeble and hard to decipher. Another way of obtaining considerable dispersion is by using a diffraction grating instead of a prism. This consists generally of a piece of glass on which lines are ruled by a diamond point. When the lines are sufficiently close together, they split up light falling on them into its constituents and produce a spectrum. The modern diffraction grating is a truly wonderful piece of work. It contains several thousands of lines to the inch, and these lines have to be spaced with the greatest accuracy. But in this instrument, again, there is a considerable loss of light. We have said that every substance has its own distinctive spectrum, and it might be thought that, when a list of spectra of different substances has been prepared, spectrum analysis would become perfectly straightforward. In practice, however, things are not quite so simple. The spectrum emitted by a substance is influenced by a variety of conditions. The pressure, the temperature, the state of motion of the object we are observing, all make a difference, and one of the most laborious tasks of the modern spectroscopist is to disentangle these effects from one another. Simple as it is in its broad outlines, spectroscopy is, in reality, one of the most intricate branches of modern science. End of section 2.
Section 3 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Anna Simon. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 3. Part 2. The Story of Evolution. Introductory. The beginning of the Earth. Making a home for life. The first living creatures. 1. The evolution idea is a master key that opens many doors. It is a luminous interpretation of the world, throwing the light of the past upon the present. Everything is seen to be in antiquity, with a history behind it, a natural history, which enables us to understand in some measure how it has come to be as it is. We cannot say more than understand in some measure, for while the fact of evolution is certain, we are only beginning to discern the factors that have been at work. The evolution idea is very old, going back to some of the Greek philosophers, but it is only in modern times that it has become an essential part of our mental equipment. It is now an everyday intellectual tool. It was applied to the origin of the solar system and to the making of the earth before it was applied to plants and animals. It was extended from these to man himself. It spread to language, to folkways, to institutions. Within recent years, the evolution idea has been applied to the chemical elements, for it appears that uranium may change into radium, that radium may produce helium, and that lead is the final stable result when the changes of uranium are complete. Perhaps all the elements may be the outcome of an inorganic evolution. Not less important is the extension of the evolution idea to the world within as well as to the world without. For alongside of the evolution of bodies and brains is the evolution of feelings and emotions, ideas and imagination. Organic evolution means that the present is the child of the past and the parent of the future. It is not a power or a principle. It is a process of becoming. It means that the present-day animals and plants, and all the subtle interrelations between them, have arisen in a natural, knowable way from a preceding state of affairs, on the whole somewhat simpler, and that again from forms and interrelations simpler still, and so on backwards and backwards for millions of years, till we lose all clues in the thick mist that hangs over life's beginnings. Our solar system was once represented by a nebula of some sort, and we may speak of the evolution of the sun and the planets. But since it has been the same material throughout, that has changed in its distribution and forms, it might be clearer to use some word like genesis. Similarly, our human institutions were once very different from what they are now, and we may speak of the evolution of government or of cities. But man works with a purpose, with ideas and ideals in some measure controlling his actions and guiding his achievements, so that it is probably clearer to keep the good old word history for all processes of social becoming in which man has been a conscious agent. Now, between the genesis of the solar system and the history of civilization, there comes the vast process of organic evolution. The word development should be kept for the becoming of the individual, the chick out of the egg, for instance. Organic evolution is a continuous natural process of racial change by successive steps in a definite direction, whereby distinctively new individualities arise, take root, and flourish, sometimes alongside of, and sometimes, sooner or later, in place of, the originative stock. Our domesticated breeds of pigeons and poultry are the results of evolutionary change whose origins are still with us, in the rock dove and the jungle fowl, but in most cases in wild nature the ancestral stocks of present-day forms are long since extinct, and in many cases they are unknown. Evolution is a long process of coming and going, appearing and disappearing, a long drawn-out, sublime process like a great piece of music. 2. The beginning of the earth. When we speak the language of science, we cannot say "in the beginning," for we do not know of and cannot think of any condition of things that did not arise from something that went before. But we may qualify the phrase and legitimately inquire into the beginning of the earth within the solar system. If the result of this inquiry is to trace the sun and the planets back to a nebula, we reach only a relative beginning. The nebula has to be accounted for. And even before matter there may have been a pre-material world. If we say, as was said long ago, "in the beginning was mind," we may be expressing or trying to express a great truth, but we've gone beyond science. The nebular hypothesis. One of the grandest pictures that the scientific mind has ever thrown upon the screen is that of the nebular hypothesis. According to Laplace's famous form of this theory, 1796, the solar system was once a gigantic glowing mass, spinning slowly and uniformly around its center. As the incandescent world cloud of gas cooled and its speed of rotation increased, the shrinking mass gave off a separate whirling ring, which broke up and gathered together again as the first and most distant planet. The main mass gave off another ring, and another, till all the planets, including the earth, were formed. The central mass persisted as the sun. Laplace spoke of his theory, which Kant had anticipated 41 years before, with scientific caution. Quote, "Conjectures which I present with all the distrust which everything not the result of observation or of calculation ought to inspire." End quote. Subsequent research justified his distrust, for it has been shown that the original nebula need not have been hot and need not have been gaseous. Moreover, there are great difficulties in Laplace's theory of the separation of successive rings from the main mass, and of the condensation of a whirling gaseous ring into a planet. So it has come about that the picture of a hot gaseous nebula revolving as a unit body has given place to other pictures. Thus Sir Norman Lockyer pointed out, 1890, that the earth is gathering to itself millions of meteorites every day. This has been going on for millions of years. In distant ages the accretion may have been vastly more rapid and voluminous, and so the earth has grown. Now the meteoritic contributions are undoubted, but they require a centre to attract them, and the difficulty is to account for the beginning of a collecting centre or planetary nucleus. Moreover, meteorites are sporadic and erratic, scattered hither and thither rather than collecting into unit bodies. As Professor Chamberlain says, quote, "Meteorites have rather the characteristics of the wreckage of some earlier organization than of the parentage of our planetary system." End quote. Several other theories have been propounded to account for the origin of the earth, but the one that has found most favor in the eyes of authority is that of Chamberlain and Moulton. According to this theory, a great nebular mass condensed to form the sun, from which, under the attraction of passing stars, planet after planet, the earth included, was heaved off in the form of knotted spiral nebulae, like many of those now observed in the heavens. Of great importance were the knots, for they served as collecting centers, drawing flying matter into their clutches. Whatever part of the primitive bolt escaped and scattered was drawn out into independent orbits round the sun, forming the planetesimals, which behave like minute planets. These planetesimals formed the food on which the knots subsequently fed. The growth of the earth. It has been calculated that the newborn earth, the earth knot of Chamberlain's theory, had a diameter of about 5,500 miles, but it grew by drawing planetesimals into itself until it had a diameter of over 8,100 miles at the end of its growing period. Since then it has shrunk, by periodic shrinkages which have meant the buckling up of successive series of mountains, and it has now a diameter of 7,918 miles. But during the shrinking the earth became more varied. A sort of slow boiling of the internally hot earth often forced molten matter through the cold outer crust, and there came about a gradual assortment of lighter materials nearer the surface and heavier materials deeper down. The continents are built of the lighter materials, such as granites, while the beds of the great oceans are made of the heavier materials, such as basalts. In limited areas land has often become sea, and sea has often given place to land, but the probability is that the distinction of the areas corresponding to the great continents and oceans goes back to a very early stage. The lithosphere is the more or less stable crust of the earth, which may have been, to begin with, about 50 miles in thickness. It seems that the young earth had no atmosphere, and that ages passed before water began to accumulate on its surface. Before, in other words, there was any hydrosphere. The water came from the earth itself, to begin with, and it was long before there was any rain, dissolving out saline matter from the exposed rocks and making the sea salt. The weathering of the high grounds of the ancient crust by air and water furnished the material which formed the sandstones and mudstones and other sedimentary rocks, which are said to amount to a thickness of over 50 miles in all. 3. Making a home for life. It is interesting to inquire how the callous, rough-and-tumble conditions of the outer world in early days were replaced by others that allowed of the germination and growth of that tender plant we call life. There are very tough living creatures, but the average organism is ill-suited for violence. Most living creatures are adapted to mild temperatures and gentle reactions. Hence the fundamental importance of the early atmosphere, heavy with planetesimal dust, in blanketing the earth against intensities of radiance from without, as Chamberlain says, and inequalities of radiance from within. This was the first preparation for life, but it was an atmosphere without free oxygen. Not less important was the appearance of pools and lakelets, of lakes and seas. Perhaps the early waters covered the earth, and water was the second preparation for life. Water that can dissolve a larger variety of substances in greater concentration than any other liquid. Water that in summer does not readily evaporate altogether from a pond, nor in winter freeze throughout its whole extent. Water that is such a mobile vehicle and such a subtle cleaver of substances. Water that forms over 80% of living matter itself. Of great significance was the abundance of carbon, hydrogen, and oxygen, in the form of carbonic acid and water, in the atmosphere of the cooling earth, for these three wonderful elements have a unique ensemble of properties, ready to enter into reactions and relations, making great diversity and complexity possible, favoring the formation of the plastic and permeable materials that build up living creatures. We must not pursue the idea, but it is clear that the stones and mortar of the inanimate world are such that they build a friendly home for life. Origin of living creatures upon the earth. During the early chapters of the earth's history, no living creature that we can imagine could possibly have lived there. The temperature was too high, there was neither atmosphere nor surface water. Therefore it follows that at some uncertain but inconceivably distant date, living creatures appeared upon the earth. No one knows how, but it is interesting to consider possibilities. From ancient times it has been a favorite answer that the dust of the earth may have become living in a way which is outside scientific description. This answer forecloses the question, and it is far too soon to do that. Science must often say ignoramus. Science should be slow to say ignorabimus. A second position held by Helmholtz, Lord Kelvin, and others suggests that minute living creatures may have come to the earth from elsewhere, in the cracks of a meteorite or among cosmic dust. It must be remembered that such can survive prolonged exposure to very low temperatures, that seeds can survive prolonged exposure to very low temperatures, that spores of bacteria can survive high temperature, that seeds of plants and germs of animals in a state of latent life can survive prolonged drought and absence of oxygen. It is possible, according to Berthelot, that as long as there is not molecular disintegration, vital activities may be suspended for a time, and may afterwards recommence when appropriate conditions are restored. Therefore, one should be slow to say that a long journey through space is impossible. The obvious limitation of Lord Kelvin's theory is that it only shifts the problem of the origin of organisms, that is, living creatures, from the earth to elsewhere. The third answer is that living creatures of a very simple sort may have emerged on the earth's surface from not living material, for example from some semi-fluid carbon compounds activated by ferments. The tenability of this view is suggested by the achievements of the synthetic chemists, who are able artificially to build up substances such as oxalic acid, indigo, salicylic acid, caffeine, and grape sugar. We do not know, indeed, what in nature's laboratory would take the place of the clever synthetic chemist, but there seems to be a tendency to complexity. Corpuscles form atoms, atoms form molecules, small molecules large ones. Various concrete suggestions have been made in regard to the possible origin of living matter, which will be dealt with in a later chapter. So far as we know of what goes on today, there is no evidence of spontaneous generation. Organisms seem always to arise from pre-existing organisms of the same kind. Where any suggestion of the contrary has been fancied, there have been flaws in the experimenting. But it is one thing to accept the verdict omne vivum e vivo, as a fact to which experiment has not yet discovered an exception, and another thing to maintain that this must always have been true, or must always remain true. If the synthetic chemists should go on surpassing themselves, if substances like white of egg should be made artificially, and if we should get more light on possible steps by which simple living creatures may have arisen from not living materials, this would not greatly affect our general outlook on life, though it would increase our appreciation of what is often libelled as inert matter. If the dust of the earth did naturally give rise very long ago to living creatures, if they are in a real sense born of her and of the sunshine, then the whole world becomes more continuous and more vital, and all the inorganic groaning and travailing becomes more intelligible. 4. The first organisms upon the earth. We cannot have more than a speculative picture of the first living creatures upon the earth, or rather in the waters that covered the earth. A basis for speculation is to be found, however, in the simplest creatures living today, such as some of the bacteria and one-celled animalcules, especially those called protists, which have not taken any very definite step towards becoming either plants or animals. No one can be sure, but there is much to be said for the theory that the first creatures were microscopic globules of living matter, not unlike the simplest bacteria of today, but able to live on air, water, and dissolved salts. From such a source may have originated a race of one-celled marine organisms which were able to manufacture chlorophyll, or something like chlorophyll, that is to say, the green pigment which makes it possible for plants to utilize the energy of the sunlight in breaking up carbon dioxide and in building up, photosynthesis, carbon compounds like sugars and starch. These little units were probably encased in a cell wall of cellulose, but their boxed-in energy expressed itself in the undulatory movement of a lash or flagellum, by means of which they propelled themselves energetically through the water. There are many similar organisms today, mostly in water, but some of them, simple one-celled plants, paint the tree stems and even the paving stones green in wet weather. According to Professor A.H. Church, there was a long chapter in the history of the earth when the sea that covered everything teemed with these green flagellates, the originators of the vegetable kingdom. On another tack, however, there probably evolved a series of simple predatory creatures, not able to build up organic matter from air, water, and salts, but devouring their neighbors. These units were not closed in with cellulose, but remained naked, with their living matter or protoplasm flowing out in changeful processes, such as we see in the amoeba in the ditch, or in our own white blood corpuscles and other amoeboid cells. These were the originators of the animal kingdom. Thus, from very simple protists, the first animals and the first plants may have arisen. All were still very minute, and it is worth remembering that had there been any scientific spectator after our kind upon the earth during these long ages, he would have lamented the entire absence of life, although the seas were teeming. The simplest forms of life and the protoplasm which Huxley called the physical basis of life will be dealt with in the chapter on biology in a later section of this work. First great steps in evolution, the first plants, the first animals, beginnings of bodies, evolution of sex, beginning of natural death. 1. The contrast between plants and animals. However it may have come about, there is no doubt at all that one of the first great steps in organic evolution was the forking of the genealogical tree into plants and animals, the most important parting of the ways in the whole history of nature. Typical plants have chlorophyll. They are able to feed at a low chemical level on air, water, and salts, using the energy of the sunlight in their photosynthesis. They have their cells boxed in by cellulose walls, so that their opportunities for motility are greatly restricted. They manufacture much more nutritive material than they need, and live far below their income. They have no ready way of getting rid of any nitrogenous waste matter that they may form, and this probably helps to keep them sluggish. Animals, on the other hand, feed at a high chemical level on the carbohydrates, for example starch and sugar, fats, and proteins, for example gluten, albumin, casein, which are manufactured by other animals, or to begin with by plants. Their cells have not cellulose walls, nor in most cases much wool of any kind, and motility in the majority is unrestricted. Animals live much more nearly up to their income. If we could make, for an animal and a plant of equal weight, two fractions showing the ratio of the upbuilding, constructive chemical processes to the downbreaking, disruptive chemical processes that go on in their respective bodies, the ratio for the plant would be much greater than the corresponding ratio for the animal. In other words, animals take the munitions which plants laboriously manufacture and explode them in locomotion and work, and the entire system of animate nature depends upon the photosynthesis that goes on in green plants. As the result of much more explosive life, animals have to deal with much in the way of nitrogenous waste products, the ashes of the living fire, but these are usually got rid of very effectively, for example in the kidney filters, and do not clog the system by being deposited as crystals and the like, as happens in plants. Sluggish animals like sea squirts, which have no kidneys, are exceptions that prove the rule, and it need hardly be said that the statements that have been made in regard to the contrasts between plants and animals are general statements. There is often a good deal of the plant about the animal, as in sedentary sponges, zoophytes, corals, and sea squirts, and there is often a little of the animal about the plant, as we see in the movements of all shoots and roots and leaves, and occasionally in the parts of the flower. But the important fact is that on the early forking of the genealogical tree, that is, the divergence of plants and animals, there depended and depends all the higher life of the animal kingdom, not to speak of mankind. The continuance of civilization, the upkeep of the human and animal population of the globe, and even the supply of oxygen to the air we breathe, depend on the silent laboratories of the green leaves, which are able with the help of the sunlight to use carbonic acid, water, and salts to build up the bread of life. 2. The beginning of land plants. It is highly probable that for long ages the waters covered the earth, and that all the primeval vegetation consisted of simple flagellates in the universal open sea. But contraction of the earth's crust brought about elevations and depressions of the sea floor, and in places the solid substratum was brought near enough the surface to allow the floating plants to begin to settle down without getting out of the light. This is how Professor Church pictures the beginning of a fixed vegetation, a very momentous step in evolution. It was perhaps among this early vegetation that animals had their first successes. As the floor of the sea in these shallow areas was raised higher and higher, there was a beginning of dry land. The sedentary plants already spoken of were the ancestors of the shore seaweeds, and there is no doubt that when we go down at the lowest tide and wade cautiously out among the jungle vegetation, only exposed on such occasions, we are getting a glimpse of very ancient days. This is the forest primeval. The protozoa. Animals below the level of zoophytes and sponges are called protozoa. The word obviously means first animals, but all that we can say is that the very simplest of them may give us some hint of the simplicity of the original first animals, for it is quite certain that the vast majority of the protozoa today are far too complicated to be thought of as primitive. Though most of them are microscopic, each is an animal complete in itself, with the same fundamental bodily attributes as are manifested in ourselves. They differ from animals of higher degree in not being built up of the unit areas or corpuscles called cells. They have no cells, no tissues, no organs, in the ordinary acceptation of these words, but many of them show a great complexity of internal structure, far exceeding that of the ordinary cells that build up the tissues of higher animals. They are complete living creatures which have not gone in for body making. In the dim and distant past there was a time when the only animals were of the nature of protozoa, and it is safe to say that one of the great steps in evolution was the establishment of three great types of protozoa. A. Some were very active, the infusorians, like the slipper animalcule, the nightlight, Noctiluca, which makes the sea phosphorescent at night, and the deadly trypanosome, which causes sleeping sickness. B. Others were very sluggish, the parasitic sporozoa, like the malaria organism which the mosquito introduces into man's body. C. Others were neither very active nor very passive, the rhizopods, with outflowing processes of living matter. This amoeboid line of evolution has been very successful. It is represented by the rhizopods, such as amoeba and the chalk-forming foraminifera, and the exquisitely beautiful flint-shelled radiolarians of the open sea. They have their counterparts in the amoeboid cells of most multicellular animals, such as the phagocytes which migrate about in the body, engulfing and digesting intruding bacteria, serving as sappers and miners when something has to be broken down and built up again, and performing other useful offices. 3. The making of a body. The great naturalist Louis Agassiz once said that the biggest gulf in organic nature was that between the unicellular and the multicellular animals, protozoa and metazoa. But the gulf was bridged very long ago, when sponges, stinging animals, and simple worms were evolved, and showed for the first time a body. What would one not give to be able to account for the making of a body, one of the great steps in evolution? No one knows, but the problem is not altogether obscure. When an ordinary protozoan or one-celled animal divides into two or more, which is its way of multiplying, the daughter units thus formed float apart and live independent lives. But there are a few protozoa in which the daughter units are not quite separated off from one another, but remain coherent. Thus Volvox, a beautiful green ball, found in some kennels and the like, is a colony of 1,000 or even 10,000 cells. It has almost formed a body. But in this colony-making protozoan, and in others like it, the component cells are all of one kind, whereas in true multicellular animals there are different kinds of cells, showing division of labour. There are some other protozoa in which the nucleus or kernel divides into many nuclei within the cell. This is seen in the giant amoeba, Pelomyxa, sometimes found in duck ponds, or the beautiful Opalina, which always lives in the hind part of the frog's foot canal. If a portion of the living matter of these protozoa should gather round each of the nuclei, then that would be the beginning of a body. It would be still nearer the beginning of a body if division of labour set in, and if there was a setting apart of egg cells and sperm cells distinct from body cells. It was possibly in some such way that animals and plants with a body were first evolved. 2 points should be noticed: that body making is not essentially a matter of size, though it made large size possible, for the body of a many-celled wheel animalcule or rotifer is no bigger than many a protozoan. Yet the rotifer, we are thinking of Hydatina, has 900 odd cells, whereas the protozoan has only 1, except in forms like Volvox. Secondly, it is a luminous fact that every many-celled animal from sponge to man that multiplies in the ordinary way begins at the beginning again as a single cell, the fertilized egg cell. It is of course not an ordinary single cell that develops into an earthworm or a butterfly, an eagle or a man. It is a cell in which a rich inheritance, the fruition of ages, is somehow condensed. But it is interesting to bear in mind the elementary fact that every many-celled creature, reproduced in the ordinary way, and not by budding or the like, starts as a fertilized egg cell. The coherence of the daughter cells into which the fertilized egg cell divides is a reminiscence, as it were, of the primeval coherence of daughter units that made the first body possible. The beginning of sexual reproduction. A freshwater hydra, growing on the duckweed, usually multiplies by budding. It forms daughter buds, living images of itself. A check comes to nutrition, and these daughter buds go free. A big sea anemone may divide in 2 or more parts, which become separate animals. This is asexual reproduction, which means that the multiplication takes place by dividing into 2 or many portions, and not by liberating egg cells and sperm cells. Among animals, as among plants, asexual reproduction is very common. But it has great disadvantages, for it is apt to be physiologically expensive, and it is beset with difficulties when the body shows great division of labour, and is very intimately bound into unity. Thus no one can think of a bee or a bird multiplying by division or by budding. Moreover, if the body of the parent has suffered from injury or deterioration, the result of this is bound to be handed on to the next generation if asexual reproduction is the only method. Splitting into 2 or many parts was the old-fashioned way of multiplying, but one of the great steps in evolution was the discovery of a better method, namely sexual reproduction. The gist of this is simply that during the process of body building, by the development of the fertilized egg cell, certain units, the germ cells, do not share in forming ordinary tissues or organs, but remain apart, continuing the full inheritance which was condensed in the fertilized egg cell. These cells, kept by themselves, are the originators of the future reproductive cells of the mature animal. They give rise to the egg cells and the sperm cells. The advantages of this method are great. 1. The new generation is started less expensively, for it is easier to shed germ cells into the cradle of the water than to separate off half of the body. 2. It is possible to start a great many new lives at once, and this may be of vital importance when the struggle for existence is very keen and when parental care is impossible. 3. The germ cells are little likely to be prejudicially affected by disadvantageous dints impressed on the body of the parent, little likely unless the dints have peculiarly penetrating consequences, as in the case of poisons. 4. A further advantage is implied in the formation of two kinds of germ cells, the ovum or egg cell, with a considerable amount of building material and often with a legacy of nutritive yolk, the spermatozoon or sperm cell, adapted to move in fluids and to find the ovum from a distance, thus securing change-provoking cross-fertilization. 4. The evolution of sex. Another of the great steps in organic evolution was the differentiation of two different physiological types, the male or sperm producer and the female or egg producer. It seems to be a deep-seated difference in constitution which leads one egg to develop into a male, and another, lying beside it in the nest, into a female. In the case of pigeons, it seems almost certain, from the work of Professor Oscar Riddle, that there are two kinds of egg, a male-producing egg and a female-producing egg, which differ in their yolk-forming and other physiological characters. In sea urchins we often find two creatures superficially indistinguishable, but the one is a female with large ovaries, and the other is a male with equally large testes. Here the physiological difference does not affect the body as a whole, but the reproductive organs or gonads only, though more intimate physiology would doubtless discover differences in the blood or in the chemical routine, metabolism. In a large number of cases, however, there are marked superficial differences between the sexes, and everyone is familiar with such contrasts as peacock and peahen, stag and hind. In such cases the physiological difference between the sperm producer and the ovum producer, for this is the essential difference, saturates through the body and expresses itself in masculine and feminine structures and modes of behavior. The expression of the masculine and feminine characters is in some cases under the control of hormones or chemical messengers which are carried by the blood from the reproductive organs throughout the body, and pull the trigger which brings about the development of an antler or a wattle or a decorative plume or a capacity for vocal and saltatory display. In some cases it is certain that the female carries in a latent state the masculine features, but these are kept from expressing themselves by other chemical messengers from the ovary. Of these chemical messengers more must be said later on. Recent research has shown that while the difference between male and female is very deep-rooted, corresponding to a difference in gearing, it is not always clear-cut. Thus a hen pigeon may be very masculine, and a cock pigeon very feminine. The difference is in degree, not in kind. 5. What is the meaning of the universal, or almost universal, inevitableness of death? A sequoia, or big tree, of California has been known to live for over 2,000 years, but eventually it died. A centenarian tortoise has been known, and a sea anemone 60 years of age, but eventually they die. What is the meaning of this apparently inevitable stoppage of bodily life? The beginning of natural death. There are three chief kinds of death. A. The great majority of animals come to a violent end, being devoured by others or killed by sudden and extreme changes in their surroundings. B. When an animal enters a new habitat or comes into new associations with other organisms, it may be invaded by a microbe or by some larger parasite to which it is unaccustomed and to which it can offer no resistance. With many parasites a live and let live compromise is arrived at, but new parasites are apt to be fatal, as man knows to his cost when he is bitten by a tsetse fly which infects him with a microscopic animal, a trypanosome, that causes sleeping sickness. In many animals the parasites are not troublesome as long as the host is vigorous, but if the host is out of condition the parasites may get the upper hand, as in the so-called grouse disease, and become fatal. C. But besides violent death and microbic or parasitic death, there is natural death. This is in great part to be regarded as the price paid for a body. A body worth having implies complexity or division of labor, and this implies certain internal furnishings of a more or less stable kind, in which the effects of wear and tear are apt to accumulate. It is not the living matter itself that grows old, so much as the framework in which it works, the furnishings of the vital laboratory. There are various processes of rejuvenescence, for example, rest, repair, change, reorganization, which work against the inevitable processes of senescence, but sooner or later the victory is with aging. Another deep reason for natural death is to be found in the physiological expensiveness of reproduction, for many animals, from worms to eels, illustrate natural death as the nemesis of starting new lives. Now it is a very striking fact that to a large degree the simplest animals of protozoa are exempt from natural death. They are so relatively simple that they can continually recuperate by rest and repair. They do not accumulate any bad deaths. Moreover, their modes of multiplying, by dividing into two or many units, are very inexpensive physiologically. It seems that in some measure this bodily immortality of the protozoa is shared by some simple many-celled animals like the freshwater hydra and planarian worms. Here is an interesting chapter in evolution, the evolution of means of evading or staving off natural death. Thus there is the well-known case of the pallilar worm of the coral reefs, where the body breaks up in liberating the germ cells, but the head end remains fixed in a crevice of the coral and buds out a new body at leisure. Along with the evolution of the ways of avoiding death should be considered also the gradual establishment of the length of life best suited to the welfare of the species, and the punctuation of the life history to suit various conditions. 6. Great acquisitions. In animals like sea anemones and jellyfishes, the general symmetry of the body is radial, that is to say, there is no right or left, and the body might be halved along many planes. It is a kind of symmetry well suited for sedentary or for drifting life. But worms began the profitable habit of moving with one end of the body always in front, and from worms to man the great majority of animals have bilateral symmetry. They have a right and a left side, and there is only one cut that halves the body. This kind of symmetry is suited for a more strenuous life than radial animals show. It is suited for pursuing food, for avoiding enemies, for chasing mates. And with the establishment of bilateral symmetry must be associated the establishment of head brains, the beginning of which is to be found in some simple worm types. Among the other great acquisitions gradually evolved, we may notice a well-developed head with sense organs, the establishment of large internal surfaces such as the digestive and absorptive wall of the food canal, the origin of quickly contracting striped muscle and of muscular appendages, the formation of blood as a distributing medium throughout the body, from which all the parts take what they need and to which they also contribute. Another very important acquisition, almost confined, so far as is known, to backboned animals, was the evolution of what are called glands of internal secretion, such as the thyroid and the suprarenal. These manufacture subtle chemical substances which are distributed by the blood throughout the body, and have a manifold influence in regulating and harmonizing the vital processes. Some of these chemical messengers are called hormones, which stimulate organs and tissues to greater activity. Others are called chalones, which put on a brake. Some regulate growth, and others rapidly alter the pressure and composition of the blood. Some of them call into active development certain parts of the body which have been, as it were, waiting for an appropriate trigger pulling. Thus, at the proper time, the milk glands of a mammalian mother are awakened from their dormancy. This very interesting outcome of evolution will be dealt with in another portion of this work. End of section 3.
Section 4 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 4. Part 2. The Story of Evolution, continued. The Inclined Plane of Animal Behavior. 1. Before passing to a connected story of the gradual emergence of higher and higher forms of life in the course of the successive ages, the procession of life as it may be called, it will be useful to consider the evolution of animal behavior. Evolution of mind. A human being begins as a microscopic fertilized egg cell, within which there is condensed the long result of time, man's inheritance. The long period of 9 months before birth, with its intimate partnership between mother and offspring, is passed as if it were in sleep, and no one can make any statement in regard to the mind of the unborn child. Even after birth, the dawn of mind is as slow as it is wonderful. To begin with, there is in the ovum and early embryo no nervous system at all, and it develops very gradually from simple beginnings. Yet as mentality cannot come in from outside, we seem bound to conclude that the potentiality of it, whatever that means, resides in the individual from the very first. The particular kind of activity known to us as thinking, feeling, and willing is the most intimate part of our experience, known to us directly apart from our senses, and the possibility of that must be implicit in the germ cell, just as the genius of Newton was implicit in a very miserable specimen of an infant. Now what is true of the individual is true also of the race. There is a gradual evolution of that aspect of the living creature's activity which we call mind. We cannot put our finger on any point and say, before this stage there was no mind. Indeed, many facts suggest the conclusion that wherever there is life there is some degree of mind, even in the plants. Or it might be more accurate to put the conclusion in another way, that the activity we call life has always in some degree an inner or mental aspect. In another part of this book there is an account of the dawn of mind in backboned animals. What we aim at here is an outline of what may be called the inclined plane of animal behavior. A very simple animal accumulates a little store of potential energy, and it proceeds to expend this, like an explosive, by acting on its environment. It does so in a very characteristic self-preservative fashion, so that it burns without being consumed and explodes without being blown to bits. It is characteristic of the organism that it remains a going concern for a longer or shorter period, its length of life. Living creatures that expended their energy ineffectively or self-destructively would be eliminated in the struggle for existence. When a simple one-celled organism explores a corner of the field seen under a microscope, behaving to all appearance very like a dog scouring a field seen through a telescope, it seems permissible to think of something corresponding to mental endeavor associated with its activity. This impression is strengthened when an amoeba pursues another amoeba, overtakes it, engulfs it, loses it, pursues it again, recaptures it, and so on. What is quite certain is that the behavior of the animalcule is not like that of a potassium pill fizzing about in a basin of water, nor like the lurching movements of a gun that has got loose and taken charge on board ship. Another feature is that the locomotor activity of an animalcule often shows a distinct individuality. It may swim, for instance, in a loose spiral. But there is another side to vital activity besides acting upon surrounding world. The living creature is acted on by influences from without. The organism acts on its environment. That is the one side of the shield. The environment acts upon the organism. That is the other side. If we are to see life whole, we must recognize these two sides of what we call living, and it is missing an important part of the history of animal life if we fail to see that evolution implies becoming more advantageously sensitive to the environment, making more of its influences, shutting out profitless stimuli, and opening more gateways to knowledge. The bird's world is a larger and finer world than an earthworm's. The world means more to the bird than to the worm. The trial and error method. Simple creatures act with a certain degree of spontaneity on their environment, and they likewise react effectively to surrounding stimuli. Animals come to have definite answers back, sometimes several, sometimes only one, as in the case of the slipper animalcule, which reverses its cilia when it comes within the sphere of some disturbing influence, retreats, and turning upon itself tentatively, sets off again in the same general direction as before, but at an angle to the previous line. If it misses the disturbing influence, well and good. If it strikes it again, the tactics are repeated until a satisfactory way out is discovered or the stimulation proves fatal. It may be said that the slipper animalcule has but one answer to every question. But there are many protozoa which have several enregistered reactions. When there are alternative reactions which are tried one after another, the animal is pursuing what is called the trial and error method, and a higher note is struck. There is an endeavor after satisfaction, and a trial of answers. When the creature profits by experience to the extent of giving the right answer first, there is the beginning of learning. Reflex actions. Among simple multicellular animals such as sea anemones, we find the beginnings of reflex actions, and a considerable part of the behavior of lower animals is reflex. That is to say, there are laid down in the animal in the course of its development certain prearrangements of nerve cells and muscle cells which secure that a fit and proper answer is given to a frequently recurrent stimulus. An earthworm, half out of its burrow, becomes aware of the light tread of a thrush's foot, and jerks itself back into its hole before anyone can say reflex action. What is it that happens? Certain sensory nerve cells in the earthworm's skin are stimulated by vibrations in the earth. The message travels down a sensory nerve fiber from each of the stimulated cells and enters the nerve cord. The sensory fibers come into vital connection with branches of intermediary, associative, or communicating cells, which are likewise connected with motor nerve cells. To these the message is thus shunted. From the motor nerve cells, an impulse or command travels by motor nerve fibers, one from each cell, to the muscles, which contract. If this took as long to happen as it takes to describe, even in outline, it would not be of much use to the earthworm. But the motor answer follows the sensory stimulus almost instantaneously. The great advantage of establishing or enregistering these reflex chains is that the answers are practically ready-made or inborn, not requiring to be learned. It is not necessary that the brain should be stimulated if there is a brain, nor does the animal will to act, though in certain cases it may, by means of higher controlling nerve centers, keep the natural reflex response from being given, as happens, for instance, when we control a cough or a sneeze on some solemn occasion. The evolutionary method, if we may use the expression, has been to enregister ready-made responses, and as we ascend the animal kingdom we find reflex actions becoming complicated and often linked together, so that the occurrence of one pulls the trigger of another, and so on in a chain. The behavior of the insectivorous plant called Venus's flytrap, when it shuts on an insect, is like a reflex action in an animal, but plants have no definite nervous system. What are called tropisms? A somewhat higher level on the inclined plane is illustrated by what are called tropisms, obligatory movements which the animal makes, adjusting its whole body so that physiological equilibrium results in relation to gravity, pressure, currents, moisture, heat, light, electricity, and surfaces of contact. A moth is flying past a candle. The eye next the light is more illumined than the other. A physiological inequilibrium results, affecting nerve cells and muscle cells. The outcome is that the moth automatically adjusts its flight so that both eyes become equally illumined. In doing this, it often flies into the candle. It may seem bad business that the moth should fly into the candle, but the flame is an utterly artificial item in its environment, to which no one can expect it to be adapted. These tropisms play an important role in animal behavior. 2. Instinctive behavior. On a higher level is instinctive behavior, which reaches such remarkable perfection in ants, bees, and wasps. In its typical expression, instinctive behavior depends on inborn capacities. It does not require to be learned. It is independent of practice or experience, though it may be improved by both. It is shared equally by all members of the species of the same sex, for the female's instincts are often different from the male's. It refers to particular conditions of life that are of vital importance, though they may occur only once in a lifetime. The female yucca moth emerges from the cocoon when the yucca flower puts forth its bell-like blossoms. She flies to a flower, collects some pollen from the stamens, kneads it into a pill-like ball, and stows this away under her chin. She flies to an older yucca flower and lays her eggs in some of the ovules within the seed box. But before she does so, she has to deposit on the stigma the ball of pollen. From this the pollen tubes grow down, and the pollen nucleus of a tube fertilizes the egg cell in an ovule, so that the possible seeds become real seeds, for it is only a fraction of them that the yucca moth has destroyed by using them as cradles for her eggs. Now it is plain that the yucca moth has no individual experience of yucca flowers, yet she secures the continuance of her race by a concatenation of actions which form part of her instinctive repertory. From a physiological point of view, instinctive behavior is like a chain of compound reflex actions, but in some cases at least, there is reason to believe that the behavior is suffused with awareness and backed by endeavor. This is suggested in exceptional cases where the stereotyped routine is departed from to meet exceptional conditions. It should also be noted that just as ants, hive bees, and wasps exhibit in most cases pure instinctive behavior, but move on occasion on the main line of trial and error or of experimental initiative, so among birds and mammals, the intelligent behavior is sometimes replaced by instinctive routine. Perhaps there is no instinctive behavior without a spice of intelligence, and no intelligent behavior without an instinctive element. The old view that instinctive behavior was originally intelligent, and that instinct is lapsed intelligence, is a tempting one, and is suggested by the way in which habitual intelligent actions cease in the individual to require intelligent control, but it rests on the unproved hypothesis that the acquisitions of the individual can be entailed on the race. It is almost certain that instinct is on a line of evolution quite different from intelligence, and that it is nearer to the inborn inspirations of the calculating boy or the musical genius than to the plodding methods of intelligent learning. Animal intelligence. The higher reaches of the inclined plane of behavior show intelligence in the strict sense. They include those kinds of behavior which cannot be described without the suggestion that the animal makes some sort of perceptual inference, not only profiting by experience, but learning by ideas. Such intelligent actions show great individual variability. They are plastic and adjustable in a manner rarely hinted at in connection with instincts where routine cannot be departed from without the creature being nonplussed. They are not bound up with particular circumstances as instinctive actions are, but imply an appreciative awareness of relations. When there is an experimenting with general ideas, when there is conceptual, as contrasted with perceptual inference, we speak of reason, but there is no evidence of this below the level of man. It is not indeed always that we can credit man with rational conduct, but he has the possibility of it ever within his reach. Animal instinct and intelligence will be illustrated in another part of this work. We are here concerned simply with the general question of the evolution of behavior. There is a main line of tentative experimental behavior both below and above the level of intelligence, and it has been part of the tactics of evolution to bring about the hereditary enregistration of capacities of effective response, the advantages being that the answers come more rapidly and that the creature is left free, if it chooses, for higher adventures. There is no doubt as to the big fact that in the course of evolution, animals have shown an increasing complexity and masterfulness of behavior, that they have become at once more controlled and more definitely free agents, and that the inner aspect of the behavior, experimenting, learning, thinking, feeling, and willing, has come to count for more and more. 3. Evolution of parental care. Mammals furnish a crowning instance of a trend of evolution which expresses itself at many levels: the tendency to bring forth the young at a well-advanced stage, and to an increase of parental care associated with a decrease in the number of offspring. There is a British starfish called Ludia, which has 200 millions of eggs in a year, and there are said to be several millions of eggs in conger eels and some other fishes. These illustrate the spawning method of solving the problem of survival. Some animals are naturally prolific, and the number of eggs which they sow broadcast in the waters allows for enormous infantile mortality and obviates any necessity for parental care. But some other creatures, by nature less prolific, have found an entirely different solution of the problem. They practice parental care, and they secure survival with greatly economized reproduction. This is a trend of evolution particularly characteristic of the higher animals. So much so that Herbert Spencer formulated the generalization that the size and frequency of the animal family is inverse ratio to the degree of evolution to which the animal has attained. Now there are many different methods of parental care which secure the safety of the young, and one of these is called viviparity. The young ones are not liberated from the parent until they are relatively well advanced and more or less able to look after themselves. This gives the young a good send-off in life, and their chances of death are greatly reduced. In other words, the animals that have varied in the direction of economized reproduction may keep their foothold in the struggle for existence if they have varied at the same time in the direction of parental care. In other cases, it may have worked the other way round. In the interesting archaic animal called Peripatus, which has to face a modern world too severe for it, one of the methods of meeting the environing difficulties is the retention of the offspring for many months within the mother, so that it is born a fully formed creature. There are only a few offspring at a time, and although there are exceptional cases like the summer green flies, which are very prolific though viviparous, the general rule is that viviparity is associated with a very small family. The case of flowering plants stands by itself, for although they illustrate a kind of viviparity, the seed being embryos, an individual plant may have a large number of flowers and therefore a huge family. Viviparity naturally finds its best illustrations among terrestrial animals, where the risks to the young life are many, and it finds its climax among mammals. Now it is an interesting fact that the three lowest mammals, the duck mole and two spiny anteaters, lay eggs, that is, are oviparous, that the marsupials on the next grade bring forth their young, as it were, prematurely, and in most cases stow them away in an external pouch, while all the others, the placentals, show a more prolonged antenatal life and an intimate partnership between the mother and the unborn young. 4. There is another way of looking at the sublime process of evolution. It has implied a mastery of all the possible haunts of life. It has been a progressive conquest of the environment. 1. It is highly probable that living organisms found their foothold in the stimulating conditions of the shore of the sea, the shallow water, brightly illumined, seaweed-growing shelf fringing the continents. This littoral zone was a propitious environment where sea and fresh water, earth and air all meet, where there is stimulating change, abundant oxygenation, and a copious supply of nutritive material in what the streams bring down and in the rich seaweed vegetation. It is not an easy haunt of life, but none the worse for that, and it is tenanted today by representatives of practically every class of animals, from infusorians to seashore birds and mammals. The cradle of the open sea. 2. The open sea, or pelagic haunt, includes all the brightly illumined surface waters beyond the shallow water of the shore area. It is perhaps the easiest of all haunts of life, for there is no crowding, there is considerable uniformity, and an abundance of food for animals is afforded by the inexhaustible floating sea meadows of microscopic algae. These are reincarnated in minute animals like the open sea crustaceans, which again are utilized by fishes, these in turn making life possible for higher forms like carnivorous turtles and toothed whales. It is quite possible that the open sea was the original cradle of life, and perhaps Professor Church is right in picturing a long period of pelagic life before there was any sufficiently shallow water to allow the floating plants to anchor. It is rather in favor of this view that many shore animals such as crabs and starfishes spend their youthful stages in the relatively safe cradle of the open sea, and only return to the more strenuous conditions of their birthplace after they have gained considerable strength of body. It is probably safe to say that the honor of being the original cradle of life lies between the shore of the sea and the open sea. The Great Deeps. 3. A third haunt of life is the floor of the deep sea, the abyssal area, which occupies more than a half of the surface of the globe. It is a region of extreme cold, an eternal winter, of utter darkness, an eternal night, relieved only by the fitful gleams of phosphorescent animals, of enormous pressure, 2.5 tons on the square inch at a depth of 2,500 fathoms, of profound calm, unbroken silence, immense monotony. And as there are no plants in the great abysses, the animals must live on one another, and in the long run, on the rain of moribund animalcules which sink from the surface through the miles of water. It seems a very unpromising haunt of life, but it is abundantly tenanted, and it gives us a glimpse of the insurgent nature of the living creature that the difficulties of the deep sea should have been so effectively conquered. It is probable that the colonizing of the great abysses took place in relatively recent times, for the fauna does not include many very antique types. It is practically certain that the colonization was due to littoral animals which followed the food debris, millennium after millennium, further and further down the long slope from the shore. The fresh waters. 4. A fourth haunt of life is that of the fresh waters, including river and lake, pond and pool, swamp and marsh. It may have been colonized by gradual migration up estuaries and rivers, or by more direct passage from the seashore into the brackish swamp. Or it may have been in some cases that partially landlocked corners of ancient seas became gradually turned into freshwater basins. The animal population of the fresh waters is very representative, and is diversely adapted to meet the characteristic contingencies, the risk of being dried up, the risk of being frozen hard in winter, and the risk of being left high and dry after floods or of being swept down to the sea. Conquest of the dry land. 5. The terrestrial haunt has been invaded age after age by contingents from the sea or from the fresh waters. We must recognize the worm invasion, which led eventually to the making of the fertile soil, the invasion due to air-breathing arthropods, which led eventually to the important linkage between flowers and their insect visitors, and the invasion due to air-breathing amphibians, which led eventually to the higher terrestrial animals and to the development of intelligence and family affection. Besides these three great invasions, there were minor ones, such as that leading to land snails, for there has been a widespread and persistent tendency among aquatic animals to try to possess the dry land. Getting onto dry land had a manifold significance. It implied getting into a medium with a much larger supply of oxygen than there is dissolved in the water. But the oxygen of the air is more difficult to capture, especially when the skin becomes hard or well protected, as it is almost bound to become in animals living on dry ground. Thus this leads to the development of internal surfaces, such as those of lungs, where the oxygen taken into the body may be absorbed by the blood. In most animals, the blood goes to the surface of oxygen capture, but in insects and their relatives there is a different idea, of taking the air to the blood, or in greater part to the area of oxygen consumption, the living tissues. A system of branching air tubes takes air into every hole and corner of the insect's body, and this thorough aeration is doubtless in part the secret of the insect's intense activity. The blood never becomes impure. The conquest of the dry land also implied a predominance of that kind of locomotion which may be compared to punting, when the body is pushed along by pressing a lever against a hard substratum, and it also followed that, with few exceptions, the body of the terrestrial animal tended to be compact, readily lifted off the ground by the limbs or adjusted in some other way so that there may not be too large a surface trailing on the ground. An animal like a jellyfish, easily supported in the water, would be impossible on land. Such apparent exceptions as earthworms, centipedes, and snakes are not difficult to explain, for the earthworm is a burrower which eats its way through the soil. The centipede's long body is supported by numerous hard legs, and the snake pushes itself along by means of the large ventral scales to which the lower ends of very numerous ribs are attached. Methods of mastering the difficulties of terrestrial life. A great restriction attendant on the invasion of the dry land is that locomotion becomes limited to one plane, namely, the surface of the earth. This is in great contrast to what is true in the water, where the animal can move up or down, to right or to left, at any angle and in 3 dimensions. It surely follows from this that the movements of land animals must be rapid and precise, unless, indeed, safety is secured in some other way. Hence it is easy to understand why most land animals have very finely developed striped muscles, and why a beetle running on the ground has far more numerous muscles than a lobster swimming in the sea. Land animals were also handicapped by the risks of drought and of frost, but these were met by defenses of the most diverse description, from the hairs of woolly caterpillars to the fur of mammals, from the carapace of tortoises to the armor of armadillos. In other cases, it is hardly necessary to say, the difficulties may be met in other ways, as frogs meet the winter by falling into a lethargic state in some secluded retreat. Another consequence of getting onto dry land is that the eggs or young can no longer be set free anyhow, as is possible when the animal is surrounded by water, which is in itself more or less of a cradle. If the eggs were laid or the young liberated on dry ground, the chances are many that they would be dried up or devoured. So there are numerous ways in which land animals secure the safety of their young. For example, by burying them in the ground, or by hiding them in nests, or by carrying them about for a prolonged period either before or after birth. This may mean great safety for the young, this may make it possible to have only a small family, and this may tend to the evolution of parental care and the kindly emotions. Thus it may be understood that from the conquest of the land many far-reaching consequences have followed. Finally, it is worth dwelling on the risks of terrestrial life, because they enable us better to understand why so many land animals have become burrowers and others climbers of trees, why some have returned to the water and others have taken to the air. It may be asked, perhaps, why the land should have been colonized at all when the risks and difficulties are so great. The answer must be that necessity and curiosity are the mother and father of invention. Animals left the water because the pools dried up, or because they were overcrowded, or because of inveterate enemies, but also because of that curiosity and spirit of adventure which, from first to last, has been one of the spurs of progress. Conquering the air. 6. The last great haunt of life is the air, a mastery of which must be placed to the credit of insects, pterodactyls, birds, and bats. These have been the successes, but it should be noted that there have been many brilliant failures, which have not attained to much more than parachuting. These include the flying fishes, which take leaps from the water and are carried for many yards and to considerable heights, holding their enlarged pectoral fins taut or with little more than a slight fluttering. There is a so-called flying frog, Rhacophorus, that skims from branch to branch, and the more effective flying dragon, Dracovolans of the Far East, which has been mentioned already. Among mammals there are flying phalangers, flying lemurs, and more besides, all attaining to great skill as parachutists, and illustrating the endeavor to master the air which man has realized in a way of his own. The power of flight brings obvious advantages. A bird feeding on the ground is able to evade the stalking carnivore by suddenly rising into the air. Food and water can be followed rapidly and to great distances. The eggs or the young can be placed in safe situations, and birds in their migrations have made a brilliant conquest both of time and space. Many of them know no winter in their year, and the migratory flight of the Pacific golden plover from Hawaii to Alaska and back again does not stand alone. The procession of life through the ages. 1. The rock record. How do we know when the various classes of animals and plants were established on the earth? How do we know the order of their appearance and the succession of their advances? The answer is by reading the rock record. In the course of time, the crust of the earth has been elevated into continents and depressed into ocean troughs, and the surface of the land has been buckled up into mountain ranges and folded in gentler hills and valleys. The high places of the land have been weathered by air and water in many forms, and the results of the weathering have been borne away by rivers and seas, to be laid down again elsewhere as deposits which eventually formed sandstones, mudstones, and similar sedimentary rocks. Much of the material of the original crust has thus been broken down and worked up again many times over, and if the total thickness of the sedimentary rocks is added up, it amounts, according to some geologists, to a total of 67 miles. In most cases, however, only a small part of this thickness is to be seen in one place, for the deposits were usually formed in limited areas at any one time. The use of fossils. When the sediments were accumulating age after age, it naturally came about that remains of the plants and animals living at the time were buried, and these formed the fossils by the aid of which it is possible to read the story of the past. By careful piecing together of evidence, the geologist is able to determine the order in which the different sedimentary rocks were laid down, and thus to say, for instance, that the Devonian period was the time of the origin of amphibians. In other cases, the geologist utilizes the fossils in his attempt to work out the order of the strata when these have been much disarranged. For the simpler fossil forms of any type must be older than those that are more complex. There is no vicious circle here, for the general succession of strata is clear, and it is quite certain that there were fishes before there were amphibians, and amphibians before there were reptiles, and reptiles before there were birds and mammals. In certain cases, for example of fossil horses and elephants, the actual historical succession has been clearly worked out. If the successive strata contain good samples of all the plants and animals living at the time when the beds were formed, then it would be easy to read the record of the rocks. But many animals were too soft to become satisfactory fossils. Many were eaten or dissolved away. Many were destroyed by heat and pressure, so that the rock record is like a library very much damaged by fire and looting and decay. 2. The geological timetable. The long history of the earth and its inhabitants is conveniently divided into eras. Thus, just as we speak of the ancient, medieval, and modern history of mankind, so we may speak of Paleozoic, Mesozoic, and Cenozoic eras in the history of the earth as a whole. Geologists cannot tell us except in an approximate way how long the process of evolution has taken. One of the methods is to estimate how long has been required for the accumulation of the salts of the sea, for all these have been dissolved out of the rocks since rain began to fall on the earth. Dividing the total amount of saline matter by what is contributed every year in modern times, we get about 100 million years as the age of the sea. But as the present rate of salt accumulation is probably much greater than it was during many of the geological periods, the prodigious age just mentioned is in all likelihood far below the mark. Another method is to calculate how long it would take to form the sedimentary rocks, like sandstones and mudstones, which have a total thickness of over 50 miles, though the local thickness is rarely over a mile. As most of the materials have come from the weathering of the Earth's crust, and as the annual amount of weathering now going on can be estimated, the time required for the formation of the sedimentary rocks of the world can be approximately calculated. There are some other ways of trying to tell the Earth's age and the length of the successive periods, but no certainty has been reached. The eras before the Cambrian correspond to about 32 miles of thickness of strata, and all the subsequent eras with fossil-bearing rocks to a thickness of about 21 miles, in itself an astounding fact. Perhaps 30 million years must be allotted to the Precambrian eras, 18 to the Paleozoic, 9 to the Mesozoic, 3 to the Cenozoic, making a grand total of 60 millions. The establishment of invertebrate stocks. It is an astounding fact that at least half of geological time, the Archeozoic and Proterozoic eras, passed before there were living creatures with parts sufficiently hard to form fossils. In the latter part of the Proterozoic era, there are traces of one-celled marine animals, radiolarians, with shells of flint, and of worms that wallowed in the primal mud. It is plain that as regards the most primitive creatures, the rock record tells us little. The rarity of direct traces of life in the oldest rocks is partly due to the fact that the primitive animals would be of delicate build, but it must also be remembered that the ancient rocks have been profoundly and repeatedly changed by pressure and heat, so that the traces which did exist would be very liable to obliteration, and if it be asked what right we have to suppose the presence of living creatures in the absence or extreme rarity of fossils, we must point to great accumulations of limestone which indicate the existence of calcareous algae, and to deposits of iron which probably indicate the activity of iron-forming bacteria. Ancient beds of graphite similarly suggest that green plants flourished in these ancient days. 3. The era of ancient life, Paleozoic. The Cambrian period was the time of the establishment of the chief stocks of backboneless animals, such as sponges, jellyfishes, worms, sea cucumbers, lamp shells, trilobites, crustaceans, and mollusks. There is something very eloquent in the broad fact that the peopling of the seas had definitely begun some 30 million years ago, for Professor H. F. Osborn points out that in the Cambrian period there was already a colonization of the shore of the sea, the open sea, and the deep waters. The Ordovician period was marked by abundant representation of the once very successful class of trilobites, jointed-footed, antenna-bearing, segmented marine animals, with numerous appendages and a covering of chitin. They died away entirely with the end of the Paleozoic era. Also very notable was the abundance of predatory cuttlefishes, the bullies of the ancient seas. But it was in this period that the first backboned animals made their appearance, an epoch-making step in evolution. In other words, true fishes were evolved, destined in the course of ages to replace the cuttlefishes, which are mere mollusks, in dominating the seas. In the Silurian period, in which the peopling of the seas went on apace, there was the first known attempt at colonizing the dry land. For in the Silurian rocks there are fossil scorpions, and that implies ability to breathe dry air, by means of internal surfaces, in this case known as lung books. It was also towards the end of the Silurian, when a period of great aridity set in, that fishes appeared related to our mudfishes or double breathers, dipnoi, which have lungs as well as gills. This again meant utilizing dry air, just as the present-day mudfishes do when the water disappears from the pools in hot weather. The lungfishes or mudfishes of today are but 3 in number, one in Queensland, one in South America, and one in Africa, but they are extremely interesting living fossils, binding the class of fishes to that of amphibians. It is highly probable that the first invasion of the dry land should be put to the credit of some adventurous worms, but the second great invasion was certainly due to air-breathing arthropods, like the pioneer scorpion we mentioned. The Devonian period, including that of the Old Red Sandstone, was one of the most significant periods in the Earth's history, for it was the time of the establishment of flowering plants upon the Earth, and of terrestrial backboned animals. One would like to have been the discoverer of the Devonian footprint of Thinopus, the first known amphibian footprint, an eloquent vestige of the third great invasion of the dry land. It was probably from a stock of Devonian lungfishes that the first amphibians sprang, but it was not till the next period that they came to their own. While they were still feeling their way, there was a remarkable exuberance of shark-like and heavily armored fishes in the Devonian seas. End of section 4. Section 5 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 5. Part 2. The Story of Evolution, continued. Evolution of Land Animals. 1. Giant amphibians and coal measures. The Carboniferous period was marked by a mild, moist climate and a luxuriant vegetation in the swampy lowgrounds. It was a much less strenuous time than the Devonian period. It was like a very long summer. There were no trees of the type we see now, but there were forests of club mosses and horsetails that grew to gigantic size compared with their pygmy representatives of today. In these forests the jointed-footed invaders of the dry land ran riot in the form of centipedes, spiders, scorpions, and insects, and on these the primeval amphibians fed. The appearance of insects made possible a new linkage of far-reaching importance, namely, the cross-fertilization of flowering plants by their insect visitors, and from this time onwards it may be said that flowers and their visitors have evolved hand in hand. Cross-fertilization is much surer by insects than by the wind, and cross-fertilization is more advantageous than self-fertilization because it promotes both fertility and plasticity. It was probably in this period that colored flowers, attractive to insect visitors, began to justify themselves as beauty became useful, and began to relieve the monotonous green of the horsetail and club moss forests, which covered great tracts of the earth for millions of years. In the Carboniferous forests there were also land snails, representing one of the minor invasions of the dry land, tending on the whole to check vegetation. They too were probably preyed upon by the amphibians, some of which attained a large size. Each age has had its giants, and those of the Carboniferous were amphibians called labyrinthodonts, some of which were almost as big as donkeys. It need hardly be said that it was in this period that most of the coal measures were laid down by the immense accumulation of the spores and debris of the club moss forests. Ages afterwards, it was given to man to tap this great source of energy, traceable back to the sunshine of millions of years ago. Even then it was true that no plant or animal lives or dies to itself. The acquisitions of amphibians. As amphibians had their golden age in the Carboniferous period, we may fitfully use this opportunity of indicating the advances in evolution which the emergence of amphibians implied. 1. In the first place, the passage from water to dry land was the beginning of a higher and more promiseful life, taxed no doubt by increased difficulties. The natural question rises why animals should have migrated from water to dry land at all, when great difficulties were involved in the transition. The answers must be a. That local drying up of water basins or elevations of the land surface often made the old haunts untenable. b. That there may have been great congestion and competition in the old quarters, and c. That there has been an undeniable endeavor after well-being throughout the history of animal life. In the same way with mankind, migrations were prompted by the setting in of prolonged drought, by overpopulation, and by the spirit of adventure. 2. In amphibians, for the first time, the non-digitate paired fins of fishes were replaced by limbs with fingers and toes. This implied an advantageous power of grasping, of holding firm, of putting food into the mouth, of feeling things in 3 dimensions. 3. We cannot be positive in regard to the soft parts of the ancient amphibians, known only as fossils, but if they were in a general way like the frogs and toads, newts and salamanders of the present day, we may say that they made among other acquisitions the following: true ventral lungs, a 3-chambered heart, a movable tongue, a drum to the ear, and lids to the eyes. It is very interesting to find that though the tongue of the tadpole has some muscle fibers in it, they are not strong enough to affect movement, recalling the tongue of fishes, which has not any muscles at all. Gradually, as the tadpole becomes a frog, the muscle fibers grow in strength and make it possible for the full-grown creature to shoot out its tongue upon insects. This is probably a recapitulation of what was accomplished in the course of millennia in the history of the amphibian race. 4. Another acquisition made by amphibians was a voice, due, as in ourselves, to the rapid passage of air over taut membranes, vocal cords, stretched in the larynx. It is an interesting fact that for millions of years there was upon the earth no sound of life at all, only the noise of wind and wave, thunder and avalanche. Apart from the instrumental music of some insects, perhaps beginning in the Carboniferous, the first vital sounds were due to amphibians, and there certainly was the first voice, surely one of the great steps in organic evolution. Evolution of the voice. The first use of the voice was probably that indicated by our frogs and toads. It serves as a sex call. That is the meaning of the trumpeting with which frogs herald the spring, and it is often only in the males that the voice is well developed. But if we looked forward, past amphibians altogether, we find the voice becoming a maternal call, helping to secure the safety of the young, a use very obvious when young birds squat motionless at the sound of the parent's danger note. Later on, probably, the voice became an infantile call, as when the unhatched crocodile pipes from within the deeply buried egg, signaling to the mother that it is time to be unearthed. Higher still, the voice expresses emotion, as in the song of birds, often outside the limits of the breeding time. Later still, particular sounds become words, signifying particular things or feelings, such as food, danger, home, anger, and joy. Finally, words become a medium of social intercourse and, as symbols, help to make it possible for man to reason. 2. The early reptiles. In the Permian period, reptiles appeared, or perhaps one should say, began to assert themselves. That is to say, there was an emergence of backboned animals which were free from water and relinquished the method of breathing by gills, which amphibians retained in their young stages at least. The unhatched or unborn reptile breathes by means of a vascular hood spread underneath the eggshell and absorbing dry air from without. It is an interesting point that this vascular hood, called the allantois, is represented in amphibians by an unimportant bladder growing out from the hind end of the food canal. A great step in evolution was implied in the origin of this antenatal hood or fetal membrane, and another one, of protective significance, called the amnion, which forms a water bag over the delicate embryo. The step meant total emancipation from the water and from gill breathing, and the two fetal membranes, the amnion and the allantois, persist not only in all reptiles but in birds and mammals as well. These higher vertebrates are therefore called amniota, in contrast to the lower vertebrates or anamnia, the amphibians, fishes, and primitive types. It is a suggestive fact that the embryos of all reptiles, birds, and mammals show gill clefts, a telltale evidence of their distant aquatic ancestry. But these embryonic gill clefts are not used for respiration and show no trace of gills except in a few embryonic reptiles and birds, where their dwindled vestiges have been recently discovered. As to the gill clefts, they are of no use in higher vertebrates except that the first becomes the eustachian tube leading from the ear passage to the back of the mouth. The reason why they persist, when only one is of any use, and that in a transformed guise, would be difficult to interpret except in terms of the evolution theory. They illustrate the lingering influence of a long pedigree, the living hand of the past, the tendency that individual development has to recapitulate racial evolution. In a condensed and telescoped manner, of course, for what took the race a million years may be recapitulated by the individual in a week. In the Permian period, the warm, moist climate of most of the Carboniferous period was replaced by severe conditions, culminating in an ice age which spread from the southern hemisphere throughout the world. With this was associated a waning of the Carboniferous flora and the appearance of a new one, consisting of ferns, conifers, ginkgos, and cycads, which persisted until near the end of the Mesozoic era. The Permian Ice Age lasted for millions of years and was most severe in the far south. Of course, it was a very different world then, for North Europe was joined to North America, Africa to South America, and Australia to Asia. It was probably during the Permian Ice Age that many of the insects divided their life history into two main chapters: the feeding, growing, molting, immature, larval stages, that is, caterpillars, and the more ascetic, non-growing, non-molting, winged phase, adapted for reproduction. Between these there intervened the quiescent, well-protected pupa stage or chrysalis, probably adapted to begin with as a means of surviving the severe winter. For it is easier for an animal to survive when the vital processes are more or less in abeyance. Disappearance of many ancient types. We cannot leave the last period of the Paleozoic era and its prolonged ice age without noticing that it meant the entire cessation of a large number of ancient types, especially among plants and backboneless animals, which now disappear forever. It is necessary to understand that the animals of ancient days stand in three different relations to those of today. A. There are ancient types that have living representatives, sometimes few and sometimes many, sometimes much changed and sometimes but slightly changed. The lamp shell, Lingulella, of the Cambrian or Ordovician period, has a very near relative in the Lingula of today. There are a few extremely conservative animals. B. There are ancient types which have no living representatives, except in the guise of transformed descendants, as the king crab, Limulus, may be said to be a transformed descendant of the otherwise quite extinct race to which Eurypterids or sea scorpions belonged. C. There are altogether extinct types, lost races, which have left not a whack behind, for there is not any representation today of such races as graptolites and trilobites. Looking backwards over the many millions of years comprised in the Paleozoic era, what may we emphasize as the most salient features? There was in the Cambrian the establishment of the chief classes of backboneless animals, in the Ordovician the first fishes, and perhaps the first terrestrial plants, in the Silurian the emergence of air-breathing invertebrates and mudfishes, in the Devonian the appearance of the first amphibians, from which all higher land animals are descended, and the establishment of a land flora. In the Carboniferous, the great club moss forests and an exuberance of air-breathing insects and their allies. In the Permian, the first reptiles and a new flora. The geological Middle Ages. 1. The Mesozoic era. In a broad way, the Mesozoic era corresponds with the golden age of reptiles, and with the climax of the conifer and cycad flora, which was established in the Permian. But among the conifers and cycads our modern flowering plants were beginning to show face tentatively, just like birds and mammals among the great reptiles. In the Triassic period, the exuberance of reptilian life which marked the Permian was continued. Besides turtles, which still persist, there were ichthyosaurs, plesiosaurs, dinosaurs, and pterosaurs, none of which lasted beyond the Mesozoic era. Of great importance was the rise of the dinosaurs in the Triassic, for it is highly probable that within the limits of this vigorous and plastic stock, some of them bipeds, we must look for the ancestors of both birds and mammals. Both land and water were dominated by reptiles, some of which attained to gigantic size. Had there been any zoologist in those days, he would have been very sagacious indeed if he had suspected that reptiles did not represent the climax of creation. The flying dragons. The Jurassic period showed a continuance of the reptilian splendor. They radiated in many directions, becoming adapted to many haunts. Thus there were many fish lizards paddling in the seas, many types of terrestrial dragons stalking about on land, many swiftly gliding alligator-like forms, and the flying dragons which began in the Triassic attained to remarkable success and variety. Their wing was formed by the extension of a great fold of skin on the enormously elongated outermost finger, and they varied from the size of a sparrow to a spread of over 5 feet. A soldering of the dorsal vertebrae, as in our flying birds, was an adaptation to striking the air with some force, but as there is not more than a slight keel, if any, on the breastbone, it is unlikely that they could fly far. For we know from our modern birds that the power of flight may be to some extent gauged from the degree of development of the keel, which is simply a great ridge for the better insertion of the muscles of flight. It is absent, of course, in the running birds, like the ostrich, and it has degenerated in an interesting way in the burrowing parrot, stringops, and a few other birds that have gone back. The first known bird. But the Jurassic is particularly memorable because its strata have yielded two fine specimens of the first known bird, Archaeopteryx. These were entombed in the deposits which form the fine-grained lithographic stones of Bavaria, and practically every bone in the body is preserved except the breastbone. Even the feathers have left their marks with distinctness. This oldest known bird, too far advanced to be the first bird, was about the size of a crow and was probably of arboreal habits. Of great interest are its reptilian features, so pronounced that one cannot evade the evolutionist suggestion. It had teeth in both jaws, which no modern bird has. It had a long lizard-like tail, which no modern bird has. It had claws on 3 fingers and a sort of half-made wing. That is to say, it does not show what all modern birds show, a fusion of half the wrist bones with the whole of the palm bones, the well-known carpo-metacarpus bone, which forms a basis for the longest pinions. In many reptiles, such as crocodiles, there are peculiar bones running across the abdomen beneath the skin, the so-called abdominal ribs, and it seems an eloquent detail to find these represented in Archaeopteryx, the earliest known bird. No modern bird shows any trace of them. There is no warrant for supposing that the flying reptiles or pterodactyls gave rise to birds, for the two groups are on different lines, and the structure of the wings is entirely different. Thus, the long-fingered pterodactyl wing was a parachute wing, while the secret of the bird's wing has its center in the feathers. It is highly probable that birds evolved from certain dinosaurs which had become bipeds, and it is possible that they were for a time swift runners that took flying jumps along the ground. Thereafter, perhaps, came a period of arboreal apprenticeship, during which there was much gliding from tree to tree before true flight was achieved. It is an interesting fact that the problem of flight has been solved 4 times among animals, by insects, by pterodactyls, by birds, and by bats, and that the 4 solutions are on entirely different lines. In the Cretaceous period, the outstanding events included the waning of giant reptiles, the modernizing of the flowering plants, and the multiplication of small mammals. Some of the Permian reptiles, such as the dog-toothed cynodonts, were extraordinarily mammal-like, and it was probably from among them that definite mammals emerged in the Triassic. Comparatively little is known of the early Triassic mammals, except that their back teeth were marked by numerous tubercles on the crown, but they were gaining strength in the late Triassic when small arboreal insectivores, not very distant from the modern tree shrews, Tupaia, began to branch out in many directions indicative of the great divisions of modern mammals, such as the clawed mammals, hoofed mammals, and the race of monkeys or primates. In the Upper Cretaceous, there was an exuberant radiation of mammals, adaptive to the conquest of all sorts of haunts, and this was vigorously continued in Tertiary times. There is no difficulty in the fact that the earliest remains of definite mammals in the Triassic precede the first known bird in the Jurassic. For although we usually rank mammals as higher than birds, being mammals ourselves, how could we do otherwise? There are many ways in which birds are preeminent. For example, in skeletal, musculature, integumentary structures, and respiratory system. The fact is that birds and mammals are in 2 quite different tacks of evolution, not related to one another, save in having a common ancestry in extinct reptiles. Moreover, there is no reason to believe that the Jurassic Archaeopteryx was the first bird in any sense except that it was the first of which we have any record. In any case, it is safe to say that birds came to their own before mammals did. Looking backwards, we may perhaps sum up what is most essential in the Mesozoic era in Professor Schuchert's sentence. The Mesozoic is the age of reptiles, and yet the little mammals and the toothed birds are storing up intelligence and strength to replace the reptiles when the cycads and conifers shall give way to the higher flowering plants. 2. The Cenozoic or Tertiary era. In the Eocene period, there was a replacement of the small-brained archaic mammals by big-brained modernized types, and with this must be associated the covering of the earth with a garment of grass and dry pasture. Marshes were replaced by meadows, and browsing by grazing animals. In the spreading meadows, an opportunity was also offered for a richer evolution of insects and birds. During the Oligocene, the elevation of the land continued, the climate became less moist, and the grazing herds extended their range. The Miocene was the mammalian golden age, and there were crowning examples of what Osborn calls adaptive radiation. That is to say, mammals, like the reptiles before them, conquer every haunt of life. There are flying bats, vol-plating parachutists, climbers in trees like sloths and squirrels, quickly moving hoofed animals, burrowers like the moles, freshwater mammals like duck, mole, and beaver, shore-frequenting seals and manatees, and open-sea cetaceans, some of which dive far more than full fathoms 5. It is important to realize the perennial tendency of animals to conquer every corner and to fill every niche of opportunity, and to notice that this has been done by successive sets of animals in succeeding ages. Most notably, the mammals repeat all the experiments of reptiles on a higher turn of the spiral. Thus arises what is called convergence, the superficial resemblance of unrelated types, like whales and fishes, the resemblance being due to the fact that the different types are similarly adapted to similar conditions of life. Professor H. F. Osborn points out that mammals may seek any one of the 12 different habitat zones, and that in each of these there may be 6 quite different kinds of food. Living creatures penetrate everywhere like the flowing waters of a great river in flood. 3. The Pliocene period was a more strenuous time, with less genial climatic conditions, and with more intense competition. Old land bridges were broken and new ones made, and the geographical distribution underwent great changes. Professor R. S. Lull describes the Pliocene as a period of great unrest. Many migrations occurred the world over, new competitions arose, and the weaker stocks began to show the effects of the strenuous life. One momentous event seems to have occurred in the Pliocene, and that was the transformation of the precursor of humanity into man, the culmination of the highest line of evolution. The Pleistocene period was a time of sifting. There was a continued elevation of the continental masses, and ice ages set in, relieved by less severe interglacial times when the ice sheets retreated northwards for a time. Many types like the mammoth, the woolly rhinoceros, the saber-toothed tiger, the cave lion, and the cave bear became extinct. Others which formerly had a wide range became restricted to the far north, or were left isolated here and there on the high mountains, like the snow mouse, which now occurs on isolated alpine heights above the snow line. Perhaps it was during this period that many birds of the northern hemisphere learned to evade the winter by the sublime device of migration. Looking backwards, we may quote Professor Schuchert again. The lands in the Cenozoic began to bloom with more and more flowering plants and grand hardwood forests. The atmosphere is scented with sweet odors, a vast crowd of new kinds of insects appear, and the places of the once dominant reptiles of the lands and seas are taken by the mammals. Out of these struggles there rises a greater intelligence, seen in nearly all of the mammal stocks, but particularly in one, the monkey-ape man. Brute man appears on the scene with the introduction of the last glacial climate, a most trying time for all things endowed with life. And finally, there results the dominance of reasoning man over all his brute associates. In man and human society, the story of evolution has its climax. The ascent of man. Man stands apart from animals in his power of building up general ideas and of using these in the guidance of his behavior and the control of his conduct. This is essentially wrapped up with his development of language as an instrument of thought. Some animals have words, but man has language, logos. Some animals show evidence of perceptual inference, but man often gets beyond this to conceptual inference, reason. Many animals are affectionate and brave, self-forgetful and industrious, but man thinks the ought, definitely guiding his conduct in the light of ideals, which in turn are wrapped up with the fact that he is a social person. Besides his big brain, which may be 3 times as heavy as that of a gorilla, man has various physical peculiarities. He walks erect. He plants the sole of his foot flat on the ground. He has a chin and a good heel, a big forehead and a non-protrusive face, a relatively uniform set of teeth without conspicuous canines, and a relatively naked body. But in spite of man's undeniable apartness, there is no doubt as to his solidarity with the rest of creation. There is an all-pervading similitude of structure between man and the anthropoid apes, though it is certain that it is not from any living form that he took his origin. None of the anatomical distinctions, except the heavy brain, could be called momentous. Man's body is a veritable museum of relics, vestigial structures, inherited from pre-human ancestors. In his everyday bodily life and in some of its disturbances, man's pedigree is often revealed. Even his facial expression, as Darwin showed, is not always human. Some fossil remains bring modern man nearer to the anthropoid type. It is difficult not to admit the ring of truth in the closing words of Darwin's Descent of Man. We must, however, acknowledge, as it seems to me, that man with all his noble qualities, with sympathy which feels for the most debased, with benevolence which extends not only to other men, but to the humblest living creature, with his god-like intellect which has penetrated into the movements and constitution of the solar system, with all these exalted powers, man still bears in his bodily frame the indelible stamp of his lowly origin. The evolving system of nature. There is another side of evolution so obvious that it is often overlooked, the tendency to link lives together in vital interrelations. Thus flowers and their insect visitors are often virtually interlinked in mutual dependence. Many birds feed on berries and distribute the seeds. The tiny freshwater snail is the host of the juvenile stages of the liver fluke of the sheep. The mosquito is the vehicle of malaria from man to man, and the tsetse fly spreads sleeping sickness. The freshwater mussel cannot continue its race without the unconscious cooperation of the minnow, and the freshwater fish called the bitterling cannot continue its race without the unconscious cooperation of the mussel. There are numerous mutually beneficial partnerships between different kinds of creatures, and other interrelations where the benefit is one-sided, as in the case of insects that make galls on plants. There are also among kindred animals many forms of colonies, communities, and societies. Nutritive chains bind long series of animals together, the cod feeding on the whelk on the worm on the organic dust of the sea. There is a system of successive incarnations, and matter is continually passing from one embodiment to another. These instances must suffice to illustrate the central biological idea of the web of life, the interlinked system of animate nature. Linnaeus spoke of the systema naturae, meaning the orderly hierarchy of classes, orders, families, genera, and species. But we owe to Darwin in particular some knowledge of a more dynamic systema naturae, the network of vital interrelations. This has become more and more complex as evolution has continued, and man's web is most complex of all. It means making animate nature more of a unity. It means an external method of registering steps of progress. It means an evolving set of sieves by which new variations are sifted, and living creatures are kept from slipping down the steep ladder of evolution. Parasitism. It sometimes happens that the interrelation established between one living creature and another works in a retrograde direction. This is the case with many thoroughgoing internal parasites which have sunk into an easygoing kind of life, utterly dependent on their host for food, requiring no exertions, running no risks, and receiving no spur to effort. Thus we see that evolution is not necessarily progressive. Everything depends on the conditions in reference to which the living creatures have been evolved. When the conditions are too easygoing, the animal may be thoroughly well adapted to them, as a tapeworm certainly is, but it slips down the rungs of the ladder of evolution. This is an interesting minor chapter in the story of evolution, the establishment of different kinds of parasites, casual and constant, temporary and lifelong, external hangers-on and internal unpaying boarders, those that live in the food canal and depend on the host's food, and those that inhabit the blood or the tissues and find their food there. It seems clear that ichneumon grubs and the like which hatch inside a caterpillar and eat it alive are not so much parasites as beasts of prey working from within. But there are two sides to this minor chapter. There is the evolution of the parasite, and there is also the evolution of counteractive measures on the part of the host. Thus there is the maintenance of a bodyguard of wandering amoeboid cells which tackle the microbes invading the body and often succeed in overpowering and digesting them. Thus, again, there is the protective capacity the blood has of making antagonistic substances or antibodies which counteract poisons, including the poisons which the intruding parasites often make. The evidences of evolution. How it came about. 1. Progress in evolution. There has often been slipping back and degeneracy in the course of evolution, but the big fact is that there has been progress. For millions of years, life has been slowly creeping upwards, and if we compare the highest animals, birds and mammals, with their predecessors, we must admit that they are more controlled, more masters of their fate with more mentality. Evolution is, on the whole, integrative. That is to say, it makes against instability and disorder and towards harmony and progress. Even in the rise of birds and mammals, we can discern that the evolutionary process was making towards a fuller embodiment or expression of what man values most: control, freedom, understanding, and love. The advance of animal life through the ages has been checkered, but on the whole it has been an advance towards increasing fullness, freedom, and fitness of life. In the study of this advance, the central fact of organic evolution, there is assuredly much for man's instruction and much for his encouragement. Evidences of evolution. In all this, it may be said, the fact of evolution has been taken for granted, but what are the evidences? Perhaps it should be frankly answered that the idea of evolution, that the present is the child of the past and the parent of the future, cannot be proved, as one may prove the law of gravitation. All that can be done is to show that it is a key, a way of looking at things, that fits the facts. There is no lock that it does not open. But if the facts that the evolution theory vividly interprets be called the evidences of its validity, there is no lack of them. There is historical evidence. And what is more eloquent than the general fact that fishes emerged before amphibians, and these before reptiles, and these before birds, and so on? There are wonderfully complete fossil series, for example among cuttlefishes, in which we can almost see evolution in process. The pedigree of horse and elephant and crocodile is in general very convincing, though it is to be confessed that there are other cases in regard to which we have no light. Who can tell, for instance, how vertebrates arose or from what origin? There is embryological evidence, for the individual development often reads like an abbreviated recapitulation of the presumed evolution of the race. The mammal's visceral clefts are telltale evidence of remote aquatic ancestors, breathing by gills. Something is known in regard to the historical evolution of antlers in bygone ages. The red deer of today recapitulates at least the general outlines of the history. The individual development of an asymmetrical flatfish, like a plaice or sole, which rests and swims on one side, tells us plainly that its ancestors were symmetrical fishes. There is what might be called physiological evidence, for many plants and animals are variable before our eyes, and evolution is going on around us today. This is familiarly seen among domesticated animals and cultivated plants, but there is abundant flux in wild nature. It need hardly be said that some organisms are very conservative, and that change need not be expected when a position of stable equilibrium has been secured. There is also anatomical evidence of a most convincing quality. In the forelimbs of backboned animals, say, the paddle of a turtle, the wing of a bird, the flipper of a whale, the foreleg of a horse, and the arm of a man, the same essential bones and muscles are used to such diverse results. What could it mean save blood relationship? And as to the two sets of teeth in whalebone whales, which never even cut the gum, is there any alternative but to regard them as relics of useful teeth which ancestral forms possessed? In short, the evolution theory is justified by the way in which it works. 2. Factors in evolution. If it be said, so much for the fact of evolution, but what of the factors? The answer is not easy. For not only is the problem the greatest of all scientific problems, but the inquiry is still very young. The scientific study of evolution practically dates from the publication of The Origin of Species in 1859. Heritable novelties or variations often crop up in living creatures, and these form the raw material of evolution. These variations are the outcome of expression of changes in the germ cells that develop into organisms. But why should there be changes in the constitution of the germ cells? Perhaps because the living material is very complex and inherently liable to change. Perhaps because it is the vehicle of a multitude of hereditary items among which there are very likely to be reshufflings or rearrangements. Perhaps because the germ cells have very changeful surroundings, the blood, the body cavity fluid, the seawater. Perhaps because deeply saturating outside influences, such as change of climate and habitat, penetrate through the body to its germ cells and provoke them to vary. But we must be patient with the wearisome reiteration of perhaps. Moreover, every many-celled organism reproduced in the usual way arises from an egg cell fertilized by a sperm cell, and the changes involved in and preparatory to this fertilization may make new permutations and combinations of the living items and hereditary qualities not only possible but necessary. It is something like shuffling a pack of cards, but the cards are living. As to the changes wrought on the body during its lifetime by peculiarities in nurture, habits, and surroundings, these dents or modifications are often very important for the individual, but it does not follow that they are directly important for the race, since it is not certain that they are transmissible. Given a crop of variations or new departures or mutations, whatever the inborn novelties may be called, we have then to inquire how these are sifted. The sifting, which means the elimination of the relatively less fit variations and the selection of the relatively more fit, effected in many different ways in the course of the struggle for existence. The organism plays its new card in the game of life, and the consequences may determine survival. The relatively less fit to given conditions will tend to be eliminated, while the relatively more fit will tend to survive. If the variations are hereditary and reappear, perhaps increased in amount, generation after generation, and if the process of sifting continue consistently, the result will be the evolution of the species. The sifting process may be helped by various forms of isolation, which lessen the range of free intercrossing between members of a species, for example by geographical barriers. Interbreeding of similar forms tends to make a stable stock. Outbreeding among dissimilars tends to promote variability. But for an outline like this, it is enough to suggest the general method of organic evolution. Throughout the ages, organisms have been making tentatives, new departures of varying magnitude, and these tentatives have been tested. The method is that of testing all things and holding fast that which is good. End of section 5.
Section 6 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Outline of Science, Volume 1, by J. Arthur Thomson, Section 6. Part 3. Adaptations to Environment. We saw in a previous chapter how the process of evolution led to a mastery of all the haunts of life. But it is necessary to return to these haunts or homes of animals in some detail, so as to understand the peculiar circumstances of each, and to see how in the course of ages of struggle all sorts of self-preserving and race-continuing adaptations or fitnesses have been wrought out and firmly established. Living creatures have spread over all the earth, and in the waters under the earth. Some of them have conquered the underground world, and others the air. It is possible, however, as has been indicated, to distinguish 6 great haunts of life, each tenanted by a distinctive fauna, namely, the shore of the sea, the open sea, the depths of the sea, the fresh waters, the dry land, and the air. In the deep sea there are no plants at all. In the air the only plants are floating bacteria, though there is a sense in which a tree is very aerial, and the orchid perched on its branches still more so. In the other 4 haunts there is a flora as well as a fauna, the two working into one another's hands in interesting and often subtle interrelations, the subject of a separate study. 1. The shore of the sea. The seaweed area. By the shore of the sea, the zoologist means much more than the narrow zone between tide marks. He means the whole of the relatively shallow, well-illumined, seaweed-growing shelf around the continents and continental islands. Technically, this is called the littoral area, and it is divisible into zones, each with its characteristic population. It may be noted that the green seaweeds are highest up on the shore. The brown ones come next. The beautiful red ones are lowest. All of them have got green chlorophyll, which enables them to utilize the sun's rays in photosynthesis, i.e., building up carbon compounds from air, water, and salts. But in the brown and red seaweeds the green pigment is masked by others. It is maintained by some botanists that these other pigments enable their possessors to make more of the scantier light in the deeper waters. However this may be, we must always think of the shore haunt as the seaweed growing area. Directly and indirectly, the life of the shore animals is closely wrapped up with the seaweeds, which afford food and foothold and temper the force of the waves. The minute fragments broken off from seaweeds and from the seagrass, a flowering plant called zostera, form a sort of nutritive sea dust which is swept slowly down the slope from the shore to form a very useful deposit in the quietness of deepish water. It is often found in the stomachs of marine animals living a long way offshore. Conditions of shore life. The littoral area, as defined, is not a large haunt of life. It occupies only about 9 million square miles, a small fraction of the 197 million of the whole earth's surface. But it is a very long haunt, some 150,000 miles, winding in and out by bay and fjord, estuary and creek. Where deep water comes close to cliffs there may be no shore at all. In other places the relatively shallow water, with seaweeds growing over the bottom, may extend outwards for miles. The nature of the shore varies greatly according to the nature of the rocks, according to what the streams bring down from inland, and according to the jetsam that is brought in by the tides. The shore is a changeful place. There is, in the upper reaches, a striking difference between tide in and tide out. There are vicissitudes due to storms, to freshwater floods, to wind-blown sand, and to slow changes of level up and down. The shore is a very crowded haunt, for it is comparatively narrow, and every niche among the rocks may be precious. Keen struggle for existence. It follows that the shore must be the scene of a keen struggle for existence, which includes all the answers back that living creatures make to environing difficulties and limitations. There is struggle for food, accentuated by the fact that small items tend to be swept away by the outgoing tide, or to sink down the slope to deep water. Apart from direct competition, e.g., between hungry hermit crabs, it often involves hard work to get a meal. This is true even of apparently sluggish creatures. Thus the crumb-of-bread sponge, or any other seashore sponge, has to lash large quantities of water through the intricate canal system of its body before it can get a sufficient supply of the microscopic organisms and organic particles on which it feeds. An index of the intensity of the struggle for food is afforded by the nutritive chains which bind animals together. The shore is almost noisy with the conjugation of the verb to eat in its many tenses. 1 pound of rock cod requires for its formation 10 pounds of whelk. 1 pound of whelk requires 10 pounds of sea worms, and 1 pound of worms requires 10 pounds of sea dust. Such is the circulation of matter, ever passing from one embodiment or incarnation to another. Besides struggle for food, there is struggle for foothold and for fresh air, struggle against the scouring tide and against the pounding breakers. The risk of dislodgment is often great, and the fracture of limbs is a common accident. Of kinds of armor, the sea urchin's hedgehog-like test, the crab's shard, the limpet's shell, there is great variety, surpassed only by that of weapons. The sea anemone's stinging cells, the sea urchin's snapping blades, the hermit crab's forceps, the grappling tentacles and parrot's beak jaws of the octopus. Shifts for a living. We get another glimpse of the intensity of the seashore struggle for existence in the frequency of shifts for a living, adaptations of structure or of behavior which meet frequently recurrent vicissitudes. The starfish is often in the dilemma of losing a limb or its life. By a reflex action it jettisons the captured arm and escapes. And what is lost is gradually regrown. The crab gets its leg broken past all mending. It casts off the leg across a weak breakage plane near the base, and within a preformed bandage, which prevents bleeding, a new leg is formed in miniature. Such is the adaptive device, more reflex than reflective, which is called self-mutilation, or autotomy. In another part of this book there is a discussion of camouflaging and protective resemblance. How abundantly these are illustrated on the shore! But there are other shifts for a living. Some of the sandhoppers and their relatives illustrate the puzzling phenomenon of feigning death, becoming suddenly so motionless that they escape the eyes of their enemies. Cuttlefishes, by discharging sepia from their ink bags, are able to throw dust in the eyes of their enemies. Some undisguised shore animals, e.g. crabs, are adepts in a hide-and-seek game. Some fishes, like the butterfish or gunnel, escape between stones where there seemed no opening, and are almost uncatchable in their slipperiness. Subtlest of all, perhaps, is the habit some hermit crabs have of entering into mutually beneficial partnership, commensalism, with sea anemones, which mask their bearers and also serve as mounted batteries, getting transport as their reward, and likewise crumbs from the frequently spread table. But enough has been said to show that the shore haunt exhibits an extraordinary variety of shifts for a living. Parental care on the shore. According to Darwin, the struggle for existence, as a big fact in the economy of animate nature, includes not only competition, but all the endeavors which secure the welfare of the offspring and give them a good send-off in life. So it is without a jolt that we pass from struggle for food and foothold to parental care. The marine leech, called Pontobdella, an interesting greenish warty creature fond of fixing itself to skate, places its egg cocoons in the empty shell of a bivalve mollusk and guards them for weeks, removing any mud that might injure their development. We have seen a British starfish with its fully formed young ones creeping about on its body, though the usual mode of development for shore starfishes is that the young ones pass through a free-swimming larval period in the open water. The father sea spider carries about the eggs attached to two of his limbs. The father seahorse puts his mate's eggs into his breast pocket and carries them there in safety until they are hatched. The father stickleback of the shore pools makes a seaweed nest and guards the eggs which his wives are induced to lay there. The father lumpsucker mounts guard over the bunch of pinkish eggs which his mate has laid in a nook of a rocky shore pool, and drives off intruders with zest. He also aerates the developing eggs by frequently paddling with his pectoral fins and tail, as the Scots name cockpadle probably suggests. It is interesting that the salient examples of parental care in the shore haunt are mostly on the male parent's side, but there is maternal virtue as well. The fauna of the shore is remarkably representative, from unicellular protozoa to birds like the oyster-catcher and mammals like the seals. Almost all the great groups of animals have apparently served an apprenticeship in the shore haunt, and since lessons learned for millions of years sink in and become organically enregistered, it is justifiable to look to the shore as a great school in which were gained racial qualities of endurance, patience, and alertness. 2. The open sea. In great contrast to the narrow, crowded, difficult conditions of the shore haunt, littoral area, are the spacious, bountiful, and relatively easy-going conditions of the open sea, pelagic area, which means the well-lighted surface waters quite away from land. Many small organisms have their maximum abundance at about 50 fathoms, so that the word surface is to be taken generously. The light becomes very dim at 250 fathoms, and the open sea, as a zoological haunt, stops with the light. It is hardly necessary to say that the pelagic plants are more abundant near the surface, and that below a certain depth the population consists almost exclusively of animals. Not a few of the animals sink and rise in the water periodically. There are some that come near the surface by day, and others that come near the surface by night. Of great interest is the habit of the extremely delicate ctenophores, or sea gooseberries, which the splash of a wave would tear into shreds. Whenever there is any hint of a storm, they sink beyond its reach, and the ocean's surface must have remained flat as a mirror for many hours before they can be lured upwards from the calm of their deep retreat. The floating sea meadows. To understand the vital economy of the open sea, we must recognize the incalculable abundance of minute, unicellular plants, for they form the fundamental food supply. Along with these must also be included numerous microscopic animals which have got possession of chlorophyll, or have entered into internal partnership with unicellular algae (symbiosis). These green or greenish plants and animals are the producers, using the energy of the sunlight to help them in building up carbon compounds out of air, water, and salts. The animals which feed on the producers, or on other animals, are the consumers. Between the two come those open sea bacteria that convert nitrogenous material, e.g. from dead plants or animals that other bacteria have rotted, into forms, e.g. nitrates, which plants can reutilize. The importance of these middlemen is great in keeping the circulation of matter a-going. The floating sea meadows, as Sir John Murray called them, are always receiving contributions from inshore waters, where the conditions are favorable for the prolific multiplication of unicellular algae, and there is also a certain amount of non-living sea dust always being swept out from the seaweed and seagrass area. Swimmers and drifters. The animals of the open sea are conveniently divided into the active swimmers, nekton, and the more passive drifters, plankton. The swimmers include whales great and small, such birds as the storm petrel, the fish-eating turtles and sea snakes, such fishes as mackerel and herring, the winged snails or sea butterflies on which whalebone whales largely feed, some of the active cuttles or squids, various open sea prawns and their relatives, some worms like the transparent arrow worm, and such active protozoa as Noctiluca, whose luminescence makes the waves sparkle in the short summer darkness. Very striking as an instance of the insurgence of life are the sea skimmers, Halobatidae, wingless insects related to the water measurers in the ditch. They are found hundreds of miles from land, skimming on the surface of the open sea, and diving in stormy weather. They feed on floating dead animals. The drifters, or easy-going swimmers, for there is no hard and fast line, are represented, for instance, by the flinty-shelled radiolarians and certain of the chalk-forming animals, Globigerinoid, foraminifera; by jellyfishes, swimming bells, and Portuguese men-of-war; by the comb-bearers, or ctenophores; by legions of minute crustaceans; by strange animals called salps, related to the sedentary sea-squirts, and by some sluggish fishes like globe fishes, which often float idly on the surface. Open sea animals tend to be delicately built, with a specific gravity near that of the sea water, with adaptations, such as projecting filaments, which help flotation, and with capacities of rising and sinking according to the surrounding conditions. Many of them are luminescent, and many of them are very inconspicuous in the water, owing to their transparency or their bluish color. In both cases, the significance is obscure. Hunger and love. Hunger is often very much in evidence in the open sea, especially in areas where the plankton is poor. For there is great diversity in this respect, most of the Mediterranean, for instance, having a scanty plankton as compared with the North Sea. In the South Pacific, west of Patagonia, there is said to be an immense sea desert, where there is little plankton, and therefore little in the way of fishes. The success of fisheries in the north, e.g. on the Atlantic cod banks, is due to the richness of the floating sea meadows and the abundance of the smaller constituents of the animal plankton. Hunger is plain enough when the baleen whale rushes through the water with open jaws, engulfing in the huge cavern of its mouth, where the pendant whalebone plates form a huge sieve, incalculable millions of small fry. But there is love as well as hunger in the open sea. The maternal care exhibited by the whale reaches a very high level, and the delicate shell of the female paper nautilus or argonaut, in which the eggs and the young ones are sheltered, may well be described as the most beautiful cradle in the world. Besides the permanent inhabitants of the open sea, there are the larval stages of many shore animals, which are there only for a short time. For there is an interesting give and take between the shore haunt and the open sea. From the shore come nutritive contributions and minute organisms which multiply quickly in the open waters. But not less important is the fact that the open waters afford a safe cradle or nursery for many a delicate larva, e.g. of crab and starfish, acorn shell and sea urchin, which could not survive for a day in the rough and tumble conditions of the shore and the shallow water. After undergoing radical changes and gaining strength, the young creatures return to the shore in various ways. 3. The deep sea. Very different from all the other haunts are the depths of the sea, including the floor of the abysses and the zones of water near the bottom. This haunt, forever unseen, occupies more than a third of the earth's surface, and it is thickly peopled. It came into emphatic notice in connection with the mending of telegraph cables, but the results of the Challenger expedition, 1873 to 1876, gave the first impressive picture of what was practically a new world. Physical conditions. The average depth of the ocean is about 2½ miles. Therefore, since many parts are relatively shallow, there must be enormous depths. A few of these, technically called deeps, are about 6 miles deep, in which Mount Everest would be engulfed. There is enormous pressure in such depths. Even at 2,500 fathoms, it is 2½ tons on the square inch. The temperature is on and off the freezing point of fresh water, due to the continual sinking down of cold water from the poles, especially from the south. Apart from the fitful gleams of luminescent animals, there is utter darkness in the deep waters. The rays of sunlight are practically extinguished at 250 fathoms, though very sensitive bromogelatin plates, exposed at 500 fathoms, have shown faint indications even at that depth. It is a world of absolute calm and silence, and there is no scenery on the floor. A deep, cold, dark, silent, monotonous world. Biological conditions. While some parts of the floor of the abysses are more thickly peopled than others, there is no depth limit to the distribution of life. Wherever the long arm of the dredge has reached, animals have been found, e.g. protozoa, sponges, corals, worms, starfishes, sea urchins, sea lilies, crustaceans, lamp shells, mollusks, ascidians, and fishes, a very representative fauna. In the absence of light there can be no chlorophyll possessing plants, and as the animals cannot all be eating one another, there must be an extraneous source of food supply. This is found in the sinking down of minute organisms which are killed on the surface by changes of temperature and other causes. What is left of them, before or after being swallowed, and of sea dust and mineral particles of various kinds, forms the diversified ooze of the seafloor, a soft, muddy precipitate, which is said to have in places the consistence of butter in summer weather. There seems to be no bacteria in the abysses, so there can be no rotting. Everything that sinks down, even the huge carcass of a whale, must be nibbled away by hungry animals and digested, or else, in the case of most bones, slowly dissolved away. Of the whale there are left only the ear bones, of the shark his teeth. Adaptations to deep sea life. In adaptation to the great pressure the bodies of deep sea animals are usually very permeable, so that the water gets through and through them, as in the case of Venus's flower basket, a flinty sponge which a child's finger would shiver. But when the pressure inside is the same as that outside, nothing happens. In adaptation to the treacherous ooze, so apt to smother, many of the active deep-sea animals have very long, stilt-like legs, and many of the sedentary types are lifted into safety on the end of long stalks, which have their bases embedded in the mud. In adaptation to the darkness, in which there is only luminescence that eyes could see, there is a great development of tactility. The interesting problem of luminescence will be discussed elsewhere. As to the origin of the deep-sea fauna, there seems no doubt that it has arisen by many contributions from the various shore haunts. Following the down-drifting food, many shore animals have in the course of many generations reached the world of eternal night and winter, and become adapted to its strange conditions. For the animals of the deep sea are as fit, beautiful, and vigorous as those elsewhere. There are no slums in nature. 4. The fresh waters. Of the whole earth's surface, the fresh waters form a very small fraction, about 1/100th, but they make up for their smallness by their variety. We think of deep lake and shallow pond, of the great river and the purling brook, of lagoon and swamp, and more besides. There is a striking resemblance in the animal population of widely separated freshwater basins. And this is partly because birds carry many small creatures on their muddy feet from one watershed to another, partly because some of the freshwater animals are descended from types which make their way from the sea and the seashore through estuaries and marshes, and only certain kinds of constitution could survive the migration, and partly because some lakes are landlocked, dwindling relics of ancient seas. And similar forms again would survive the change. A typical assemblage of freshwater animals would include many protozoa, like amoebae and the bell animalcules, a representative of one family of sponges, Spongillidae, the common hydra, many unsegmented worms, notably planarians and nematodes, many annelids related to the earthworms, many crustaceans, insects, and mites, many bivalves and snails, various fishes, a newt or two, perhaps a little mud turtle, or in warm countries a huge crocodilian, various interesting birds like the water ouzel or dipper, and mammals like the water vole and the water shrew. Freshwater animals have to face certain difficulties, the greatest of which are drought, frost, and being washed away in times of flood. There is no more interesting study in the world than an inquiry into the adaptations by which freshwater animals overcome the difficulties of the situation. We cannot give more than a few illustrations. 1. Drought is circumvented by the capacity that many freshwater animals have of lying low and saying nothing. Thus the African mudfish may spend half the year encased in the mud, and many minute crustaceans can survive being dried up for years. 2. Escape from the danger of being frozen hard in the pool is largely due to the almost unique property of water that it expands as it approaches the freezing point. Thus the colder water rises to the surface and forms or adds to the protecting blanket of ice. The warmer water remains unfrozen at the bottom, and the animals live on. 3. The risk of being washed away, e.g. to the sea, is lessened by all sorts of gripping, grappling, and anchoring structures, and by shortening the juvenile stages when the risks are greatest. 5. The dry land. Over and over again in the history of animal life there have been attempts to get out of the water on to terra firma, and many of these have been successful, notably those made 1. By worms, 2. By air-breathing arthropods, and 3. By amphibians. In thinking of the conquest of the dry land by animals, we must recognize the indispensable rule of plants in preparing the way. The dry ground would have proved too inhospitable had not terrestrial plants begun to establish themselves, affording food, shelter, and humidity. There had to be plants before there could be earthworms, which feed on decaying leaves and the like. But how soon was the debt repaid when the earthworms began their worldwide task of forming vegetable mold, opening up the earth with their burrows, circulating the soil by means of their castings, and bruising the particles in their gizzard, certainly the most important mill in the world. Another important idea is that littoral haunts, both on the seashore and in the fresh waters, afforded the necessary apprenticeship and transitional experience for the more strenuous life on dry land. Much that was perfected on land had its beginnings on the shore. Let us inquire, however, what the passage from water to dry land actually implied. This has been briefly discussed in a previous article, on evolution, but the subject is one of great interest and importance. Difficulties and results of the transition from water to land. Leaving the water for dry land implied a loss in freedom of movement, for the terrestrial animal is primarily restricted to the surface of the earth. Thus it became essential that movements should be very rapid and very precise, needs with which we may associate the acquisition of fine, cross-striped, quickly contracting muscles, and also, in time, their multiplication into very numerous separate engines. We exercise 54 muscles in the half second that elapses between raising the heel of our foot in walking and planting it firmly on the ground again. Moreover, the need for rapid, precisely controlled movements implied an improved nervous system, for the brain was a movement-controlling organ for ages before it did much in the way of thinking. The transition to terra firma also involved a greater compactness of body, so that there should not be too great friction on the surface. An animal like the jellyfish is unthinkable on land, and the elongated bodies of some land animals like centipedes and snakes are specially adapted so that they do not sprawl. They are exceptions that prove the rule. Getting on to dry land meant entering a kingdom where the differences between day and night, between summer and winter, are more felt than in the sea. This made it advantageous to have protections against evaporation and loss of heat and other such dangers. Hence a variety of ways in which the surface of the body acquired a thickened skin, or a dead cuticle, or a shell, or a growth of hair, and so forth. In many cases there is an increase of the protection before the winter sets in, e.g., by growing thicker fur, or by accumulating a layer of fat below the skin. But the thickening or protection of the skin involved a partial or total loss of the skin as a respiratory surface. There is more oxygen available on dry land than in the water, but it is not so readily captured. Thus we see the importance of moist internal surfaces for capturing the oxygen which has been drawn into the interior of the body into some sort of lung. A unique solution was offered by tracheate arthropods, such as peripatus, centipedes, millipedes, and insects, where the air is carried to every hole and corner of the body by a ramifying system of air tubes or trachea. In most animals the blood goes to the air; in insects the air goes to the blood. In the robber crab which has migrated from the shore inland, the dry air is absorbed by vascular tufts growing under the shelter of the gill cover. The problem of disposing of eggs or young ones is obviously much more difficult on land than in the water. For the water offers an immediate cradle, whereas on the dry land there were many dangers, e.g., of drought, extremes of temperature, and hungry, sharp-eyed enemies, which had to be circumvented. So we find all manner of ways in which land animals hide their eggs, or their young ones, in holes and nests, on herbs and on trees. Some carry their young ones about after they are born, like the Suriname toad and the kangaroo, while others have prolonged the period of antenatal life during which the young ones develop in safety within their mother, and in very intimate partnership with her in the case of the placental animals. It is very interesting to find that the pioneer animal called Peripatus, which bridges the gap between worms and insects, carries its young for almost a year before birth. Enough has been said to show that the successive conquests of the dry land had great evolutionary results. It is hardly too much to say that the invasion which the amphibians led was the beginning of better brains, more controlled activities, and higher expressions of family life. 6. The air. There are no animals thoroughly aerial, but many insects spend much of their adult life in the free air, and the swift hardly pauses in its flight from dawn to dusk of the long summer day, alighting only for brief moments at the nest to deliver insects to the young. All the active life of bats certainly deserves to be called aerial. The air was the last haunt of life to be conquered, and it is interesting to inquire what the conquest implied. 1. It meant transcending the radical difficulty of terrestrial life which confines the creatures of the dry land to moving on one plane, the surface of the earth. But the power of flight brought its possessors back to the universal freedom of movement which water animals enjoy. When we watch a sparrow rise into the air, just as the cat has completed her stealthy stalking, we see that flight implies an enormous increase of safety. 2. The power of flight also opened up new possibilities of following the prey, of exploring new territories, of prospecting for water. 3. Of great importance, too, was the practicability of placing the eggs and the young, perhaps in a nest, in some place inaccessible to most enemies. When one thinks of it, the rooks' nests swaying on the tree-tops expresses the climax of a brilliant experiment. 4. The crowning advantage was the possibility of migrating, of conquering time by circumventing the arid summer and the severe winter, and of conquering space by passing quickly from one country to another, and sometimes almost girdling the globe. There are not many acquisitions that have meant more to their possessors than the power of flight. It was a key opening the doors of a new freedom. The problem of flight, as has been said in a previous chapter, has been solved 4 times, and the solution has been different in each case. The 4 solutions are those offered by insects, extinct pterodactyls, birds, and bats. Moreover, as has been pointed out, there have been numerous attempts at flight which remain glorious failures, notably the flying fishes, which take a great leap and hold their pectoral fins taut, the flying tree toad, whose webbed fingers and toes form a parachute, the flying lizard, Draco volans, which has its skin pushed out on 5 or 6 greatly elongated mobile ribs, and various flying mammals, e.g., flying phalangers and flying squirrels, which take great swooping leaps from tree to tree. The wings of an insect are hollow, flattened sacs, which grow out from the upper parts of the sides of the 2nd and 3rd rings of the region called the thorax. They are worked by powerful muscles, and are supported like a fan by ribs of chitin, which may be accompanied by air tubes, blood channels, and nerves. The insect's body is lightly built and very perfectly aerated, and the principle of the insect's flight is the extremely rapid striking of the air by means of the lightly built elastic wings. Many an insect has over 200 strokes of its wings in 1 second. Hence, in many cases, the familiar hum, comparable on a small scale to that produced by the rapidly revolving blades of an aeroplane's propeller. For a short distance a bee can outfly a pigeon, but few insects can fly far, and they are easily blown away or blown back by the wind. Dragonflies and bees may be cited as examples of insects that often fly for 2 or 3 miles, but this is exceptional, and the usual shortness of insect flight is an important fact for man, since it limits the range of insects like houseflies and mosquitoes, which are vehicles of typhoid fever and malaria respectively. The most primitive insects, springtails and bristletails, show no trace of wings, while fleas and lice have become secondarily wingless. It is interesting to notice that some insects only fly once in their lifetime, namely, in connection with mating. The evolution of the insect's wing remains quite obscure, but it is probable that insects could run, leap, and parachute before they could actually fly. The extinct flying dragons or pterodactyls had their golden age in the Cretaceous era, after which they disappeared, leaving no descendants. A fold of skin was spread out from the sides of the body by the enormously elongated outermost finger, usually regarded as corresponding to our little finger. It was continued to the hind legs, and thence to the tail. It is unlikely that the pterodactyls could fly far, for they have at most a weak keel on their breastbone. On the other hand, some of them show a marked fusion of dorsal vertebrae, which, as in flying birds, must have served as a firm fulcrum for the stroke of the wings. The quaint creatures varied from the size of a sparrow up to a magnificent spread of 15 to 20 feet from tip to tip of the wings. They were the largest of all flying creatures. The bird's solution to the problem of flight, which will be discussed separately, is centered in the feather, which forms a coherent vane for striking the air. In pterodactyl and bat the wing is a web wing, or patagium, and a small web is to be seen on the front side of the bird's wing. But the bird's patagium is unimportant, and the bird's wing is on an evolutionary tack of its own, a forelimb transformed for bearing the feathers of flight. Feathers are in a general way comparable to the scales of reptiles, but only in a general way, and no transition stage is known between the two. Birds evolved from a bipedal dinosaur stock, as has been noticed already, and it is highly probable that they began their ascent by taking running leaps along the ground, flapping their scaly forelimbs, and balancing themselves in kangaroo-like fashion with an extended tail. A second chapter was probably an arboreal apprenticeship, during which they made a fine art of parachuting, a persistence of which is to be seen in the pigeon gliding from the dovecot to the ground. It is in birds that the mastery of the air reaches its climax, and the mysterious sailing of the albatross and the vulture is surely the most remarkable locomotor triumph that has ever been achieved. Without any apparent stroke of the wings, the bird sails for half an hour at a time, with the wind and against the wind, around the ship and in majestic spirals in the sky, probably taking advantage of currents of air of different velocities, and continually changing the energy of position into energy of motion as it sinks, and energy of motion into energy of position as it rises. It is interesting to know that some dragonflies are also able to sail. The web wing of bats involves much more than the forearm. The double fold of skin begins on the side of the neck, passes along the front of the arm, skips the thumb, and is continued over the elongated palm bones and fingers to the sides of the body again, and to the hind legs, and to the tail, if there is a tail. It is interesting to find that the bones of the bat's skeleton tend to be lightly built, as in birds, that the breastbone has likewise a keel for the better insertion of the pectoral muscles, and that there is a solidifying on the vertebrae of the back, affording, as in birds, a firm basis for the wing action. Such similar adaptations to similar needs, occurring in animals not nearly related to one another, are called convergences, and form a very interesting study. In addition to adaptations which the bat shares with the flying bird, it has many of its own. There are so many nerve endings on the wing, and often also on special skin leaves about the ears and nose, that the bat flying in the dusk does not knock against branches or other obstacles. Some say that it is helped by the echoes of its high-pitched voice, but there is no doubt as to its exquisite tactility. That it usually produces only a single young one at a time is a clear adaptation to flight, and similarly the sharp, mountain-top-like cusps on the back teeth are adapted in insectivorous bats for crunching insects. Whether we think of the triumphant flight of birds, reaching a climax in migration, or of the marvel that a creature of the earth, as a mammal essentially is, should evolve such a mastery of the air as we see in bats, or even of the repeated but splendid failures which parachuting animals illustrate, we gain an impression of the insurgence of living creatures in their characteristic endeavor after fuller well-being. We have said enough to show how well adapted many animals are to meet the particular difficulties of the haunt which they tenant. But difficulties and limitations are ever arising afresh, and so one fitness follows on another. It is natural, therefore, to pass to the frequent occurrence of protective resemblance, camouflage, and mimicry, the subject of the next article. End of section 6. Read by Kara Schallenberg, www.kray.org, on June 28, 2008, in San Diego, California.
Section 7 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by James Christopher. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 7. Part 4. The Struggle for Existence. Animal and Bird Mimicry and Disguise. 1. For every animal one discovers when observing carefully, there must be 10 unseen. This is partially because many animals burrow in the ground or get in underneath things and into dark corners, being what is called cryptozoic or elusive. But it is partly because many animals put on disguise or have in some way acquired a garment of invisibility. This is very common among animals, and it occurs in many forms and degrees. The reason why it is so common is because the struggle for existence is often very keen, and the reasons why the struggle for existence is keen are 4. First, there is a tendency to overpopulation in many animals, especially those of low degree. Second, there is the fact that the scheme of nature involves nutritive change or successive incarnations, one animal depending upon another for food, and all in the long run on plants. Thirdly, every vigorous animal is a bit of a hustler, given to insurgence and sticking out his elbows. There is a fourth great reason for the struggle for existence, namely, the frequent changefulness of the physical environment, which forces animals to answer back or die. But the first 3 reasons have most to do with the very common assumption of some sort of disguise. Even when an animal is in no sense a weakling, it may be very advantageous for it to be inconspicuous when it is resting or when it is taking care of its young. Our problem is the evolution of elusiveness, so far at least as that depends on likeness to surroundings, on protective resemblance to other objects, and in its highest reaches on true mimicry. Color permanently like that of surroundings. Many animals living on sandy places have a light brown color, as is seen in some lizards and snakes. The green lizard is like the grass, and the green tree snake is inconspicuous among the branches. The spotted leopard is suited to the interrupted light of the forest, and it is sometimes hard to tell where the jungle ends and the striped tiger begins. There is no better case than the hare, or the partridge sitting a few yards off in the plowed field. Even a donkey grazing in the dusk is much more readily heard than seen. The experiment has been made of tethering the green variety of praying mantis on green herbage, fastening them with silk threads. They escape the notice of birds. The same is true when the brown variety is tethered on withered herbage. But if the green ones are put on brown plants, or the brown ones on green plants, the birds pick them off. Similarly, out of 300 chickens in a field, 240 white or black and therefore inconspicuous, 60 spotted and inconspicuous, 24 were soon picked off by crows, but only one of these was spotted. This was not the proportion that there should have been if the mortality had been fortuitous. There is no doubt that it often pays an animal to be like its habitual surroundings, like a little piece of scenery if the animal is not moving. It is safe to say that in process of time, wide departures from the safest coloration will be wiped out in the course of nature's ceaseless sifting. But we must not be credulous, and there are 3 cautions to be borne in mind. 1. An animal may be very like its surroundings without there being any protection implied. The arrowworms in the sea are as clear as glass, and so are many open sea animals, but this is because their tissues are so watery, with a specific gravity near that of salt water, and the invisibility does not save them, always or often, from being swallowed by larger animals that gather the harvest of the sea. 2. Among the cleverer animals, it looks as if the creature sometimes sought out a spot where it was most inconspicuous. A spider may place itself in the middle of a little patch of lichen, where its self-effacement is complete. Perhaps it is more comfortable as well as safer to rest in surroundings the general color of which is like that of the animal's body. 3. The fishes that live among the coral reefs are startling in their brilliant coloration, and there are many different patterns. To explain this, it has been suggested that these fishes are so safe among the mazy passages and endless nooks of the reef that they can well afford to wear any color that suits their constitution. In some cases this may be true, but naturalists who have put on a diving suit and walked about among the coral have told us that each kind of fish is particularly suited to some particular place, and that some are suited for midday work and others for evening work. Sometimes there is a sort of box and cox arrangement by which 2 different fishes utilize the same corner at different times. 2. Gradual change of color. The common shore crab shows many different colors in mottlings, especially when it is young. It may be green or gray, red or brown, and so forth, and it is often an admirable adjustment to the color of the rock pool where it is living. Experiments, which require extension, have shown that when the crab has molted, which it has to do very often when it is young, the color of the new shell tends to harmonize with the general color of the rocks and seaweed. How this is brought about we do not know. The color does not seem to change till the next molt, and not then unless there is some reason for it. A full-grown shore crab is well able to look after itself, and it is of interest to notice, therefore, that the variety of coloration is mainly among the small individuals who have, of course, a much less secure position. It is possible, moreover, that the resemblance to the surroundings admits of more successful hunting, enabling the small crab to take its victim unawares. Professor Poulton's experiments with the caterpillars of the small tortoiseshell butterfly showed that in black surroundings the pupae tend to be darker, in white surroundings lighter, in gilded boxes golden, and the same is true in other cases. It appears that the surrounding color affects the caterpillars through the skin during a sensitive period, the 20 hours immediately preceding the last 12 hours of the larval state. The result will tend to make the quiescent pupae less conspicuous during the critical time of metamorphosis. The physiology of this sympathetic coloring remains obscure. Seasonal change of coloring. The ptarmigan molts 3 times in a year. Its summer plumage is rather grouse-like above, with a good deal of rufous brown. The back becomes much more gray in autumn. Almost all the feathers of the winter plumage are white. That is to say, they develop without any pigment, and with numerous gas bubbles in their cells. Now there can be no doubt that this white winter plumage makes the ptarmigan very inconspicuous amidst the snow. Sometimes one comes within a few feet of the crouching bird without seeing it, and this garment of invisibility may save it from the hungry eyes of golden eagles. Similarly, the brown stoat becomes the white ermine, mainly by the growth of a new suit of white fur, and the same is true of the mountain hare. The ermine is all white except the black tip of its tail. The mountain hare in its winter dress is all white save the black tips of its ears. In some cases, especially in the mountain hare, it seems that individual hairs may turn white, by loss of pigment, as may occur in man. According to Metchnikoff, the wandering amoeboid cells of the body, called phagocytes, may creep up into the hairs and come back again with microscopic burdens of pigment. The place of the pigment is taken by gas bubbles, and that is what causes the whiteness. In no animals is there any white pigment. The white color is like that of snow or foam. It is due to the complete reflection of the light from innumerable minute surfaces of crystals or bubbles. The mountain hare may escape the fox the more readily because its whiteness makes it so inconspicuous against a background of snow, and yet at other times we have seen the creature standing out like a target on the dark moorland. So it cuts both ways. The ermine has almost no enemies except the gamekeeper, but its winter whiteness may help it to sneak upon its victims, such as grouse or rabbit, when there is snow upon the ground. In both cases, however, the probability is that the constitutional rhythm which leads to white hair in winter has been fostered and fixed for a reason quite apart from protection. The fact is that for a warm-blooded creature, whether bird or mammal, the physiologically best dress is a white one, for there is less radiation of the precious animal heat from white plumage or white pelage than from any other color. The quality of warm-bloodedness is a prerogative of birds and mammals, and it means that the body keeps an almost constant temperature day and night, year in and year out. This is effected by the automatic internal adjustment which regulates the supply of heat, chiefly from the muscles, to the loss of heat, chiefly through the skin and from the lungs. The chief importance of this internal heat is that it facilitates the smooth continuance of the chemical processes on which life depends. If the temperature falls, as in hibernating mammals, whose warm-bloodedness is imperfect, the rate of the vital process is slowed down, sometimes dangerously. Thus we see how the white coat helps the life of the creature. 3. Rapid color change. Bony flatfishes, like plaice and sole, have a remarkable power of adjusting their hue and pattern to the surrounding gravel and sand, so that it is difficult to find them even when we know that they are there. It must be admitted that they are also very quick to get a sprinkling of sand over their upturned side, so that only the eyes are left showing. But there is no doubt as to the exactness with which they often adjust themselves to be just like a little piece of the substratum on which they lie. They will do this within limits in experimental conditions when they are placed on a quite artificial floor. As these fishes are very palatable, and are much sought after by such enemies as cormorants and otters, it is highly probable that their power of self-effacement often saves their life, and it may be effected within a few minutes, in some cases within a minute. In these self-effacing flatfishes we know with some precision what happens. The adjustment of color and pattern is due to changes in the size, shape, and position of mobile pigment cells, chromatophores, and the skin. But what makes the pigment cells change? The fact that a blind flatfish does not change its color gives us the first part of the answer. The color and the pattern of the surroundings must affect the eye. The message travels by the optic nerve to the brain. From the brain, instead of passing down the spinal cord, the message travels down the chain of sympathetic ganglia. From these it passes along the nerves which comes out of the spinal cord and control the skin. Thus the message reaches the color cells in the skin, and before you have carefully read these lines, the flatfish is slipped on its guidous ring and becomes invisible. The same power of rapid color change is seen in cuttlefish, where it is often an expression of nervous excitement, though it sometimes helps to conceal. It occurs with much subtlety in the Aesop prawn, Hippolyte, which may be brown on a brown seaweed, green on sea lettuce or seagrass, red on red seaweed, and so on through an extensive repertoire. According to the nature of the background, Professor Gimbel writes, so is the mixture of the pigments compounded so as to form a close reproduction both of its color and its pattern. A sweep of the shrimp net detaches a battalion of these sleeping prawns, and if we turn the motley into a dish and give a choice of seaweed, each variety after its kind will select the one with which it agrees in color and vanish. When both young and when full grown, the Aesop prawn takes on the color of its immediate surroundings. At nightfall, Hippolyte, of whatever color, changes to a transparent azure blue. Its stolidity gives place to a nervous restlessness. At the least tremor it leaps violently, and often swims actively from one food plant to another. This blue fit lasts until daybreak, and is then succeeded by the prawn's diurnal tint. Thus, Professor Gamble continues, the color of an animal may express a nervous rhythm. The case of chameleons. The highest level at which rapid color change occurs is among lizards, and the finest exhibition of it is among the chameleons. These quaint creatures are characteristic of Africa, but they also occur in Andalusia, Arabia, Ceylon, and southern India. They are adapted for life on trees, where they hunt insects with great deliberateness and success. The protrusible tongue, ending in a sticky club, can be shot out for about 7 inches in the common chameleon. Their hands and feet are split so that they grip the branches firmly, and the prehensile tail rivals a monkey's. When they wish, they can make themselves very slim, contracting the body from side to side, so that they are not very readily seen. In other circumstances, however, they do not practice self-effacement, but the very reverse. They inflate their bodies, having not only large lungs, but air sacs in connection with them. The throat bulges, the body sways from side to side, and the creature expresses its sentiments in a hiss. The power of color change is very remarkable, and depends partly on the contraction and expansion of the color cells, chromatophores, in the underskin, or dermis, and partially on close-packed refractive granules and crystals of a waste product called guanin. The repertoire of possible colors in the common chameleon is greater than in any other animal except the Aesop prawn. There is a legend of a chameleon which was brown in a brown box, green in a green box, and blue in a blue box, and died when put into one line with tartan. And there is no doubt that one and the same animal has a wide range of colors. The so-called chameleon, Anolis, of North America, is so sensitive that a passing cloud makes it change its emerald hue. There is no doubt that a chameleon may make itself more inconspicuous by changing its color, being affected by the play of light on its eyes. A bright green hue is often seen on those that are sitting among strongly illumined green leaves, but the color also changes with the time of day and with the animal's moods. A sudden irritation may bring about a rapid change. In other cases, a transformation comes about very gradually. When the color change expresses a chameleon's feelings, it might be compared to blushing, but that is due to an expansion of the arteries of the face, allowing more blood to get into the capillaries of the underskin. The case of the chameleon is peculiarly interesting because the animal has two kinds of tactics: self-effacement on the one hand, and bluffing on the other. There can be little doubt that the power of color change sometimes justifies itself by driving off intruders. Dr. Cyril Crossland observed that a chameleon attacked by a fox terrier turned round and opened its great pink mouth in the face of the advancing dog, at the same time rapidly changing color, becoming almost black. This ruse succeeded every time, the dog turning off at once. In natural leafy surroundings the startling effect would be much greater: a sudden throwing off of the mantle of invisibility and the exposure of a conspicuous black body with a large red mouth. 4. Likeness to other things. Dr. H. O. Forbes tells of a flat spider which presents a striking resemblance to a bird's dropping on a leaf. Years after he first found it, he was watching in a forest in the far east when his eye fell on a leaf before him which had been blotched by a bird. He wondered idly why he had not seen for so long another specimen of the bird-dropping spider, Ornithos godates deceptians, and drew the leaf towards him. Instantaneously he got a characteristic sharp nip. It was the spider after all. Here the color resemblance was enhanced by a form resemblance. But why should it profit a spider to be like a bird dropping? Perhaps because it thereby escapes attention, but there is another possibility. It seems that some butterflies, allied to our blues, are often attracted to excrementitious material, and the spider Dr. Forbes observed had actually caught its victim. This is borne out by a recent observation by Dr. D. G. H. Carpenter, who found a Uganda bug closely resembling a bird dropping on sand. The bug actually settled down on a bird dropping on sand and caught a blue butterfly which came to feed there. Some of the walking stick insects belonging to the order of crickets and grasshoppers, Orthoptera, have their body elongated and narrow like a thin dry branch, and they have a way of sticking out their limbs at abrupt and diverse angles, which makes the resemblance to twigs very close indeed. Some of these quaint insects rest through the day and have the remarkable habit of putting themselves into a sort of cataleptic state. Many creatures turn stiff when they get a shock, or pass suddenly into new surroundings, like some of the sandhoppers when we lay them on the palm of our hand. But these twig insects put themselves into this strange state. The body is rocked from side to side for a short time, and then it stiffens. An advantage may be that even if they were surprised by a bird or a lizard, they will not be able to betray themselves even by a tremor. Disguise is perfected by a remarkable habit, a habit which leads us to think of a whole series of different ways of lying low and saying nothing, which are often of life-preserving value. The top end of the series is seen when a fox plays possum. The leaf butterfly, Calima, conspicuously colored on its upper surface, is like a withered leaf when it settles down and shows the underside of its wings. Here again there is a precise form resemblance, for the nervatures on the wings are like the midrib and side veins on a leaf. and the touch of perfection is given in the presence of whitish spots which look exactly like the discolorations produced by lichens on leaves. An old entomologist, Mr. Jennifer Weir, confessed that he repeatedly pruned off a caterpillar on a bush in mistake for a superfluous twig. For many brownish caterpillars fasten themselves by their posterior claspers and by an invisible thread of silk from their mouth, and project from the branch at a twig-like angle. An insect may be the very image of a sharp prickle or a piece of soft moss. A spider may look precisely like a tiny knob on a branch or a fragment of lichen. One of the seahorses, Philopteryx, has frond-like tassels on various parts of its body, so that it looks extraordinarily like the seaweed among which it lives. In a few cases, e.g. among spiders, it has been shown that animals with a special protective resemblance to something else seek out a position where this resemblance tells, and there is urgent need for observations bearing on this selection of environment. 5. Mimicry in the true sense. It sometimes happens that in one and the same place there are two groups of animals not very nearly related which are doubles of one another. Investigation shows that the members of one group, always in the majority, are in some way specially protected, e.g. by being unpalpable. They are the mimicked. The members of the other group, always in the minority, have not got the special protection possessed by the others. They are the mimickers, though the resemblance is not, of course, associated with any conscious imitation. The theory is that the mimickers live on the reputation of the mimicked. If the mimicked are left alone by the birds because they have a reputation for unpalpability, or because they are able to sting, the mimickers survive, although they are palpable and stingless. They succeed not through any virtue of their own, but because of their resemblance to the mimicked, for whom they are mistaken. There are many cases of mimetic resemblance so striking and so subtle that it seems impossible to doubt that the thing works. There are other cases which are rather far-fetched, and may be somewhat of the nature of coincidences. Thus, although Mr. Bates tells us that he repeatedly shot hummingbird moths in mistake for hummingbirds, we cannot think that this is a good illustration of mimicry. What is needed for many cases is what is forthcoming for some, namely, experimental evidence, e.g. that the unpalpable mimic butterflies are left in relative peace, while similar palatable butterflies are persecuted. It is also necessary to show that the mimickers do actually consort with the mimicked. Some beetles and moths are curiously wasp-like, which may be a great advantage. The common dronefly is superficially like a small bee. Some harmless snakes are very like poisonous species. And Mr. Wallace maintained that the powerful friar birds of the East are mimicked by the weak and timid orioles. When the model is unpalpable or repulsive or dangerous, and the mimic the reverse, the mimicry is called Batesian, after Mr. Bates. But there is another kind of mimicry, called Müllerian, after Fritz Mahler, where the mimic is also unpalpable. The theory in this case is that the mimicry serves as a mutual assurance, the members of the ring getting on better by consistently presenting the same appearance, which has come to mean to possible enemies a signal, noli me tangere, leave me alone. There is nothing out of the question in this theory, but it requires to be taken in a critical spirit. It leads us to think of warning colors, which are the very opposite of the disguises which we are now studying. Some creatures like skunks, magpies, coral snakes, cobras, brightly colored tree frogs are obtrusive rather than elusive, and the theory of Alfred Russel Wallace was that the flaunting conspicuousness serves as a useful advertisement, impressing itself on the memories of inexperienced enemies, who soon learn to leave the creatures with warning colors alone. In any case, it is plain that an animal which is as safe as a wasp or a coral snake can afford to wear any suit of clothes it likes. Masking. The episode in Scottish history called the Walking Wood of Burnham, when the advancing troop masked their approach by cutting down branches of the trees, has had its counterpart in many countries. But it is also enacted on the seashore. There are many kinds of crabs that put on disguise with what looks like deliberateness. The sand crab takes a piece of seaweed, nibbles at the end of it, and then rubs it on the back of the carapace or on the legs so that it fixes to the bristles. As the seaweed continues to live, the crab soon has a little garden on its back, which masks the crab's real nature. It is most effective camouflaging, but if the crab continues to grow it has to molt, and that means losing the disguise. It is then necessary to make a new one. The crab must have on the shore something corresponding to a reputation. That is to say, other animals are clearly or dimly aware that the crab is a voracious and combative creature. How useful to the crab, then, to have its appearance cloaked by a growth of innocent seaweed, or sponge, or zoophyte. It will enable the creature to sneak up upon its victims, or to escape the attention of its own enemies. If a narrow-beaked crab is cleaned artificially, it will proceed to clothe itself again. The habit has become instinctive. And it must be admitted that while a particular crab prefers a particular kind of seaweed for its dress, it will cover itself with unsuitable and even conspicuous material, such as pieces of colored cloth, if nothing better is available. The disguise differs greatly, for one crab is masked by a brightly colored and unpalpable sponge densely packed with flinty needles. Another cuts off the tunic of a sea squirt and throws it over its shoulders. Another trundles about a bivalve shell. The facts recall the familiar case of the hermit crab, which protects its soft tail by tucking it into the empty shell of a periwinkle or a whelk or some other sea snail, and that case leads on to the elaboration known as commensalism, where the hermit crab fixes sea anemones on the back of its borrowed house. The advantage here is beyond that of masking, for the sea anemone can sting, which is a useful quality in a partner. That this second advantage may become the main one is evident in several cases where the sea anemone is borne, just like a weapon, on each of the crustacean's great claws. Moreover, as the term commensalism, eating at the same table, suggests, the partnership is mutually beneficial, for the sea anemone is carried about by the hermit crab, and it doubtless gets its share of crumbs from its partner's frequent meals. There is a very interesting sidelight on the mutual benefit in the case of a dislodged sea anemone which skulked for a while and then waited in a state of preparedness until a hermit crab passed it and touched it, whereupon the sea anemone gripped and slowly worked itself up to the back of the shell. 6. Other kinds of elusiveness. There are various kinds of disguise which are not readily classified. A troop of cuttlefish swimming in the sea is a beautiful sight. They keep time with one another in their movements, and they show the same change of color almost at the same moment. They are suddenly attacked, however, by a small shark, and then comes a simultaneous discharge of sepia from their ink bags. There are clouds of ink in the clear water, for, as Professor Hickson puts it, the cuttlefish have thrown dust in the eyes of their enemies. One can see a newborn cuttlefish do this a minute after it escapes from the egg. Very beautiful is the way in which many birds, like our common cayfinch, disguise the outside of their nest with moss and lichens and other trifles felted together, so that the cradle is as inconspicuous as possible. There seems to be a touch of art in fastening pieces of spider webs on the outside of a nest. How curious is the case of the tree sloth of South American forest, that walks slowly, down backwards along the undersides of the branches, hanging on by its long curved fingers and toes. It is a nocturnal animal, and therefore not in special danger, but when resting during the day it is almost invisible because its shaggy hair is so like certain lichens and other growths on the branches. But the protective resemblance is enhanced by the presence of a green alga, which actually lives on the surface of the sloth's hairs, an alga like the one that makes tree stems and gateposts green in damp weather. There is no commoner sight in the early days of summer than the cuckoo spit on the grasses and herbage by the wayside. It is conspicuous, and yet it is said to be left severely alone by almost all creatures. In some way it must be a disguise. It is a sort of soap made by the activity of small frog hoppers while they are still in the wingless larval stage, before they begin to hop. The insect pierces with its sharp mouth parts the skin of the plant and sucks in sweet sap which by and by overflows over its body. It works its body up and down many times, whipping in air which mixes with the sugary sap, reminding one of how whipped egg is made. But along with the sugary sap in the air there is a little ferment from the food canal and a little wax from glands on the skin, and the four things mixed together make a kind of soap which lasts through the heat of the day. There are many other modes of disguise besides those which we have been able to illustrate. Indeed, the biggest fact is that there are so many, for it brings us back to the idea that life is not an easy business. It is true, as Walt Whitman says, that animals do not sweat and whine about their condition. Perhaps it is true, as he says, that not one is unhappy over the whole earth. But there is another truth, that this world is not a place for the unlit lamp and the ungirt loin, and that when a creature has not armor or weapons or cleverness, it must find some path of safety or go back. One of these paths of safety is disguise, and we have illustrated its evolution. End of Section 7. Recording by James Christopher, jxchristopher@yahoo.com.
Section 8 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Outline of Science, Volume 1 by J. Arthur Thomson. Section 8. Part 5. The Ascent of Man. 1. No one thinks less of Sir Isaac Newton because he was born a very puny infant, and no one should think less of the human race because it sprang from a stock of arboreal mammals. There is no doubt as to man's apartness from the rest of creation when he is seen at his best, a little lower than the angels, crowned with glory and honor. What a piece of work! How noble in reason, how infinite in faculty, in form and moving, how express and admirable, in action how like an angel, in apprehension so like a god. Nevertheless, all the facts point to his affiliation to the stock to which monkeys and apes also belong. Not, indeed, that man is descended from any living ape or monkey. It is rather that he and they have sprung from a common ancestry, are branches of the same stem. This conclusion is so momentous that the reasons for accepting it must be carefully considered. They were expounded with masterly skill in Darwin's Descent of Man in 1871, a book which was but an expansion of a chapter in The Origin of Species, 1859. Anatomical proof of man's relationship with a simian stock. The anatomical structure of man is closely similar to that of the anthropoid apes, the gorilla, the orang, the chimpanzee, and the gibbon. Bone for bone, muscle for muscle, blood vessel for blood vessel, nerve for nerve, man and ape agree. As the conservative anatomist Sir Richard Owen said, there is between them an all-pervading similitude of structure. Differences, of course, there are, but they are not momentous, except man's big brain, which may be 3 times as heavy as that of a gorilla. The average human brain weighs about 48 ounces. The gorilla brain does not exceed 20 ounces at its best. The capacity of the human skull is never less than 55 cubic inches. In the orang and the chimpanzee, the figures are 26 and 27.5 respectively. We are not suggesting that the most distinctive features of man are such as can be measured and weighed, but it is important to notice that the main seat of his mental powers is physically far ahead of that of the highest of the anthropoid apes. Man alone is thoroughly erect after his infancy is past. His head, weighted with the heavy brain, does not droop forward as the ape's does. With his erect attitude there is perhaps to be associated his more highly developed vocal organs. Compared with an anthropoid ape, man has a bigger and more upright forehead, a less protrusive face region, smaller cheekbones and eyebrow ridges, and more uniform teeth. He is almost unique in having a chin. Man plants the sole of his foot flat on the ground, his big toe is usually in a line with the other toes, and he has a better heel than any monkey has. The change of the shape of the head is to be thought of in connection with the enlargement of the brain, and also in connection with the natural reduction of the muzzle region, when the hand was freed from being an organ of support and became suited for grasping food and conveying it to the mouth. Everyone is familiar in man's clothing with traces of the past persisting in the present, though their use has long since disappeared. There are buttons on the back of the waist of the morning coat, to which the tails of the coat used to be fastened up, and there are buttons, occasionally with buttonholes, at the wrist, which were once useful in turning up the sleeve. The same is true of man's body, which is a veritable museum of relics. Some anatomists have made out a list of over 100 of these vestigial structures, and though this number is perhaps too high, there is no doubt that the list is long. In the inner upper corner of the eye there is a minute tag, but larger in some races than in others, which is the last dwindling relic of the third eyelid, used in cleaning the front of the eye, which most mammals possess in a large and well-developed form. It can be easily seen, for instance, in ox and rabbit. In man and in monkeys it has become a useless vestige, and the dwindling must be associated with the fact that the upper eyelid is much more mobile in man and monkeys than in the other mammals. The vestigial third eyelid in man is enough of itself to prove his relationship with the mammals, but it is only one example out of many. Some of these are discussed in the article dealing with the human body, but we may mention the vestigial muscles going to the ear trumpet, man's dwindling counterpart of the skin-twitching muscle, which we see a horse use when he jerks a fly off his flanks, and the short tail, which in the 7-weeks-old human embryo is actually longer than the leg. Without committing ourselves to a belief in the entire uselessness of the vermiform appendix, which grows out as a blind alley at the junction of the small intestine with the large, we are safe in saying that it is a dwindling structure, the remains of a blind gut which must have been capacious and useful in ancestral forms. In some mammals, like the rabbit, the blind gut is the bulkiest structure in the body, and bears the vermiform appendix at its far end. In man, the appendix alone is left, and it tells its tale. It is interesting to notice that it is usually longer in the orang than in man, and that it is very variable, as dwindling structures tend to be. One of the unpleasant expressions of this variability is the liability to go wrong, hence appendicitis. Now these vestigial structures are, as Darwin said, like the unsounded, that is, functionless letters in words, such as the O in leopard, the B in doubt, the G in rain. They are of no use, but they tell us something of the history of the words. So do man's vestigial structures reveal his pedigree. They must have an historical or evolutionary significance. No other interpretation is possible. Some men, oftener than women, show on the inturned margin of the ear trumpet or pinna a little conical projection of great interest. It is the vestige of the tip of the pointed ear of lower mammals, and it is well named Darwin's point. It was he who described it as a surviving symbol of the stirring times and dangerous days of man's animal youth. 2. Physiological proof of man's relationship with a simian stock. The everyday functions of the human body are practically the same as those of the anthropoid ape, and similar disorders are common to both. Monkeys may be infected with certain microbes to which man is peculiarly liable, such as the bacillus of tuberculosis. Darwin showed that various human gestures and facial expressions have their counterparts in monkeys. The sneering curl of the upper lip, which tends to expose the canine tooth, is a case in point, though it may be seen in other mammals besides monkeys, in dogs, for instance, which are at some considerable distance from the simian branch to which man's ancestors belonged. When human blood is transfused into a dog or even a monkey, it behaves in a hostile way to the other blood, bringing about a destruction of the red blood corpuscles. But when it is transfused into a chimpanzee, there is an harmonious mingling of the two. This is a very literal demonstration of man's blood relationship with the higher apes. But there is a finer form of the same experiment. When the blood fluid or serum of a rabbit, which has had human blood injected into it, is mingled with human blood, it forms a cloudy precipitate. It forms almost as marked a precipitate when it is mingled with the blood of an anthropoid ape, but when it is mingled with the blood of an American monkey, there is only a slight clouding after a considerable time and no actual precipitate. When it is added to the blood of one of the distantly related half-monkeys or lemurs, there is no reaction, or only a very weak one. With the blood of mammals off the simian line altogether, there is no reaction at all. Thus, as a distinguished anthropologist, Professor Schwabel, has said, we have in this not only a proof of the literal blood relationship between man and apes, but the degree of relationship with the different main groups of apes can be determined beyond possibility of mistake. We can imagine how this modern line of experiment would have delighted Darwin. Embryological proof of man's relationship with a simian stock. In his individual development, man does in some measure climb up his own genealogical tree. Stages in the development of the body during its 9 months of antenatal life are closely similar to stages in the development of the anthropoid embryo. Babies born in times of famine or siege are sometimes, as it were, imperfectly finished, and sometimes have what may be described as monkeyish features and ways. A visit to an institution for the care of children who show arrested, defective, or disturbed development leaves one sadly impressed with the risk of slipping down the rungs of the steep ladder of evolution. And even in adults, the occurrence of serious nervous disturbance, such as shell shock, is sometimes marked by relapses to animal ways. It is a familiar fact that a normal baby reveals the past in its surprising power of grip, and the careful experiments of Dr. Lewis Robinson showed that an infant 3 weeks old could support its own weight for over 2 minutes, holding on to a horizontal bar. In many cases, no signs of distress is evinced and no cry uttered until the grasp begins to give. This persistent grasp probably points back to the time when the baby had to cling to its arboreal mother. The human tail is represented in the adult by a fusion of 4 or 5 vertebrae forming the coccyx at the end of the backbone, and is normally concealed beneath the flesh, but in the embryo the tail projects freely and is movable. Up to the 6th month of the antenatal sleep, the body is covered, all but the palms and soles, with longish hair, the lanugo, which usually disappears before birth. This is a stage in the normal development, which is reasonably interpreted as a recapitulation of a stage in the racial evolution. We draw this inference when we find that the unborn offspring of an almost hairless whale has an abundant representation of hairs. We must draw a similar inference in the case of man. It must be noticed that there are two serious errors in the careless statement often made that man in his development is at one time like a little fish, at a later stage like a little reptile, at a later stage like a little primitive mammal, and eventually like a little monkey. The first error here is that the comparison should be made with embryo fish, embryo reptile, embryo mammal, and so on. It is in the making of the embryos that the great resemblance lies. When the human embryo shows the laying down of the essential vertebrate characters, such as brain and spinal cord, then it is closely comparable to the embryo of a lower vertebrate at a similar stage. When, at a subsequent stage, its heart, for instance, is about to become a four-chambered mammalian heart, it is closely comparable to the heart of, let us say, a turtle, which never becomes more than three-chambered. The point is that in the making of the organs of the body, say brain and kidneys, the embryo of man pursues a path closely corresponding to the path followed by the embryos of other backboned animals lower in the scale, but at successive stages it parts company with these, with the lowest first, and so on in succession. A human embryo is never like a little reptile, but the developing organs pass through stages which very closely resemble the corresponding stages in lower types, which are in a general way ancestral. The second error is that every kind of animal, man included, has from the first a certain individuality, with peculiar characteristics which are all its own. This is expressed by the somewhat difficult word specificity, which just means that every species is itself and no other. So, in the development of the human embryo, while there are close resemblances to the embryos of apes, monkeys, other mammals, and even, at earlier stages still, to the embryos of reptile and fish, it has to be admitted that we are dealing from first to last with a human embryo with peculiarities of its own. Every human being begins his or her life as a single cell, a fertilized egg cell, a treasure house of all the ages. For in this living microcosm, only a small fraction, 1/125th of an inch in diameter, there is condensed, who can imagine how, all the natural inheritance of man, all the legacy of his parentage, of his ancestry, of his long pre-human pedigree. Darwin called the pinhead brain of the ant the most marvelous atom of matter in the world, but the human ovum is more marvelous still. It has more possibilities in it than any other thing, yet without fertilization it will die. The fertilized ovum divides and redivides. Thus results a ball of cells and a sac of cells. Gradually, division of labor becomes the rule. There is a laying down of nervous system and food canal, muscular system and skeleton, and so proceeds what is learnedly called differentiation. Out of the apparently simple there emerges the obviously complex. As Aristotle observed more than 2,000 years ago, in the developing egg of the hen there soon appears the beating heart. There is nothing like this in the non-living world. But to return to the developing human embryo, there is formed from and above the embryonic food canal a skeletal rod, which is called the notochord. It thrills the imagination to learn that this is the only supporting axis that the lower orders of the backboned race possess. The curious thing is that it does not become the backbone, which is certainly one of the essential features of the vertebrate race. The notochord is the supporting axis of the pioneer backboned animals, namely the lancelets and the roundmouths, cyclostomes, such as the lamprey. They have no backbone in the strict sense, but they have this notochord. It can easily be dissected out in the lamprey, a long, gristly rod. It is surrounded by a sheath which becomes the backbone of most fishes and of all higher animals. The interesting point is that although the notochord is only a vestige in the adults of these types, it is never absent from the embryo. It occurs even in man, a short-lived relic of the primeval supporting axis of the body. It comes and then it goes, leaving only minute traces in the adult. We cannot say that it is of any use unless it serves as a stimulus to the development of its substitute, the backbone. It is only a piece of preliminary scaffolding, but there is no more eloquent instance of the living hand of the past. One other instance must suffice of what Professor Lull calls the wonderful changes wrought in the dark of the antenatal period, which recapitulate in rapid abbreviation the great evolutionary steps which were taken by man's ancestors during the long night of the geological past. On the sides of the neck of the human embryo there are 4 pairs of slits, the visceral clefts, openings from the beginning of the food canals to the surface. There is no doubt as to their significance. They correspond to the gill slits of fishes and tadpoles. Yet in reptiles, birds, and mammals, they have no connection with breathing, which is their function in fishes and amphibians. Indeed, they are not of any use at all, except that the first becomes the eustachian tube bringing the ear passage into connection with the back of the mouth, and that the second and third have to do with the development of a curious organ called the thymus gland. Persistent, nevertheless, these gill slits are, recalling even in man an aquatic ancestry of many millions of years ago. When all these lines of evidence are considered, they are seen to converge in the conclusion that man is derived from a simian stock of mammals. He is solidary with the rest of creation. To quote the closing words of Darwin's Descent of Man, "We must, however, acknowledge, as it seems to me, that man with all his noble qualities, with sympathy which feels for the most debased, with benevolence which extends not only to other men, but to the humblest living creature, with his god-like intellect which has penetrated into the movements and constitution of the solar system, with all these exalted powers, man still bears in his bodily frame the indelible stamp of his lowly origin." We should be clear that this view does not say more than that man sprang from a stock common to him and to the higher apes. Those who are repelled by the idea of man's derivation from a simian type should remember that the theory implies rather more than this, namely, that man is the outcome of a genealogy which has implied many millions of years of experimenting and sifting, the groaning and travailing of a whole creation. Speaking of man's mental qualities, Sir Ray Lancaster says, "They justify the view that man forms a new departure in the gradual unfolding of nature's predestined plan." In any case, we have to try to square our views with the facts, not the facts with our views. And while one of the facts is that man stands unique and apart, the other is that man is a scion of a progressive simian stock. Naturalists have exposed the pit whence man has been digged, and the rock whence he has been hewn, but it is surely a heartening encouragement to know that it is an ascent, not a descent, that we have behind us. There is wisdom in Pascal's maxim, "It is dangerous to show man too plainly how like he is to the animals, without at the same time reminding him of his greatness. It is equally unwise to impress him with his greatness and not with his lowliness. It is worse to leave him in ignorance of both, but it is very profitable to recognize the two facts." 3. Man's pedigree. The facts of anatomy, physiology, and embryology, of which we have given illustrations, all point to man's affiliation with the order of monkeys and apes. To this order is given the name primates, and our first and second question must be when and whence the primates began. The rock record answers the first question. The primates emerged about the dawn of the Eocene era, when grass was beginning to cover the earth with a garment. Their ancestral home was in the north in both hemispheres, and then they migrated to Africa, India, Malay, and South America. In North America the primates soon became extinct, and the same thing happened later on in Europe. In this case, however, there was a repeopling from the south in the lower Miocene, and then a second extinction in the upper Pliocene, before man appeared. There is considerable evidence in support of Professor R.S. Lull's conclusion that in southern Asia, Africa, and South America, the evolution of primates was continuous since the first great southward migration, and there is, of course, an abundant modern representation of primates in these regions today. As to the second question, whence the primates sprang, the answer must be more conjectural. But it is a reasonable view that carnivores and primates sprang from a common insectivore stock, the one order diverging towards flesh-eating and hunting on the ground, the other order diverging towards fruit-eating and arboreal habits. There is no doubt that the insectivores, including shrews, tree shrews, hedgehog, mole, and the like, were very plastic and progressive mammals. What followed in the course of ages was the divergence of branch after branch from the main primate stem. First there diverged the South American monkeys on a line of their own, and then the Old World monkeys, such as the macaques and baboons. Ages passed, and the main stems gave off, in the Oligocene period, the branch now represented by the small anthropoid apes, the gibbon and the siamang. Distinctly later there diverged the branch of the large anthropoid apes, the gorilla, the chimpanzee, and the orang. That left a generalized humanoid stock separated off from all monkeys and apes, and including the immediate precursors of man. When this sifting out of a generalized humanoid stock took place remains very uncertain. some authorities referring it to the Miocene, others to the early Pliocene. Some would estimate its date at 500,000 years ago, others at 2 millions. The fact is that questions of chronology do not as yet admit of scientific statement. We are on firmer, though still uncertain ground, when we state the probability that it was in Asia that the precursors of man were separated off from the monkeys and apes, and began to be terrestrial rather than arboreal. Professor Lull points out that Asia is nearest to the oldest known human remains in Java, and that Asia was the seat of the most ancient civilizations and the original home of many domesticated animals and cultivated plants. The probability is that the cradle of the human race was in Asia. Man's arboreal apprenticeship. At this point it will be useful to consider man's arboreal apprenticeship and how he became a terrestrial journeyman. Professor Wood-Jones has worked out very convincingly the thesis that man had no direct four-footed ancestry, but that the primate stock to which he belongs was from its first divergence arboreal. He maintains that the leading peculiarities of the immediate precursors of man were wrought out during a long arboreal apprenticeship. The first great gain of arboreal life on bipedal erect lines, not after the quadrupedal fashion of tree sloths, for instance, was the emancipation of the hand. The foot became the supporting and branch-gripping member, and the hand was set free to reach upward, to hang on by, to seize the fruit, to lift it and hold it to the mouth, and to hug the young one close to the breast. The hand thus set free has remained plastic, a generalized, not a specialized member. Much has followed from man's handiness. The arboreal life had many other consequences. It led to an increased freedom of movement of the thigh on the hip joint, to muscular arrangements for balancing the body on the leg, to making the backbone a supple yet stable curved pillar, to a strongly developed collarbone which is only found well formed when the forelimb is used for more than support, and to a power of opposing the thumb and the big toe to the other digits of the hand and foot, an obvious advantage for branch gripping. But the evolution of a free hand made it possible to dispense with protrusive lips and gripping teeth. Thus began the recession of the snout region, the associated enlargement of the brain box, and the bringing of the eyes to the front. The overcrowding of the teeth that followed the shortening of the snout was one of the taxes on progress of which modern man is often reminded in his dental troubles. Another acquisition associated with arboreal life was a greatly increased power of turning the head from side to side, a mobility very important in locating sounds and in exploring with the eyes. Furthermore, there came about a flattening of the chest and of the back, and the movements of the midriff or diaphragm came to count for more in respiration than the movements of the ribs. The sense of touch came to be of more importance, and the sense of smell of less. The part of the brain receiving tidings from hand and eye and ear came to predominate over the part for receiving olfactory messages. Finally, the need for carrying the infant about among the branches must surely have implied an intensification of family relations, and favored the evolution of gentleness. It may be urged that we are attaching too much importance to the arboreal apprenticeship, since many tree-loving animals remain today very innocent creatures. To this reasonable objection there are two answers. First, that in its many acquisitions the arboreal evolution of the humanoid precursors of man prepared the way for the survival of a human type marked by a great step in brain development, and second, that the passage from the humanoid to the human was probably associated with a return to Mother Earth. According to Professor Lull, to whose fine textbook Organic Evolution, 1917, we are much indebted, climatic conditions in Asia in the Miocene or early Pliocene were such as to compel the descent of the pre-human ancestor from the trees, a step which was absolutely essential to further human development. Continental elevation and consequent aridity led to a dwindling of the forests, and forced the ape-man to come to earth, and at last arose the man. According to Lull, the descent from the trees was associated with the assumption of a more erect posture, with increased liberation and plasticity of the hand, with becoming a hunter, with experiments towards clothing and shelter, with an exploring habit, and with the beginning of communal life. It is a plausible view that the transition from the humanoid to the human was effected by a discontinuous variation of considerable magnitude, which is nowadays called a mutation, and that it had mainly to do with the brain and the vocal cords. But given the gains of the arboreal apprenticeship, the stimulus of an enforced descent to terra firma, and an evolving brain and voice, We can recognize accessory factors which help success to succeed. Perhaps the absence of great physical strength prompted reliance on wits. The prolongation of infancy would help to educate the parents in gentleness. The strengthening of the feeling of kinship would favor the evolution of family and social life, of which there are many anticipations at lower levels. There is much truth in the saying, "Man did not make society, society made man." A continuation of the story will deal with the emergence of the primitive types of man and the gradual ascent of the modern species. End of section 8.
Section 9 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Laurie Ann Walden. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 9. Part 5, The Ascent of Man, continued. 4. Tentative Men. So far, the story has been that of the sifting out of a humanoid stock, and of the transition to humankind from the ancestors of apes and men to the man-ape, and from the man-ape to man. It looks as if the sifting out process had proceeded further, for there were several human branches that did not lead on to the modern type of man. 1. The first of these is represented by the scanty fossil remains known as Pithecanthropus erectus, found in Java in fossiliferous beds which date from the end of the Pliocene or the beginning of the Pleistocene era. Perhaps this means 500,000 years ago, and the remains occurred along with those of some mammals which are now extinct. Unfortunately, the remains of Pithecanthropus the erect consisted only of a skullcap, a thigh bone, and 2 back teeth, so it is not surprising that experts should differ considerably in their interpretation of what was found. Some have regarded the remains as those of a large gibbon, others as those of a pre-human ape-man, and others as those of a primitive man off the main line of ascent. According to Sir Arthur Keith, Pithecanthropus was "a being human in stature, human in gait, human in all its parts, save its brain." The thigh bone indicates a height of about 5 feet 7 inches, 1 inch less than the average height of the men of today. The skull cap indicates a low, flat forehead, beetling brows, and a capacity about 2/3 of the modern size. The remains were found by Dubois in 1894, in Tranil, in central Java. 2. The next offshoot is represented by the Heidelberg man, Homo heidelbergensis, discovered near Heidelberg in 1907 by Dr. Schoetensack. But the remains consisted only of a lower jaw and its teeth. Along with this relic were bones of various mammals, including some long since extinct in Europe, such as elephant, rhinoceros, bison, and lion. The circumstances indicate an age of perhaps 300,000 years ago. There were also very crude flint implements, or eoliths. But the teeth are human teeth, and the jaw seems transitional between that of an anthropoid ape and that of man. Thus there was no chin. According to most authorities, the lower jaw from the Heidelberg sandpit must be regarded as a relic of a primitive type off the main line of human ascent. 3. It was in all probability in the Pliocene that there took origin the Neanderthal species of man, Homo neanderthalensis, first known from remains found in 1856 in the Neanderthal ravine near Dusseldorf. According to some authorities, Neanderthal man was living in Europe 250,000 years ago. Other specimens were afterwards found elsewhere, e.g. in Belgium, the men of Spee, in France, in Croatia, and at Gibraltar, so that a good deal is known of Neanderthal man. He was a loose-limbed fellow, short of stature and of slouching gait, but a skillful artificer, fashioning beautifully worked flints with a characteristic style. He used fire, he buried his dead reverently and furnished them with an outfit for a long journey, and he had a big brain. But he had great beetling, ape-like eyebrow ridges and massive jaws, and he showed simian characters swarming in the details of his structure. In most of the points in which he differs from modern man, he approaches the anthropoid apes, and he must be regarded as a low type of man off the main line. Huxley regarded the Neanderthal man as a low form of the modern type, but expert opinion seems to agree rather with the view maintained in 1864 by Professor William King of Galway, that the Neanderthal man represents a distinct species off the main line of ascent. He disappeared with apparent suddenness, like some aboriginal races today, about the end of the fourth great ice age, but there is evidence that before he ceased to be there had emerged a successor rather than a descendant, the modern man. 4. Another offshoot from the main line is probably represented by the Piltdown man, found in Sussex in 1912. The remains consisted of the walls of the skull, which indicate a large brain, and a high forehead without the beetling eyebrows of the Neanderthal man and Pithecanthropus. The find included a tooth and part of a lower jaw, but these perhaps belong to some ape, for they are very discrepant. The Piltdown skull represents the most ancient human remains as yet found in Britain, and Dr. Smith Woodward's establishment of a separate genus Eoanthropus expresses his conviction that the Piltdown man was off the line of the evolution of the modern type. If the tooth and piece of lower jaw belong to the Piltdown skull, then there was a remarkable combination of ape-like and human characters. As regards the brain, inferred from the skull walls, Sir Arthur Keith says: "All the essential features of the brain of modern man are to be seen in the brain cast. There are some which must be regarded as primitive. There can be no doubt that it is built on exactly the same lines as our modern brains. A few minor alterations would make it in all respects a modern brain. Although our knowledge of the human brain is limited, there are large areas to which we can assign no definite function. We may rest assured that a brain which was shaped in a mold so similar to our own was one which responded to the outside world as ours does. Piltdown man saw, heard, felt, thought, and dreamt, much as we do still." And this was 150,000 years ago at a modern estimate, and some would say 500,000. There is neither agreement nor certainty as to the antiquity of man, except that the modern type was distinguishable from its collaterals hundreds of thousands of years ago. The general impression left is very grand. In remote antiquity the primate stem diverged from the other orders of mammals. It sent forth its tentative branches, and the result was a tangle of monkeys. Ages passed, and the monkeys were left behind, while the main stem, still probing its way, gave off the anthropoid apes, both small and large. But they too were left behind, and the main line gave off other experiments, indications of which we know in Java, at Heidelberg, in the Neanderthal, and at Piltdown. None of these lasted or was made perfect. They represent tentative men who had their day and ceased to be, our predecessors rather than our ancestors. Still, the main stem goes on evolving, and who will be bold enough to say what fruit it has yet to bear? Primitive men. Ancient skeletons of men of the modern type have been found in many places, e.g., Coombe Capelle in Dordogne, Galley Hill in Kent, Cro-Magnon in Périgord, Mentone on the Riviera, and they are often referred to as cave men, or men of the early Stone Age. They had large skulls, high foreheads, well-marked chins, and other features such as modern man possesses. They were true men at last, that is to say, like ourselves. The spirited pictures they made on the walls of caves in France and Spain show artistic sense and skill. Well-finished statuettes representing nude female figures are also known. The elaborate burial customs point to a belief in life after death. They made stone implements, knives, scrapers, gravers, and the like, of the type known as Paleolithic, and these show interesting gradations of skill and peculiarities of style. The cave men lived between the 3rd and 4th ice ages, along with cave bear, cave lion, cave hyena, mammoth, woolly rhinoceros, Irish elk, and other mammals now extinct, taking us back to 30,000 to 50,000 years ago, and many would say much more. Some of the big-brained skulls of these Paleolithic cavemen show not a single feature that could be called primitive. They show teeth which in size and form are exactly the same as those of 1,000 generations afterwards, and suffering from gum boil too. There seems little doubt that these vigorous Paleolithic cavemen of Europe were living for a while contemporaneously with the men of Neanderthal, and it is possible that they directly or indirectly hastened the disappearance of their more primitive collaterals. Curiously enough, however, they had not themselves adequate lasting power in Europe, for they seem for the most part to have dwindled away, leaving perhaps stray present-day survivors in isolated districts. The probability is that after their decline Europe was repeopled by immigrants from Asia. It cannot be said that there is any inherent biological necessity for the decline of a vigorous race. Many animal races go back for millions of years, but in mankind the historical fact is that a period of great racial vigor and success is often followed by a period of decline, sometimes leading to practical disappearance as a definite race. The causes of this waning remain very obscure, sometimes environmental, sometimes constitutional, sometimes competitive. Sometimes the introduction of a new parasite, like the malaria organism, may have been to blame. After the Ice Ages had passed, perhaps 25,000 years ago, the Paleolithic culture gave place to the Neolithic. The men who made rudely dressed but often beautiful stone implements were succeeded or replaced by men who made polished stone implements. The earliest inhabitants of Scotland were of this Neolithic culture, migrating from the continent when the ice fields of the great glaciation had disappeared. Their remains are often associated with the 50-foot beach, which, though now high and dry, was the seashore in early Neolithic days. Much is known about these men of the polished stones. They were hunters, fowlers, and fishermen, without domesticated animals or agriculture, short folk, 2 or 3 inches below the present standard, living an active, strenuous life. Similarly, for the South, Sir Arthur Keith pictures for us a Neolithic community at Coldham in Kent, dating from about 4,000 years ago, a few ticks of the geological clock. It consisted in this case of agricultural pioneers, men with large heads and big brains, about 2 inches shorter in stature than the modern British average, 5 feet 8 inches, with better teeth and broader palates than men have in these days of soft food, with beliefs concerning life and death similar to those that swayed their contemporaries in Western and Southern Europe. Very interesting is the manipulative skill they showed on a large scale in erecting standing stones, probably connected with calendar keeping and with worship, and on a small scale in making daring operations on the skull. 4,000 years ago is given as a probable date for that early community in Kent, but evidences of Neolithic man occur in situations which demand a much greater antiquity, perhaps 30,000 years. And man was not young then. We must open one more chapter in the thrilling story of the ascent of man, the Metal Ages, which are in a sense still continuing. Metals began to be used in the late polished stone (Neolithic) times, for there were always overlappings. Copper came first, bronze second, and iron last. The working of copper in the East has been traced back to the 4th millennium B.C., and there was also a very ancient Copper Age in the New World. It need hardly be said that where copper is scarce, as in Britain, we cannot expect to find much trace of a Copper Age. The ores of different metals seem to have been smelted together in an experimental way by many prehistoric metallurgists, and bronze was the alloy that rewarded the combination of tin with copper. There is evidence of a more or less definite Bronze Age in Egypt and Babylonia, Greece and Europe. It is not clear why iron should not have been the earliest metal to be used by man, but the Iron Age dates from about the middle of the 2nd millennium B.C. From Egypt the usage spread through the Mediterranean region to North Europe, or it may have been that discoveries made in Central Europe, so rich in iron mines, saturated southwards, following, for instance, the route of the amber trade from the Baltic. Compared with stone, the metals afforded much greater possibilities of implements, instruments, and weapons, and their discovery and usage had undoubtedly great influence on the ascent of man, occasionally, however, on his descent. Retrospect. Looking backwards, we discern the following stages. 1. The setting apart of a primate stock, marked off from other mammals by a tendency to big brains, a free hand, gregariousness, and good-humored talkativeness. 2. The divergence of marmosets and New World monkeys and Old World monkeys, leaving a stock, an anthropoid stock, common to the present day and extinct apes, and to mankind. 3. From this common stock the anthropoid apes diverged, far from ignoble creatures, and a humanoid stock was set apart. 4. From the latter, we follow Sir Arthur Keith and other authorities, there arose what may be called, without disparagement, tentative or experimental men, indicated by Pithecanthropus the erect, the Heidelberg man, the Neanderthalers, and, best of all, the early men of the Sussex Weald, hinted at by the Piltdown skull. It matters little whether particular items are corroborated or disproved, e.g., whether the Heidelberg man came before or after the Neanderthalers, the general trend of evolution remains clear. 5. In any case, the result was the evolution of Homo sapiens, the man we are, a quite different fellow from the Neanderthaler. 6. Then arose various stocks of primitive men, proving everything and holding fast to that which is good. These were the Paleolithic peoples, with rude stone implements, a strong, vigorous race, but probably, in most cases, supplanted by fresh experiments. These may have arisen as shoots from the growing point of the old race, or as a fresh offshoot from more generalized members at a lower level. This is the eternal possible victory alike of aristocracy and democracy. 7. Paleolithic men were involved in the succession of 4 great ice ages, or glaciations, and it may be that the human race owes much to the alternation of hard times and easy times, glacial and interglacial. When the ice fields cleared off, Neolithic man had his innings. 8. And we have closed the story, in the meantime, with the Metal Ages. It seems not unfitting that we should at this point sound another note, that of the man of feeling. It is clear in William James's words, "Bone of our bone, and flesh of our flesh, are these half-brutish prehistoric brothers. Girdled about with the immense darkness of this mysterious universe, even as we are, they were born and died, suffered and struggled. Given over to fearful crime and passion, plunged in the blackest ignorance, preyed upon by hideous and grotesque delusions, yet steadfastly serving the profoundest of ideals in their fixed faith that existence in any form is better than non-existence, they ever rescued triumphantly from the jaws of ever-imminent destruction the torch of life, which, thanks to them, now lights the world for us." Races of mankind. Given a variable stock spreading over diverse territory, we expect to find it splitting up into varieties which may become steadied into races or incipient species. Thus we have races of hive bees, Italians, Punics, and so forth, and thus there arose races of men. Certain types suited certain areas, and periods of inbreeding tended to make the distinctive peculiarities of each incipient race well defined and stable. When the original peculiarities, say, of Negro and Mongol, Australian and Caucasian, arose as brusque variations or mutations, then they would have great staying power from generation to generation. They would not be readily swamped by intercrossing or averaged off. Peculiarities and changes of climate and surroundings, not to speak of other change-producing factors, would provoke new departures from age to age, and so fresh racial ventures were made. Moreover, the occurrence of outbreeding when 2 races met, in peace or in war, would certainly serve to induce fresh starts. Very important in the evolution of human races must have been the alternating occurrence of periods of inbreeding, endogamy, tending to stability and sameness, and periods of outbreeding, exogamy, tending to changefulness and diversity. Thus we may distinguish several more or less clearly defined primitive races of mankind, notably the African, the Australian, the Mongolian, and the Caucasian. The woolly-haired African race includes the Negroes and the very primitive Bushmen. The wavy to curly-haired Australian race includes the jungle tribes of the Deccan, the Vedda of Ceylon, the jungle folk or Semang, and the natives of unsettled parts of Australia, all sometimes slumped together as pre-Dravidians. The straight-haired Mongols include those of Tibet, Indochina, China, and Formosa, those of many oceanic islands, and of the north from Japan to Lapland. The Caucasians include Mediterraneans, Semites, Nordics, Afghans, Alpines, and many more. There are very few corners of knowledge more difficult than that of the races of men, the chief reason being that there has been so much movement and migration in the course of the ages. One physical type has mingled with another, inducing strange amalgams and novelties. If we start with what might be called zoological races, or strains differing, for instance, in their hair, woolly-haired Africans, straight-haired Mongols, curly or wavy-haired pre-Dravidians, and Caucasians, We find these replaced by peoples who are mixtures of various races, brethren by civilization more than by blood. As Professor Flinders Petrie has said, the only meaning the term race now can have is that of a group of human beings whose type has been unified by their rate of assimilation exceeding the rate of change produced by the infiltration of foreign elements. It is probable, however, that the progress of precise anthropology will make it possible to distinguish the various racial strains that make up any people. For the human sense of race is so strong that it convinces us of reality even when scientific definition is impossible. It was this the British sailor expressed in his answer to the question, "What is a Dago?" "Dagos," he replied, "is anything what isn't our sort of chaps." Steps in human evolution. Real men arose, we believe, by variational uplifts of considerable magnitude which led to big and complex brains and to the power of reasoned discourse. In some other lines of mammalian evolution there were, from time to time, great advances in the size and complexity of the brain, as is clear, for instance, in the case of horses and elephants. The same is true of birds as compared with reptiles, and everyone recognizes the high level of excellence that has been attained by their vocal powers. How these great cerebral advances came about we do not know, but it has been one of the main trends of animal evolution to improve the nervous system. Two suggestions may be made. First, the prolongation of the period of antenatal life, in intimate physiological partnership with the mother, may have made it practicable to start the higher mammal with a much better brain than in the lower orders, like insectivores and rodents, and still more marsupials, where the period before birth, gestation, is short. Second, we know that the individual development of the brain is profoundly influenced by the internal secretions of certain ductless glands, notably the thyroid. When this organ is not functioning properly, the child's brain development is arrested. It may be that increased production of certain hormones, itself of course to be accounted for, may have stimulated brain development in man's remote ancestors. Given variability along the line of better brains, and given a process of discriminate sifting which would consistently offer rewards to alertness and foresight, to kin sympathy and parental care, there seems no great difficulty in imagining how man would evolve. We must not think of an Aristotle or a Newton except as fine results which justify all the groaning and travailing. We must think of average men, of primitive peoples today, and of our forebears long ago. We must remember how much of man's advance is dependent on the external registration of the social heritage, not on the slowly changing natural inheritance. Looking backwards, it is impossible, we think, to fail to recognize progress. There is a ring of truth in the fine description Aeschylus gave of primitive men that, first, beholding they beheld in vain, and hearing, heard not, but, like shapes in dreams, mixed all things wildly down the tedious time, nor knew to build a house against the sun with wicketed sides, nor any woodwork knew, but lived like silly ants, beneath the ground, in hollow caves unsunned. There came to them no steadfast sign of winter, nor of spring flower perfumed, nor of summer full of fruit, but blindly and lawlessly they did all things. Contrast this picture with the position of man today. He has mastered the forces of nature, and is learning to use their resources more and more economically. He has harnessed electricity to his chariot, and he has made the ether carry his messages. He taps supplies of material which seemed for centuries unavailable, having learned, for instance, how to capture and utilize the free nitrogen of the air. With his telegraph and wireless he has annihilated distance, and he has added to his navigable kingdom the depths of the sea and the heights of the air. He has conquered one disease after another, and the young science of heredity is showing him how to control in his domesticated animals and cultivated plants the nature of the generations yet unborn. With all his faults he has his ethical face set in the right direction. The main line of movement is towards the fuller embodiment of the true, the beautiful, and the good in healthy lives which are increasingly a satisfaction in themselves. Factors in human progress. Many, we believe, were the gains that rewarded the arboreal apprenticeship of man's ancestors. Many, likewise, were the results of leaving the trees and coming down to the solid earth, a transition which marked the emergence of more than tentative men. What great steps followed? Some of the greatest were the working out of a spoken language and of external methods of registration, the invention of tools, the discovery of the use of fire, the utilization of iron and other metals, the taming of wild animals such as dog and sheep, horses and cattle, the cultivation of wild plants such as wheat and rice, and the irrigation of fields. All through the ages necessity has been the mother of invention, and curiosity its father, but perhaps we miss the heart of the matter if we forget the importance of some leisure time wherein to observe and think. If our earth had been so clouded that the stars were hidden from men's eyes, the whole history of our race would have been different. For it was through his leisure time observations of the stars that early man discovered the regularity of the year and got his fundamental impressions of the order of nature, on which all his science is founded. If we are to think clearly of the factors of human progress, we must recall the three great biological ideas: the living organism, its environment, and its functioning. For man, these mean: 1. The living creature, the outcome of parents and ancestors, a fresh expression of a bodily and mental inheritance. 2. The surroundings, including climate and soil, the plants and animals these allow. And 3. The activities of all sorts, occupations and habits, all the actions and reactions between man and his milieu. In short, we have to deal with folk, place, work, the famille, lieu, travail of the Laplace school. As to folk, human progress depends on intrinsic racial qualities, notably health and vigor of body, clearness and alertness of mind, and an indispensable sociality. The most powerful factors in the world are clear ideas in the minds of energetic men of good will. The differences in bodily and mental health which mark races, and stocks within a people, just as they mark individuals, are themselves traceable back to germinal variations or mutations, and to the kind of sifting to which the race or stock has been subjected. Easy-going conditions are not only without stimulus to new departures, they are without the sifting which progress demands. As to place, it is plain that different areas differ greatly in their material resources and in the availability of these. Moreover, even when abundant material resources are present, they will not make for much progress unless the climate is such that they can be readily utilized. Indeed, climate has been one of the great factors in civilization, here stimulating and there depressing energy, in one place favoring certain plants and animals important to man, in another place preventing their presence. Moreover, climate has slowly changed from age to age. As to work, the form of a civilization is in some measure dependent on the primary occupations, whether hunting or fishing, farming or shepherding, and on the industries of later ages which have a profound molding effect on the individual at least. We cannot, however, say more than that the factors of human progress have always had these three aspects: folk, place, work, and that if progress is to continue on stable lines it must always recognize the essential correlation of fitter folk in body and mind, improved habits and functions, alike in work and leisure, and bettered surroundings in the widest and deepest sense. End of section 9.
Section 10 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Leon Meyer. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 10. Part 6. Evolution Going On. Evolution, as we have seen in a previous chapter, is another word for race history. It means the ceaseless process of becoming, linking generation to generation of living creatures. The doctrine of evolution states the fact that the present is the child of the past and the parent of the future. It comes to this, that the living plants and animals we know are descended from ancestors on the whole simpler, and these from others likewise simpler, and so on, back and back, till we reach the first living creatures, of which, unfortunately, we know nothing. Evolution is a process of racial change in a definite direction, whereby new forms arise, take root, and flourish, alongside of or in the place of their ancestors, which were in most cases rather simpler in structure and behavior. The rock record, which cannot be wrong, though we may read it wrongly, shows clearly that there was once a time in the history of the earth when the only backboned animals were fishes. Ages passed, and there evolved amphibians, with fingers and toes, scrambling onto dry land. Ages passed, and there evolved reptiles, in bewildering profusion. There were fish lizards and sea serpents, terrestrial dragons and flying dragons, a prolific and varied stock. From the terrestrial dinosaurs, it seems that birds and mammals arose. In succeeding ages, there evolved all the variety of birds and all the variety of mammals, until at last arose the man. The question is whether similar processes of evolution are still going on. We are so keenly aware of rapid changes in mankind, though these concern the social heritage much more than the flesh and blood natural inheritance, that we find no difficulty in the idea that evolution is going on in mankind. We know the contrast between modern man and primitive man, and we are convinced that in the past, at least, progress has been a reality. That degeneration may set in is an awful possibility, involution rather than evolution. But even if going back became for a time the rule, we cannot give up the hope that the race would recover itself and begin afresh to go forward. For although there have been retrogressions in the history of life continued through unthinkably long ages, and although great races, the flying dragons for instance, have become utterly extinct, leaving no successors whatsoever, we feel sure that there has been on the whole a progress towards nobler, more masterful, more emancipated, more intelligent, and better forms of life, a progress toward what mankind at its best has always regarded as best, i.e., affording most enduring satisfaction. So we think of evolution going on in mankind, evolution checkered by involution, but on the whole progressive evolution. Evolutionary prospect for man. It is not likely that man's body will admit of great change, but there is room for some improvement, e.g. in the superfluous length of the food canal and the overcrowding of the teeth. It is likely, however, that there will be constitutional changes, e.g. of prolonged youthfulness, a higher standard of healthfulness, and a greater resistance to disease. It is justifiable to look forward to great improvements in intelligence and in control. The potentialities of the human brain, as it is, are far from being utilized to the full, and new departures of promise are of continual occurrence. What is of great importance is that the new departures or variations which emerge in fine children should be fostered, not nipped in the bud, by the social environment, education included. The evolutionary prospect for man is promising. But it is very important to realize that among plant and animals likewise, evolution is going on. The fountain of change, variability. On an ordinary big clock, we do not readily see that even the minute hand is moving, and if the clock struck only once in 100 years, we can conceive of people arguing whether the hands did really move at all. So it often is with the changes that go on from generation to generation in living creatures. The flux is so slow, like the flowing of a glacier, that some people fail to be convinced of its reality. And it must, of course, be admitted that some kinds of living creatures, like the lampshell ligula or the pearly nautilus, hardly change from age to age, whereas others, like some of the birds and butterflies, are always giving rise to something new. The evening primrose among plants, and the fruit fly, Drosophila, among animals, are well-known examples of organisms which are at present in a sporting or mutating mood. Certain dark varieties of moth, e.g. of the peppered moth, are taking the place of the paler type in some parts of England, and the same is true of some dark forms of sugar bird in the West Indian islands. Very important is the piece of statistics worked out by Professor R.C. Punnett, that, quote, if a population contains 0.001% of a new variety, and if that variety has even a 5% selection advantage over the original form, the latter will almost completely disappear in less than 100 generations. This sort of thing has been going on all over the world for untold ages, and the face of animate nature has consequently changed. We are impressed by striking novelties that crop up: a clever dwarf, a musical genius, a calculating boy, a cock with a 10-foot tail, a wonder horse with a mane reaching to the ground, a tailless cat, a white blackbird, a copper beech, a greater celandine with much cut-up leaves. But this sort of mutation is common, and smaller, less brusque variations are commoner still. They form the raw materials of possible evolution. We are actually standing before an apparently inexhaustible fountain of change. This is evolution going on. The sporting jellyfish. It is of interest to consider a common animal like the jellyfish Aurelia. It is admirably suited for a leisurely life in the open sea, where it swims about by contracting its saucer-shaped body, thus driving water out from its concavity. By means of millions of stinging cells on its 4 frilled lips and on its marginal tentacles, it is able to paralyze and lasso minute crustaceans and the like, which it then wafts into its mouth. It has a very eventful life history, for it has in its early youth to pass through a fixed stage, fastened to rock or seaweed. But it is a successful animal, well suited for its habitat, and practically cosmopolitan in its distribution. It is certainly an old established creature. Yet it is very variable in color and in size, and even in internal structure. Very often it is the size of a saucer or a soup plate, but giants over 2 feet in diameter are well known. Much more important, however, than variation in color and size are the inborn changes in structure. Normally a jellyfish has its parts in 4 or multiples of 4. Thus it has 4 frilled lips, 4 tufts of digestive filaments in its stomach, and 4 brightly colored reproductive organs. It has 8 sense organs round the margin of its disc, 8 branched and 8 unbranched radial canals, running from the central stomach to a canal round the circumference. The point of giving these details is just this, that every now and then we find a jellyfish with its parts in 6s, 5s, or 3s, and with a multitude of minor idiosyncrasies. Even in the well-established jellyfish there is a fountain of change. 1. Evolution of plants. It is instructive to look at the various kinds of cabbages, such as cauliflower and Brussels sprouts, kale and curly greens, and remember that they are all scions of the not very promising wild cabbage found on our shores. And are not all the aristocrat apple trees of our orchards descended from the plebeian crab apple of the roadside? We know far too little about the precise origin of our cultivated plants, but there is no doubt that after man got a hold of them, he took advantage of their variability to establish race after race, say of rose and chrysanthemum, of potato and cereal. The evolution of cultivated plants is continuing before our eyes, and the creations of Mr. Luther Burbank, such as the stoneless plum and the primus berry, the spineless cactus and the Shasta daisy, are merely striking instances of what is always going on. There is reason to believe that the domestic dog has risen 3 times, from 3 distinct ancestors, a wolf, a jackal, and a coyote. So a multiple pedigree must be allowed for in the case of the dog, and the same is true in regard to some other domesticated animals. But the big fact is the great variety of breeds that man has been able to fix, after he once got started with a domesticated type. There are over 200 well-marked breeds of domestic pigeons, and there is very strong evidence that all are descended from the wild rock dove, just as the numerous kinds of poultry are descended from the jungle fowl of some parts of India and the Malay Islands. Even more familiar is the way in which man has, so to speak, unpacked the complex fur of the wild rabbit, and established all the numerous color varieties which we see among domestic rabbits. And apart from color varieties, there are long-haired Angoras, and quaint lop-eared forms, and many more besides. All this points to evolution going on. The romance of the wheat. It is well known that Neolithic man grew wheat, and some authorities have put the date of the first wheat harvest at between 15,000 and 10,000 years ago. The ancient civilizations of Babylonia, Egypt, Crete, Greece, and Rome were largely based on wheat, and it is highly probable that the first great wheat fields were in the fertile land between the Tigris and the Euphrates. The oldest Egyptian tombs that contain wheat, which, by the way, never germinates after its millennia of rest, belong to the first dynasty and are about 6,000 years old. But there must have been a long history of wheat before that. Now, it is a very interesting fact that the almost certain ancestor of the cultivated wheat is at present living on the arid and rocky slopes of Mount Hermon. It is called Triticum hermonis, and it is varying notably today, as it did long ago when it gave rise to the emmer, which was cultivated in the Neolithic age and is the ancestor of all our ordinary wheats. We must think of Neolithic man noticing the big seeds of this Hermon grass, gathering some of its heads, breaking the brittle spikelet-bearing axis in his fingers, knocking off the rough awns, or bruising the spikelets in his hands, till the glooms or chaff separated off and could be blown away, chewing a mouthful of the seeds, and resolving to sow and sow again. That was the beginning of a long story, in the course of which man took advantage of the numerous variations that cropped up in this sporting stock and established one successful race after another on his fields. Virgil refers in the Georgics to the gathering of the largest and fullest ears of wheat in order to get good seed for another sowing, but it was not till the first quarter of the 19th century that the great step was taken, by men like Patrick Sheriff of Haddington, of deliberately selecting individual ears of great excellence and segregating their progeny from mingling with mediocre stock. This is the method which has been followed with remarkable success in modern times. One of the factors that assisted the Allies in overcoming the food crisis in the darkest period of the war was the virtue of Marquis wheat, a very prolific, early ripening, hard red spring wheat with excellent milling and baking qualities. It is now the dominant spring wheat in Canada and the United States, and it has enormously increased the real wealth of the world in the last 10 years, 1921. Now, our point is simply that this Marquis wheat is a fine example of evolution going on. In 1917, upwards of 250 million bushels of this wheat were raised in North America, and in 1918, upwards of 300 million bushels. Yet the whole originated from a single grain planted in an experimental plot at Ottawa by Dr. Charles E. Saunders so recently as the spring of 1903. We must not dwell too long on this particular instance of evolution, though it has meant much to our race. We wish, however, following Professor Buller's Essays on Wheat, 1919, to explain the method by which this good seed was discovered. From one we may learn all. The parent of Marquis wheat on the male side was the Mid-Europe Red Fife, a first-class cereal. The parent on the female side was less promising, a rather nondescript, not purebred wheat, called Red Calcutta, which was imported from India into Canada about 30 years ago. The father was part of a cargo that came from the Baltic to Glasgow, and was happily included in a sample sent on to David Fife in Ontario about 1842. From one kernel of this sample, David Fife started his stock of Red Fife, which was crossed by Dr. Saunders with Hard Red Calcutta. The result of this cross was a medley of types, nearly 100 varieties altogether, and it was in scrutinizing these that Dr. Saunders hit upon Marquis. He worked steadily through the material, studying head after head of what resulted from sowing, and selecting out those that gave most promise. Each of the heads selected was propagated, most of the results were rejected. The elect were sifted again and yet again, and finally Marquis wheat emerged, rich in constructive possibilities, probably the most valuable food plant in the world. It is like a romance to read that the first crop of the wheat that was destined within a dozen years to overtax the mightiest elevators in the land was stored away in the winter of 1904-5 in a paper packet no larger than an envelope. Thus, from the wild wheat of Mount Hermon there evolved one of the most important food plants of the world. This surely is evolution going on. 2. Changes in the animal life of a country. Nothing gives us a more convincing impression of evolution in being than a succession of pictures of the animal life of a country in different ages. Dr. James Ritchie, a naturalist of distinction, has written a masterly book, The Influence of Man on Animal Life in Scotland (1920), in which we get this succession of pictures. Within itself, he says, a fauna is in a constant state of uneasy restlessness, an assemblage of creatures which in its parts ebbs and flows as one local influence or another plays upon it. There are temporary and local changes, endless disturbances and readjustments of the balance of nature. One year there is a plague of field voles, perhaps next year grouse disease is rife. In one place there is huge increase of starlings, in another place of rabbits. Here cockchafer are in the ascendant, and there the moles are spoiling the pasture. But while the parts fluctuate, the fauna as a whole follows a path of its own. As well as internal tides, which swing to and fro about an average level, there is a drift which carries the fauna bodily along an irretraceable course." Unquote. This is partly due to considerable changes of climate, for climate calls the tune to which living creatures dance. But it is also due to new departures among the animals themselves. We need not go back to the extinct animals and lost faunas of past ages, for Britain has plenty of relics of these, which illustrate the reality of the faunal drift, but it may be very useful, in illustration of evolution in being, to notice what has happened in Scotland since the end of the Great Ice Age. Some 9,000 years ago or more, certain long-headed, square-jawed, short-limbed, but agile hunters and fishermen, whom we call Neolithic man, established themselves in Scotland. What was the state of the country then? It was a country of swamps, low forests of birch, alder, and willow, fertile meadows, and snow-capped mountains. Its estuaries penetrated further inland than they do now, and the sea stood at the level of the 50-foot beach. On its plains and in its forests roamed many creatures which are strange to the fauna of today: the elk and the reindeer, wild cattle, the wild boar, and perhaps wild horses, a fauna of large animals which paid toll to the European lynx, the brown bear, and the wolf. In all likelihood, the marshes resounded to the boom of the bittern, and the plains to the breeding calls of the crane and the great bustard. Such is Dr. Ritchie's initial picture. Now what happened in this kingdom of Caledonia which Neolithic man had found? He began to introduce domesticated animals, and that meant a thinning of the ranks of predaceous creatures. Safety first was the dangerous motto, in obedience to which man exterminated the lynx, the brown bear, and the wolf. Other creatures, such as the great auk, were destroyed for food, and others, like the marten, for their furs. Small pests were destroyed to protect the beginnings of agriculture. Larger animals like the boar were hunted out of existence. Others, like the pearl-bearing river mussels, yielded to subtler demands. No doubt there was protection also, protection for sport, for utility, for aesthetic reasons, and because of humane sentiments. Even wholesome superstitions have safeguarded the robin redbreast and the wren. There were introductions too: the rabbit for utility, the pheasant for sport, and the peacock for amenity. And every introduction, every protection, every killing out had its far-reaching consequences. But if we are to picture the evolution going on, we must think also of man's indirect interference with animal life. He destroyed the forests, he cultivated the wild, he made bridges, he allowed aliens, like rats and cockroaches, to get in unawares. Of course, he often did good, as when he drained swamps and got rid of the mosquitoes which once made malaria rife in Scotland. What has been the net result? Not, as one might think for a moment, a reduction in the number of different kinds of animals. 14 or so species of birds and beasts have been banished from Scotland since man interfered. But as far as numbers go, they have been more than replaced by deliberate introductions like fallow deer, rabbit, squirrel, and pheasant, and by accidental introductions like rats and cockroaches. But the change is rather in quality than in quantity. The smaller have taken the place of the larger, rather paltry pygmies of noble giants. Thus we get a vivid idea that evolution, especially when man interferes, is not necessarily progressive. That depends on the nature of the sieves with which the living materials are sifted. As Dr. Ritchie well says, the standard of the wild fauna as regards size has fallen and is falling, and it is not in size only that there is loss, there is a deterioration of quality. Quote, "For how can the increase of rabbits and sparrows and earthworms and caterpillars, and the additions of millions of rats and cockroaches and crickets and bugs, ever take the place of those fine creatures round the memories of which the glamour of Scotland's past still plays? The reindeer and the elk, the wolf, the brown bear, the lynx and the beaver, the bustard, the crane, the bumbling bittern, and many another, lost or disappearing." Unquote. Thus we see again that evolution is going on. 3. The Adventurers. All through the millions of years, during which animals have tenanted the earth and the waters under the earth, there has been a search for new kingdoms to conquer, for new corners in which to make a home. And this still goes on. It has been and is one of the methods of evolution to fill every niche of opportunity. There is a spider that lives inside a pitcher plant, catching some of the inquisitive insects which slip down the treacherous internal surface of the trap. There is another that makes its home in crevices among the rocks on the shore of the Mediterranean, or even in empty tubular shells, keeping the water out, more or less successfully, by spinning threads of silk across the entrance to its retreat. The beautiful brine shrimp, Artemia salina, that used to occur in British salterns, has found a home in the dense waters of the Great Salt Lake of Utah. Several kinds of earthworms have been found up trees, and there is a fish, Arges, that climbs on the stones of steep mountain torrents of the Andes. The intrepid explorers of the Scotia voyage found quite a number of Arctic terns spending our winter within the summer of the Antarctic Circle, which means girdling the globe from pole to pole. And every now and then there are incursions of rare birds, like Pallas's sand grouse, into Britain, just as if they were prospecting in search of a promised land. Twice or thrice the distinctively North American killdeer plover has been found in Britain, having somehow or other got across the Atlantic. We miss part of the meaning of evolution if we do not catch this note of insurgence and adventure, which some animal or other never ceases to sound, though many establish themselves in a security not easily disturbed, and though a small minority give up the struggle against the stream and are content to acquiesce, as parasites or rottenness eaters, in a drifting life of ease. More important than very peculiar cases is the broad fact that over and over again, in different groups of animals, there have been attempts to master different kinds of haunts, such as the underground world, the trees, the fresh waters, and the air. There are burrowing amphibians, burrowing reptiles, burrowing birds, and burrowing mammals. There are tree toads, tree snakes, tree lizards, tree kangaroos, tree sloths, tree shrews, tree mice, tree porcupines, and so on. Enough of a list to show, without mentioning birds, how many different kinds of animals have entered upon an arboreal apprenticeship, an apprenticeship often with far-reaching consequences. What the freeing of the hand from being an organ of terrestrial support has meant in the evolution of monkeys is a question that gives a spur to our imagination. The case of the robber crab. On some of the coral islands of the Indian and Pacific Oceans there lives a land crab, Birgus, which has learned to breathe on land. It breathes dry air by means of curious blood-containing tufts in the upper part of its gill cavity, and it also has rudimentary gills. It is often about a foot long, and it has very heavy great claws, especially on the left-hand side. With this great claw it hammers on the eye-hole of a coconut, from which it has torn off the fibrous husk. It hammers until a hole is made by which it can get at the pulp. Part of the shell is sometimes used as a protection for the soft abdomen, for the robber crab, as it is called, is an offshoot from the hermit crab stock. Every year this quaint explorer, which may go far up the hills and climb the cocoa palms, has to go back to the sea to spawn. The young ones are hatched in the same state as in our common shore crab. That is to say, they are free-swimming larvae which pass through an open water period before they settle down on the shore, and eventually creep up onto dry land. Just as open water turtles lay their eggs on sandy shores, going back to their old terrestrial haunt, so the robber crab, which has almost conquered the dry land, has to return to the seashore to breed. There is a peculiar interest in the association of the robber crab with the cocoa palm, for that tree is not a native of these coral islands, but has been introduced, perhaps from Mexico, by the Polynesian mariners before the discovery of America by Columbus. So the learning to deal with coconuts is a recent achievement, and we are face to face with a very good example of evolution going on. The story of the salmon. In late autumn or in winter, the salmon spawn in the rivers. The female makes a shallow trough in the gravel by moving her tail from side to side, and therein lays many eggs. The male, who is in attendance, fertilizes these with the milt, and then the female covers them deeply with gravel. This process is repeated over and over again for a week or more, till all the eggs are shed. For 3 to 4 months the eggs develop, and eventually there emerge the larvae, or alevins, which lurk among the pebbles. They cannot swim much, for they are encumbered by a big legacy of yolk. In a few weeks, perhaps 8, the protruding bag of yolk has disappeared, and the fry, about an inch long, begin to move about more actively and to fend for themselves. By the end of the year they have grown to be rather trout-like parr, about 4 inches long. In 2 years these are double that length. Usually in the 2nd year, but it may be earlier or later, the parr become silvery smolts, which go out to sea, usually about the month of May. They feed on young herring and the like, and grow large and strong. When they are about 3½ years old, they come up the rivers as grilse, and may spawn. Or they may pass through the whole grilse stage in the sea, and come up the rivers with all the characters of the full-grown fish. In many cases the salmon spawn only once, and some, they are called celts after spawning, are so much exhausted by starting a new generation that they die or fall victim to otters and other enemies. In the case of the salmon of the North Pacific, in the genus Oncorhynchus, Salmo, all the individuals die after spawning, none being able to return to the sea. It must be remembered that full-grown salmon do not as a rule feed in fresh waters, though they may be unable to resist snapping at the angler's strange creations. A very interesting fact is that the salmon keeps, as it were, a diary of its movements, which vary a great deal in different rivers. This diary is written in the scales, and a careful reading of the concentric lines on the scales shows the age of the fish, and when it went out to sea, and whether it has spawned or not, and more besides. Interpretation of the salmon story. When an animal frequents 2 different haunts, in one of which it breeds, it is very often safe to say that the breeding place represents the original home. The flounder is quite comfortable far up the rivers, but it has to go to the shore waters to spawn, and there is no doubt that the flounder is a marine fish which has recently learned to colonize the fresh waters. Its relatives, like plaice and sole, are strictly marine. But it is impossible to make a dogma of the rule that the breeding place corresponds to the original home. Thus, some kinds of bass, which belong to the marine family of sea perches, live in the sea or in estuaries, while 2 have become permanent residents in fresh water. Or again, the members of the herring family are very distinctively marine, but the shad, which belong to this family, spawn in rivers, and may spend their lives there. So there are 2 different ways of interpreting the life history of the salmon. Some authorities regard the salmon as a marine fish, which is establishing itself in fresh water. But others read the story the other way, and regard the salmon as a member of the freshwater race that is taken to the sea for feeding purposes. In regard to trout, we know that the ranks of those in rivers and lakes are continually being reinforced by migrants from the sea, and that some trout go down to the sea while others remain in the fresh water. We know also in regard to a related fish, the char, that while the great majority of kinds are now permanent residents in cold and deep isolated northern lakes, there are Arctic forms which live in the sea but enter the rivers to spawn. These facts favor the view that the salmon was originally a marine fish. But there are arguments on both sides, and for our present purpose the important fact is that the salmon is conquering two haunts. Its evolution is going on. The Romance of the Eel. Early in summer, at dates varying with the distance of the rivers from the open Atlantic, crowds of young eels, or elvers, come upstream. Sometimes the procession of eel fare includes thousands of individuals, each about the length of our first finger, and as thick as a stout knitting needle. They obey an inborn impulse to swim against the stream, seeking automatically to have both sides of their bodies equally stimulated by the current. So they go straight ahead. The obligation works only during the day, for when the sun goes down behind the hills, the elvers snuggle under stones or beneath the bank and rest till dawn. In the course of time they reach the quiet upper reaches of the river, or go up rivulets and drain pipes to the isolated ponds. Their impulse to go on must be very imperious, for they may wriggle up the wet moss by the side of a waterfall, or even make a short excursion in a damp meadow. In the quiet flowing stretches of the river, or in the ponds, they feed and grow for years and years. They account for a good many young fishes. Eventually, after 5 or 6 years in the case of the males, 6 to 8 years in the case of the females, the well-grown fishes, perhaps 1.5 to 2 feet long, are seized by a novel restlessness. They are beginning to be maturer. They put on a silvery jacket, and become large of eye, and they return to the sea. In getting away from the pond, it may be necessary to wriggle through the damp meadow grass before reaching the river. They travel by night and rather excitedly. The Arctic Ocean is too cold for them, and the North Sea too shallow. They must go far out to sea, to where the old margin of the once larger continent of Europe slopes down to the great abysses, from the Hebrides southwards. Eels seem to spawn in the deep dark water, but the just liberated eggs have not yet been found. The young fry rises to near the surface and becomes a knife-blade-like larva, transparent all but its eye. It lives for many months in this state, growing to be about 3 inches long, rising and sinking in the water, and swimming gently. These open-sea young eels are known as leptocephali, a name given to them before their real nature was proved. They gradually become shorter, and the shape changes from knife-blade-like to cylindrical. During this change they fast, and the weight of their delicate body decreases. They turn into glass eels, about 2.5 inches long, like a knitting needle in girth. They begin to move towards the distant shores and rivers, and they may be 1.5 years old before they reach their destination and go upstream as elvers. Those that ascend the rivers of the eastern Baltic must have journeyed 3,000 miles. It is certain that no eel ever matures or spawns in fresh water. It is practically certain that all the young eels ascending the rivers of North Europe have come in from the Atlantic, some of them perhaps from the Azores, or further out still. It is interesting to inquire how the young eels circumvent the falls of the Rhine and get into Lake Constance, or how their kindred on the other side of the Atlantic overcome the obstacle of Niagara. But it is more important to lay emphasis on the variety of habitats which this fish is trying: the deep waters, the open sea, the shore, the river, the pond, and even, it may be, a little taste of solid earth. It seems highly probable that the common eel is a deep-water marine fish which has learned to colonize the fresh waters. It has been adventurous and it has succeeded. The only shadow on the story of achievement is that there seems to be no return from the spawning. There is little doubt that death is the nemesis of their reproduction. In any case, no adult eel ever comes back from the deep sea. We are reminded of Goethe's hard saying, "Death is nature's expert advice to get plenty of life." 4. Forming new habits. There is a well-known mudfish of Australia, Neoceratodus by name, which has turned its swim bladder into a lung, and comes to the surface to spout. It expels vitiated air with considerable force and takes fresh gulps. At the same time, like an ordinary fish, it has gills, which allow the usual interchange of gases between the blood and the water. Now this Australian mudfish, or double breather, Dipnoan, which may be a long way over a yard in length, is a direct and little changed descendant of an ancient extinct fish, Ceratodus, which lived in Mesozoic times, as far back as the Jurassic, which probably means over 5 millions of years ago. The Queensland mudfish is in antiquity, and there has not been much change in its lineage for millions of years. We might take it as an illustration of the inertia of evolution. And yet, though its structure has changed but little, the fish probably illustrates evolution in process, for it is a fish that is learning to breathe dry air. It cannot leave the water, but it can live comfortably in pools, which are foul with decomposing animal and vegetable matter. In partially dried up and foul water holes, full of dead fishes or various kinds, Neoceratodus has been found vigorous and lively. Unless we take the view, which is possible, that the swim bladder of fishes was originally a lung, the mudfishes are learning to breathe dry air. They illustrate evolution agoing. The herring gull is by nature a fish-eater, but of recent years, in some parts of Britain, it has been becoming in the summer months more and more of a vegetarian, scooping out the turnips, devouring potatoes, settling on the sheaves in the harvest field, and gorging itself with grain. Similar experiments, usually less striking, are known in many birds, but the most signal illustration is that of the kea, or Nestor parrot, of New Zealand, which has taken to lighting on the loins of the sheep, tearing away the fleece, cutting at the skin, and gouging out fat. Now the parrot belongs to a vegetarian or frugivorous stock, and this change of diet, in the relatively short time since sheep ranches were established in New Zealand, is very striking. Here, since we know the dates, we may speak of evolution going on under our eyes. It must be remembered that variations in habit may give an animal a new opportunity to test variations in structure, which arise mysteriously from within, as expressions of germinal changefulness rather than as imprints from without. For of the transmissibility of the latter there is little secure evidence. Experiments in locomotion. It is very interesting to think of the numerous types of locomotion which animals have discovered, pulling and punting, sculling and rowing, and of the changes that are rung on these 4 main methods. How striking is the case of the frilled lizard, Chlamydosaurus, of Australia, which at the present time is, as it were, experimenting in bipedal progression, always a rather eventful thing to do. It gets up on its hind legs and runs totteringly for a few feet, just like a baby learning to walk. How beautiful is the adventure which has led our dipper, or water ouzel, a bird allied to the wrens, to try walking and flying under water! How admirable is the volplaning of numerous parachutists, flying fish, flying frog, flying dragon, flying phalanger, flying squirrel, and more besides, which take great leaps through the air. For are these not the splendid failures that might have succeeded in starting new modes of flight? Most daring of all, perhaps, are the aerial journeys undertaken by many small spiders. On a breezy morning, especially in the autumn, they mount on gateposts and palings and herbage, and, standing with their head to the wind, pay out 3 or 4 long threads of silk. When the wind tugs at these threads, the spinners let go, and are borne, usually back downwards, on the wings of the wind from one parish to another. It is said that if the wind falls they can unfurl more sail, or furl if it rises. In any case, these wingless creatures make aerial journeys. When tens of thousands of the used threads sink to earth, there is a shower of gossamer. On his Beagle voyage, Darwin observed that vast numbers of small gossamer spiders were borne onto the ship when it was 60 miles distant from the land. New devices. It is impossible, we must admit, to fix dates except in a few cases, relatively recent. But there is a smack of modernity in some striking devices which we can observe in operation today. Thus, no one will dispute the statement that spiders are thoroughly terrestrial animals breathing dry air. But we have the fact of the water spider conquering the underwater world. There are a few spiders about the seashore, and a few that can survive douching with fresh water. But the particular case of the true water spider, Argyroneta natans, stands by itself because the creature, as regards the female at least, has conquered the subaquatic environment. A flattish web is woven, somehow, underneath the water, and pegged down by threads of silk. Along a special vertical line, the mother spider ascends to the surface and descends again, having entangled air in the hairs of her body. She brushes off this air underneath her web, which is thereby buoyed up in a sort of dome. She does this over and over again, never getting wet all the time, until the domed web has become like a diving bell, full of dry air. In this eloquent anticipation of man's rational device, this creature, far from being endowed with reason, lays her eggs and looks after her young. The general significance of the facts is that when competition is keen, a new area of exploitation is a promised land. Thus, spiders have spread over all the earth except the polar areas. But here is a spider with some spirit of adventure, which has endeavored, instead of trekking, to find a new corner near at home. It has tackled a problem surely difficult for a terrestrial animal, the problem of living in great part under water, and it has solved it in a manner at once effective and beautiful. In conclusion, we have given but a few representative illustrations of a great theme. When we consider the changefulness of living creatures, the transformations of cultivated plants and domesticated animals, the gradual alterations in the fauna of a country, the search after new haunts, the forming of new habits, and the discovery of many inventions, are we not convinced that evolution is going on? And why should it stop? End of section 10.
Section 11 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Recording by J.C. Guan. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 11. Part 7. The Dawn of Mind. In the story of evolution, there is no chapter more interesting than the emergence of mind in the animal kingdom. But it is a difficult chapter to read, partly because mind cannot be seen or measured, only inferred from the outward behavior of the creature, and partly because it is almost impossible to avoid reading ourselves into the much simpler animals. Part 1. Two extremes to be avoided. The one extreme is that of uncritical generosity, which credits every animal, like Br'er Rabbit, who by the way was the hare, with human qualities. The other extreme is that of thinking of the animal as if it were an automatic machine, in the working of which there is no place or use for mind. Both these extremes are to be avoided. When Professor Whitman took the eggs of the passenger pigeon, which became extinct not long ago with startling rapidity, and placed them a few inches to one side of the nest, the bird looked a little uneasy, and put her beak under her body, as if to feel for something that was not there. But she did not try to retrieve her eggs, close at hand as they were. In a short time she flew away altogether. This shows that the mind of the pigeon is in some respects very different from the mind of man. On the other hand, when a certain clever dog, carrying a basket of eggs, with the handle in his mouth, came to a stile which had to be negotiated, he laid the basket on the ground, pushed it gently through a low gap to the other side, and then took a running leap over. We dare not talk of this dog as an automatic machine. A caution in regard to instinct. In studying the behavior of animals, which is the only way of getting at their mind, for it is only of our own mind that we have direct knowledge, it is essential to give prominence to the fact that there has been throughout the evolution of living creatures a strong tendency to enregister or engrain capacities of doing things effectively. Thus certain abilities come to be inborn. They are parts of the inheritance, which will express themselves whenever the appropriate trigger is pulled. The newly born child does not require to learn its breathing movements, as it afterwards requires to learn its walking movements. The ability to go through the breathing movements is inborn, ingrained, and registered. In other words, there are hereditary prearrangements of nerve cells and muscle cells which come into activity almost as easily as the beating of the heart. In a minute or two the newborn pigling creeps close to its mother and sucks milk. It has not to learn how to do this, any more than we have to learn to cough or sneeze. Thus animals have many useful ready-made, or almost ready-made, capacities of doing apparently clever things. In simple cases of these inborn prearrangements we speak of reflex actions; in more complicated cases, of instinctive behavior. Now the caution is this, that while these inborn capacities usually work well in natural conditions, they sometimes work badly when the ordinary routine is disturbed. We see this when a pigeon continues sitting for many days on an empty nest, or when it fails to retrieve its eggs only 2 inches away. But it would be a mistake to call the pigeon, because of this, an unutterably stupid bird. We have only to think of the achievements of homing pigeons to know that this cannot be true. We must not judge animals in regard to those kinds of behavior which have been handed over to instinct, and go badly agree when the normal routine is disturbed. In 99 cases out of 100, the enregistered instinctive capacities work well, and the advantage of their becoming stereotyped was to leave the animal more free for adventures at a higher level. Being a slave of instinct may give the animal a security that enables it to discover some new home or new food or new joy. Somewhat in the same way, a man of methodical habits, which he has himself established, may gain leisure to make some new departure of racial profit. When we draw back our finger from something very hot, or shut our eye to avoid a blow from a rebounding branch, we do not will the action; and this is more or less the case, probably, when a young animal sucks its mother for the first time. Some mound birds of Celebes lay their eggs in warm volcanic ash by the shore of the sea, others in a great mass of fermenting vegetation. It is inborn in the newly hatched bird to struggle out as quickly as it can from such a strange nest, else it will suffocate. If it stops struggling too soon, it perishes, for it seems that the trigger of the instinct cannot be pulled twice. Similarly, when the eggs of the turtle, that have been laid in the sand of the shore, hatch out, the young ones make instinctively for the sea. Some of the crocodiles bury their eggs 2 feet or so below the surface, among sand and decaying vegetation, an awkward situation for a birthplace. When the young crocodile is ready to break out of the eggshell, just as a chick does at the end of the 3 weeks of brooding, it utters instinctively a piping cry. On hearing this, the watchful mother digs away the heavy blankets, otherwise the young crocodile would be buried alive at birth. Now there is no warrant for believing that the young mound birds, young crocodiles, and young turtles have an intelligent appreciation of what they do when they are hatched. They act instinctively as to the manner born. But this is not to say that their activity is not backed by endeavor or even suffused with a certain amount of awareness. Of course, it is necessarily difficult for man, which is so much a creature of intelligence, to get even an inkling of the mental side of instinctive behavior. In many of the higher reaches of animal instinct, as in courtship or nest building, in hunting or preparing the food, it looks as if the starting of the routine activity also rang up the higher centers of the brain and put the intelligence on the qui vive, ready to interpose when needed. So the twofold caution is this: 1. We must not depreciate the creature too much, if, in unusual circumstances, it acts in an ineffective way along lines of behavior which are normally handed over to instinct; and 2. We must leave open the possibility that even routine instinctive behavior may be suffused with awareness and backed by endeavor. Part II. A useful law. But how are we to know when to credit the animal with intelligence, and when with something less spontaneous? Above all, how are we to know when the effective action, like opening the mouth the very instant it is touched by food, in the mother's beak, is just a physiological action like coughing or sneezing, and when there is behind it a mind at work? The answer to this question is no doubt that given by Professor Lloyd Morgan, who may be called the founder of comparative psychology, that we must describe the piece of behavior very carefully, just as it occurred, without reading anything into it, and that we must not ascribe it to a higher faculty if it can be satisfactorily accounted for in terms of a lower one. In following this principle, we may be sometimes niggardly, for the behavior may have a mental subtlety that we have missed, but in 9 cases out of 10 our conclusions are likely to be sound. It is the critical, scientific way. Bearing this law in mind, let us take a survey of the emergence of mind among backboned animals. Senses of fishes. Fishes cannot shut their eyes, having no true lids, but the eyes themselves are very well developed, and the vision is acute, especially for moving objects. Except in grizzly fishes, the external opening to the ear has been lost, so that sound waves and coarser vibrations must influence the inner ear, which is well developed, through the surrounding flesh and bones. It seems that the main use of the ear in fishes is in connection with balancing, not with hearing. In many cases, however, the sense of hearing has been demonstrated. Thus fishes will come to the side of a pond to be fed when a bell is rung, or when a whistle is blown by someone not visible from the water. The fact that many fishes pay no attention at all to loud noises does not prove that they are deaf, for an animal may hear a sound and yet remain quite indifferent or irresponsive. This merely means that the sound has no vital interest for the animal. Some fishes, such as bullhead and dogfish, have a true sense of smell, detecting by their nostrils very dilute substances permeating the water from a distance. Others, such as members of the cod family, perceive their food in part at least by the sense of taste, which is susceptible to substances near at hand and present in considerable quantity. The sense of taste may be located on the fins as well as about the mouth. At this low level the senses of smell and taste do not seem to be very readily separated. The chief use of the sensitive line or lateral line, seen on each side of a bony fish, is to make the animal aware of slow vibrations and changes of pressure in the water. The skin responds to pressures, the ear to vibrations of high frequency. The lateral line is between the two in its function. Interesting ways of fishes. The brain of the ordinary bony fish is at a very low level. Thus the cerebral hemispheres, destined to become more and more the seats of intelligence, are poorly developed. In gristly fishes, like skates and sharks, the brain is much more promising. But although the state of the brain does not lead one to expect very much from a bony fish like trout or eel, haddock or herring, illustrations are not wanting of what might be called pretty pieces of behaviour. Let us select a few cases. The stickleback's nest. The three-spined and two-spined sticklebacks live equally well in fresh or salt water. The larger 15-spined stickleback is entirely marine. In all three species the male fish makes a nest, in fresh or brackish water, in fresh or brackish water in the first two cases, in shore pools in the third case. The little species use the leaves and stems of water plants. The larger species use seaweed and zoophyte. The leaves or fronds are entangled together and fastened by glue-like threads, secreted, strange to say, by the kidneys. It is just as if a temporary disease condition had been regularized and turned to good purpose. Going through the nest several times, the male makes a little room in the middle. Partly by coercion and partly by coaxing, he induces a female, first one and then another, to pass through the nest with two doors, depositing eggs during her short sojourn. The females go on their way, and the male mounts guard over the nest. He drives off intruding fishes much bigger than himself. When the young are hatched, the male has for a time much to do, keeping his charges within bounds until they are able to move about with agility. It seems that sticklebacks are short-lived fishes, probably breeding only once, and it is reasonable to suppose that their success as a race depends to some extent on the paternal care. Now, if we could believe that the nesting behaviour had appeared suddenly in its present form, we should be inclined to credit the fish with considerable mental ability. But we are less likely to be so generous if we reflect that the routine has been in all likelihood the outcome of a long racial process of slight improvements and critical testings. The secretion of the glue probably came about as a pathological variation. Its utilization was perhaps discovered by accident. The types that had wit enough to take advantage of this were most successful. The routine became enregistered hereditarily. The stickleback is not so clever as it looks. The mind of a minnow. To find solid ground on which to base an appreciation of the behaviour of fishes, it is necessary to experiment, and we may refer to Miss Gertrude White's interesting work on American minnows and sticklebacks. After the fishes had become quite at home in their artificial surroundings, their lessons began. Cloth packets, one of which contained meat and the other cotton, were suspended at opposite ends of the aquarium. The mud minnows did not show that they perceived either packet, though they swarmed close by them. The sticklebacks were intrigued at once. Those that went towards the packet containing meat darted furiously upon it, and pulled at it with great excitement. those that went towards the cotton packet turned sharply away when they were within about 2 inches off. They then perceived what those at the other end were after, and joined them, a common habit amongst fishes. Although the minnows are not interested in the tiny bags of mystery, they were even more alert than the sticklebacks in perceiving moving objects in or on the water, and there is no doubt that both these shallow water species discover their food largely by sense of sight. The next set of lessons had to do with color associations. The fishes were fed on minced snail, chopped earthworm, fragments of liver, and the like, and the food was given to them from the end of forceps held above the surface of the water, so that the fishes could not be influenced by smell. They had to leap out of the water to take the food from the forceps. Discs of colored cardboard were slipped over the end of the forceps, so that what the fishes saw was a morsel of food in the center of a colored disc. After a week or so of preliminary training, they were so well accustomed to the colored discs that the presentation of one served as a signal for the fishes to dart to the surface and spring out of the water. When baits of paper were substituted for food, the fishes continued to jump at the discs. When, however, a blue disc was persistently used for the paper bait and a red disc for the real food, or vice versa, some of the minnows learned to discriminate infallibly between shadow and substance, both when these were presented alternatively and when they were presented simultaneously. This is not far from the dawn of mind. In the course of a few lessons, both minnows and sticklebacks learned to associate particular colors with food, and other associations were also formed. A kind of lava that a minnow could make nothing of after repeated trials was subsequently ignored. The approach of the experimenter, or anyone else, soon began to serve as a food signal. There can be no doubt that in the ordinary life of fishes there is a process of forming useful associations and suppressing useless responses. Given an inborn repertory of profitable movements that require no training, given the power of forming associations such as those we have illustrated, and given a considerable degree of sensory alertness along certain lines, fishes do not require much more. And in truth they have not got it. Moving with great freedom in 3 dimensions in a medium that supports them and is very uniform and constant, able in most cases to get plenty of food without fatiguing exertions, and to dispense with it for considerable periods if it is scarce, multiplying usually in great abundance so that the huge infantile mortality hardly counts, rarely dying a natural death, but usually coming with their strength unabated to a violent end, fishes hold their own in the struggle for existence without much in the way of mental endowment. Their brain has more to do with motion than with mentality, and they have remained at a low psychical level. Yet, just as we should greatly misjudge our own race if we confined our attention to everyday routine, so in our total, as distinguished from our average, estimate of fishes, we must remember the salmon surmounting the falls, the worry trout eluding the angler's skill, the common mud skipet, Periophthalmus, of many tropical shores, which climbs on the rocks and the roots of the mangrove trees, or actively hunts small shore animals. We must remember the adventurous life history of the eel and the quaint ways in which some fishes, males especially, look after their family. The male seahorse puts the eggs in his breast pocket. The male curtus carries them on the top of his head. The cock-pedal, or lumpsucker, guards them and aerates them in a corner of a shore pool. Part 3. The Mind of Amphibians. Towards the end of the age of the Old Red Sandstone, or Devonian, a great step in evolution was taken, the emergence of amphibians. The earliest representatives had fish-like characters even more marked than those which may be discerned in the tadpoles of our frogs and toads, and there is no doubt that amphibians sprang from a fish stock. But they made great strides, associated in part with their attempts to get out of the water on to dry land. From fossil forms we cannot say much in regard to soft parts, but if we consider the living representatives of the class, we may credit amphibians with such important acquisitions as fingers and toes, a three-chambered heart, true ventral lungs, a drum to the ear, a mobile tongue, and vocal cords. When animals began to be able to grasp an object, and when they began to be able to utter sufficient sounds, two new doors were opened. Apart from insects, whose instrumental music had probably begun before the end of the Devonian age, amphibians were the first animals to have a voice. The primary meaning of this voice was doubtless, as it is today in our frogs, a sex call, but it was the beginning of what was destined to play a very important part in the evolution of the mind. In the course of ages, the significance of the voice broadened out. It became a parental call. It became an infant's cry. Broadening still, it became a very useful means of recognition amongst kindred, especially in the dark and in the intricacies of the forest. Ages passed, and the voice rose in another turn of the evolutionary spiral, to be expressive of particular emotions beyond the immediate circle of sex. Emotions of joy and of fear, of jealousy and of contentment. Finally we judge the animal, perhaps the bird was first, began to give utterance to particular words, indicative not merely of emotions, but of particular things with an emotional halo, such as food, enemy, home. Long afterwards words became, in man, the medium of reasoned discourse. Sentences were made and judgments expressed. But was not the beginning in the croaking of amphibia? Senses of amphibians. Frogs have good eyes, and the toad's eye are jewels. There is evidence of precise vision in the neat way in which a frog catches a fly, flickering out its tongue, which is fixed in front and loose behind. There is also experimental proof that a frog discriminates between red and blue, or between red and white. And an interesting point is that while our skin is sensitive to heat rays but not to light, the skin of the frog answers back to light rays as well. Professor Yerkes experimented with a frog which had to go through a simple labyrinth if it wished to reach a tank of water. At the first alternative between two paths, a red card was placed on the wrong side and a white one on the other. When the frog had learned to take the correct path, marked by the white card, Professor Yerkes changed the cards. The confusion of the frog showed how thoroughly it had learned its lesson. We know very little in regard to sense of smell or taste in amphibians, but the sense of hearing is well developed, more developed than might be inferred from the indifference that frogs show to almost all sounds except the croaking of their kindred and splashes in the water. The toad looks almost sagacious when it is climbing up a bank, and some of the tree frogs are very alert. But there is very little that we dare say about the amphibian mind. We have mentioned that frogs may learn the secret of a simple maze, and toads sometimes make for a particular spawning pond from a considerable distance. But an examination of their brains, occupying a relatively small part of the broad, flat skull, warns us not to expect much intelligence. On the other hand, when we take frogs along a line that is very vital to them, namely, the discrimination of palatable and unpalatable insects, we find by experiment that they are quick to learn and that they remember their lessons for many days. Frogs sometimes deposit their eggs in very unsuitable pools of water, but perhaps that is not quite so stupid as it looks. The egg-laying is a matter that has been, as it were, handed over to instinctive registration. Experiments in parental care. It must be put to the credit of amphibians that they have made many experiments in methods of parental care, as if they were feeling their way to new devices. A common frog lays her clumps of eggs in the cradle of the water, sometimes far over 1,000 together. The toad winds 2 long strings round and between water weeds, and in both cases that is all. There is no parental care, and the prolific multiplication covers the enormous infantile mortality. This is the spawning solution of the problem of securing the continuance of the race. But there is another solution, that of parental care, associated with an economical reduction of the number of eggs. Thus the male of the nurse frog, Alites, not uncommon on the continent, fixes a string of 20 to 50 eggs to the upper part of his hind legs, and retires to his hole, only coming out at night to get some food and to keep up the moisture about the eggs. In 3 weeks, when the tadpoles are ready to come out, he plunges into the pond and is freed from his living burden and his family cares. In the case of the thoroughly aquatic Surinam toad, Pipa, the male helps to press the eggs, perhaps 100 in number, onto the back of the female, where each sinks into a pocket of skin with a little lid. By and by fully formed young toads jump out of the pockets. In the South American tree frogs called Nototrema, there is a pouch on the back of the female, in which the eggs develop, and it is interesting to find that in some species what come out are ordinary tadpoles, while in other species the young emerge as miniatures of their parents. Strangest of all, perhaps, is the case of Darwin's frogs, Rhinoderma of Chile, where the young, about 10 to 15 in number, develop in the male's croaking sacs, which become in consequence enormously distended. Eventually the strange spectacle is seen of miniature frogs jumping out of their father's mouth. Needless to say, we are not citing these methods of parental care as examples of intelligence, but perhaps they correct the impression of amphibians as a rather humdrum race. Whatever be the mental aspect of the facts, there has certainly been some kind of experimenting, and the increase of parental care, so marked in many amphibians, with associated reduction of the number of offsprings, is a finger-post on the path of progress. Part 4. The Reptilian Mind. We speak of the wisdom of the serpent, but it is not very easy to justify the phrase. Among all the multitude of reptiles, snakes, lizards, turtles, and crocodiles, a motley crowd, we cannot see much more than the occasional traces of intelligence. The inner life remains a tiny rill. No doubt many reptiles are very effective, but it is an instinctive rather than an intelligent efficiency. The well-known soft-shell tortoise of the United States swims with powerful strokes, and runs so quickly that it can hardly be overtaken. It hunts vigorously for crayfish and insect larvae in the rivers. It buries itself in the mud when cold weather comes. It may lie on a floating log, ready to slip into the water at a moment's notice. It may bask on a sunny bank, or in the warm shallows. Great wariness is shown in choosing times and places for egg-laying. The mother tramps the earth down upon the buried eggs. all is effective. Similar statements might be made in regard to scores of other reptiles, but what we see is almost wholly of the nature of instinctive routine, and we get little glimpse of more than efficiency and endeavour. In a few cases there is proof of reptiles finding their way back to their homes from a considerable distance, and recognition of persons is indubitable. Gilbert White remarks of his tortoise, whenever the good old lady came in sight who had waited on it for more than 30 years, it always hobbled with awkward alacrity towards its benefactress, while to strangers it was altogether inattentive. Of definite learning there are a few records. Thus Professor Yerkes studied a sluggish turtle of retiring disposition, taking advantage of its strong desire to efface itself. On the path of the darkened nest of damp grass he interposed a simple maze in the form of a partition box. After wandering about constantly for 35 minutes, the turtle found its way through the maze by chance. 2 hours afterwards it reached the nest in 15 minutes, and after another interval of 2 hours it only required 5 minutes. After the third trial the routes became more direct, there was less aimless wandering. The time of the 20th trial was 45 seconds, that of the 30th 40 seconds. In the 30th case the path followed was quite direct, and so it was on the 50th trip, which only required 35 seconds. Of course, the whole thing did not amount to very much, but there was a definite learning, a learning from experience, which has played an important part in the evolution of animal behavior. Comparing reptiles with amphibians, we may recognize an increased masterliness of behavior and a hint of greater plasticity. The records of observers who have made pets of reptiles suggest that the life of feeling or emotion is growing stronger, and so do stories, if they can be accepted, which suggest the beginning of conjugal affection. The error must be guarded against of interpreting in terms of intelligence what is merely the outcome of long-continued structure adaptation. When the limbless lizard called the slow worm is suddenly seized by the tail, it escapes by surrendering the appendage, which breaks across a preformed weak plane. But this is a reflex action, not a reflective one. It is comparable to our sudden withdrawal of our finger from a very hot cinder. The egg-eating African snake, Dasypeltis, gets the egg of a bird into its gullet unbroken, and cuts the shell against downward projecting sharp points of the vertebrae. None of the precious contents is lost, and the broken empties are returned. It is admirable, indeed unsurpassable, but it is not intelligent. Part 5. Minds in Birds. Sight and hearing are highly developed in birds, and the senses, besides pulling the triggers of inborn efficiencies, supply the raw materials for intelligence. There is some truth, though not the whole truth, in the old philosophical dictum, that there is nothing in the intellect which was not previously in the senses. Many people have admired the certainty and alacrity with which gulls pick up a fragment of biscuit from the white wake of a streamer, and the incident is characteristic. In their power of rapidity alerting the focus of the eye, birds are unsurpassed. To the sense of sight in birds, the sense of hearing comes a good second. A twig breaks under our feet, and out sounds the dagger call of the bird we were trying to catch. Many young birds, like partridges, respond when 2 or 3 hours old to the anxious warning note of the parents, and squat motionless on the ground, though other sounds, such as the excited clucking of a foster-mother hen, leave them indifferent. They do not know what they are doing when they squat. They are obeying the living hand of the past which is within them. Their behavior is instinctive. But the present point is the discriminating quality of the sense of hearing, and that is corroborated by the singing of birds. It is emotional art, expressing feeling in the medium of sound. On the part of the females who are supposed to listen, it betokens a cultivated ear. As to the other senses, touch is not highly developed except about the bill, where it reaches a climax in birds like the woodcock, which probe for unseen earthworms in the soft soil. Taste seems to be poorly developed, for most birds bolt their food, but there is sometimes an emphatic rejection of unpalatable things, like toads and caterpillars. Of smell in birds little is known, but it has been proved to be present in certain cases, e.g., in some nocturnal birds of prey. It seems certain that it is by sight, not by smell, that the eagles gather to the carcass. But perhaps there is more smell in birds than they're usually credited with. One would like to experiment with the oil from the preen gland of birds, to see whether the scent of this does not help in the recognition of kin by kin at night, or amid the darkness of the forest. There may be other senses in birds, such as a sense of temperature and a sense of balance, but no success has attended the attempts made to demonstrate a magnetic sense, which has been impatiently postulated by students of bird migration, in order to explain how birds find their way. The big fact is that in birds there are two widely open gateways of knowledge, the sense of sight and the sense of hearing. Instinctive aptitudes. Many a young water bird, such as a coot, swims right away when it is tumbled into water for the first time. So chicks peck without any learning or teaching. Very young ducklings catch small moths that flit by, and young plovers lie low when the danger signal sounds. But birds seem strangely limited as regards many of these instinctive capacities. Limited when compared with the little-brained ants and bees, which have from the first such a rich repertory of ready-made cleverness. The limitation in birds is of great interest, for it means that intelligence is coming to its own, and is going to take up the reins at many corners of the daily round. Professor Lloyd Morgan observed that his chickens incubated in the laboratory had no instinctive awareness of the significance of their mother's cluck when she was brought outside the door. Although thirsty and willing to drink from a moistened finger-tip, they did not instinctively recognize water, even when they walked through a saucerful. Only when they happened to peck their toes as they stood in the water did they appreciate water as the stuff they wanted, and raise their bills up to the sky. Once or twice they actually stuffed their crops with worms of red worsted. Instinctive aptitudes, then, the young birds have, but these are more limited than in ants, bees, and wasps, and the reason is to be found in the fact that the brain is now evolving on the track of what Sir Ray Lankester has called educability. Young birds learn with prodigious rapidity. The emancipation of the mind from the tyranny of hereditary obligations has begun. Young birds make mistakes, like the red worsted mistake, but they do not make the same mistakes often. They are able to profit by experience in a very rapid way. We do not mean that creatures of the little brain type, like ants, bees, and wasps, are unable to profit by experience, or are without intelligence. There are no such hard and fast lines. We mean that in the ordinary life of insects the unregistered instinctive capacities are on the whole sufficient for the occasion, and that intelligent educability is very slightly developed. Nor do we mean that birds are quite emancipated from the tyranny of ingrained instinctive obligations, and can always ring up intelligence in a way that is impossible for the stereotyped bee. The sight of a pigeon brooding on an empty nest, while her eggs lie disregarded only a couple of inches away, is enough to show that along certain lines birds may find it impossible to get free from the trammels of instinct. The particular interest of birds is that they have many instincts, and yet a notable power of learning intelligently. Intelligence cooperating with instinct. Professor Lloyd Morgan was foster parent to two moorhens which grew up in isolation from their kindred. They swam instinctively, but they would not dive, neither in a large bath nor in a current. But it happened one day when one of these moorhens was swimming in a pool on a Yorkshire stream that a puppy came barking down the bank and made an awkward feint towards the young bird. In a moment the moorhen dived, disappeared from view, and soon partially reappeared, his head just peeping above the water beneath the overhanging bank. This was the first time the bird had dived, and the performance was absolutely true to type. There can be little doubt as to the meaning of this observation. The moorhen has an hereditary or instinctive capacity for swimming and diving, but the latter is not so easily called into activity as the former. The particular moorhen in question has enjoyed about 2 months of swimming experience, which probably counted for something, but in the course of that experience nothing had pulled the trigger of the diving capacity. On an eventful day the young moorhen saw and heard the dog. It was emotionally excited. It probably did, to some extent, intelligently appreciate a novel and meaningful situation. Intelligence cooperated with instinct, and the bird dived appropriately. Birds have inborn predispositions to certain effective ways of pecking, scratching, swimming, diving, flying, crouching, lying low, nest building, and so on, but they are marked off from the much more purely instinctive ants and bees by the extent to which individual nurture seems to mingle with the inherited nature. The two together result in the fine product which recalled the bird's behavior. After Lloyd Morgan's chicks had tried a few conspicuous and unpalatable caterpillars, they had no use for any more. They learned in their early days with prodigious rapidity, illustrating the deep difference between the pig-brain type, relatively poor in its endowment of instinctive capacities, but eminently educable, and the little-brain type, say, of ants and bees, richly endowed with instinctive capacities, but very far from being quick or glad to learn. We owe it to Sir Ray Lankester to have made it clear that these two types of brain are, as it were, on different tacks of evolution, and should not be directly pitted against one another. The little brain type makes for a climax in the ant, where instinctive behavior reaches a high degree of perfection. The big brain type reaches its climax in horse and dog, in elephant and monkey. The particular interest that attaches to the behavior of birds is in the combination of a good deal of instinct with a great deal of intelligent learning. This is well illustrated when birds make a nest out of new materials, or in some quite novel situation. It is clearly seen when birds turn to some new kind of food, like the key parrot, which attacks the sheep in New Zealand. Some young woodpeckers are quite clever in opening fir cones to get at the seeds, and this might be hastily referred to as well-defined hereditary capacity. But the facts are that the parents bring their young ones first to the seeds themselves, then partly open cones, and then intact ones. There is an educative process, and so it is in scores of cases. Using their wits. When the Greek eagle lifts the Greek tortoise in its talons, and lets it fall from a height so that the strong carapace is broken and the flesh exposed, it is making intelligent use of an expedient. Whether it discovered the expedient by experimenting, as is possible, or by chance, as is more likely, it uses it intelligently. In the same way, herring gulls lift sea urchins and clams in their bills, and let them fall on the rocks so that the shells are broken. In the same way, rooks deal with freshwater mussels. The thrush anvil. A very instructive case is the behavior of the song thrush when it takes a wood snail in its beak and hammers it against a stone, its so-called anvil. To a young thrush, which she had brought up by hand, Miss Frances Pitt offered some wood snails, but it took no interest in them until one put out its head and began to move about. The bird then pecked at the snail's horns, but was evidently puzzled when the creature retreated within the shelter of the shell. This happened over and over again, the thrush's inquisitive interest increasing day by day. It pecked at the shell and even picked it up by the lip, but no real progress was made till the 6th day, when the thrush seized the snail and beat it on the ground as it would a big worm. On the same day it picked up a shell and knocked it repeatedly against the stone, trying first one snail and then another. After 15 minutes' hard work, the thrush managed to break one, and after that it was all easy. A certain predisposition to beat things on the ground was doubtless present, but the experiment showed that the use of an anvil could be arrived at by an untutored bird. After prolonged trying, it found out how to deal with a difficult situation. It may be said that in more natural conditions this might be picked up by imitation, but while this is quite possible, it is useful to notice that experiments with animals lead us to doubt whether imitation counts for nearly so much as used to be believed. End of section 11. Section 12 of the Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit librivox.org. Recording by J. C. Guan. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 12. Part 7. The Dawn of Mind. Continued. Part 6. The Mind of the Mammal. When we watch a collie at a sheep-driving competition, or an elephant helping the forester, or a horse shunting wagons at a railway siding, we are apt to be too generous to the mammal mind, for in the cases we have just mentioned, part of man's mind has, so to speak, got into the animals. On the other hand, when we study rabbits and guinea pigs, we are apt to be too stingy, for these rodents are under the average of mammals, and those that live in domestication illustrate the stupefying effect of a too sheltered life. The same applies to domesticated sheep contrasted with wild sheep, or even with their own lambs. If we are to form a sound judgment on the intelligence of mammals, we must not attend too much to those that have profited by man's training, nor to those whose mental life has been dulled by domestication. Instinctive aptitudes. What is to be said of the behavior of beavers who gnaw the base of a tree with their chisel-edged teeth till only a narrow core is left, to snap in the first gale, bringing the useful branches down to the ground? What is to be said of the harvest mouse constructing its nest, or of the squirrel making cache after cache of nuts? These and many similar pieces of behavior are fundamentally instinctive, due to inborn predispositions of nerve cells and muscle cells. But in mammals they seem to be often attended by a certain amount of intelligent attention, saving the creature from the tyranny of routine so marked in the ways of ants and bees. Sheer dexterity. Besides instinctive aptitudes, which are exhibited in almost equal perfection by all members of the same species, there are acquired dexterities which depend on individual opportunities. They are also marked by being outside and beyond ordinary routine. Not that any rigorous boundary line can be drawn. We read that at Mithra on the Jumna, doles of food are provided by the piety of pilgrims for the sacred river tortoises, which are so crowded when there is food going that their smooth carapaces form a more or less continuous raft across the river. On that unsteady slippery bridge the langur monkeys, Semnopithecus entellus, venture out and in spite of vicious snaps secure a share of the booty. This picture of the monkeys securing a footing on the moving mass of turtle-backs is almost a diagram of sheer dexterity. It illustrates the spirit of adventure, the will to experiment, which is, we believe, the main motive force in new departures in behavior. Power of association. A bull terrier called Jasper, studied by Professor J.B. Watson, showed great power of associating certain words with certain actions. From a position invisible to the dog, the owner would give certain commands, such as, "Go into the next room and bring me a paper lying on the floor." Jasper did this at once, and a score of similar things. Lord Avebury's dog, Van, was accustomed to go to a box containing a small number of printed cards, and select the card T, or Out, as the occasion suggested. It had established an association between certain black marks on a white background and the gratification of certain desires. It is probable that some of the extraordinary things horses and dogs have been known to do in the way of stamping a certain number of times in supposed indication of an answer to an arithmetical question, in the case of horses, or the name of an object drawn, in the case of dogs, are dependent on clever associations established by the teacher between minute signs and a number of stampings. What is certain is that mammals have in varying degrees a strong power of establishing associations. There is often some delicacy in the association established. Every one knows of cases where a dog, a cat, or a horse will remain quite uninterested, to all appearance, in its owner's movements, until some little detail, such as taking a key from its peg, pulls the trigger. Now the importance of this in the wild life of the fox or the hare, the otter or the squirrel, is obviously that the young animals learn to associate certain sounds in their environment with definite possibilities. They have to learn an alphabet of woodcraft, the letters of which are chiefly sounds and scents. The dancing mouse as a popple. The dancing or waltzing mouse is a Japanese variety with many peculiarities, such as having only one of the three semicircular canals of the ear well developed. It has a strong tendency to waltz round and round in circles without sufficient cause, and to trip sideways towards its dormitory instead of proceeding in the orthodox head-on fashion. But this freak is a very educable creature, as Professor Yerkes has shown. In a careful way he confronted his mouse popple with alternative pathways marked by different degrees of illumination, or by different colors. If the mouse chose compartment A, it found a clear passage direct to its nest. If it chose compartment B, it was punished by a mild electric shock, and it had to take a roundabout road home. Needless to say, the A compartment was sometimes to the right hand, sometimes to the left, else mere position would have been a guide. The experiments showed that the dancing mice learned to discriminate the right path from the wrong, and similar results have been got from other mammals, such as rats and squirrels. There is no proof of learning by ideas, but there is proof of learning by experience, and the same must be true in wild life. Many mammals, such as cats and rats, learn how to manipulate puzzle boxes and how to get at the treasure at the heart of a Hampton Court maze. Some of the puzzle boxes, with a reward of food inside, are quite difficult, for the various bolts and bars have to be dealt with in a particular order, and yet many mammals master the problem. What is plain is that they gradually eliminate useless movements, that they make fewer and fewer mistakes, that they eventually succeed, and that they register the solution within themselves so that it remains with them for a time. It looks a little like the behavior of a man who learns a game of skill without thinking. It is a learning by experience, not by ideas or reflection. Thus, it is very difficult to suppose that a rat or a cat could form any idea or even picture of the Hampton Court maze, which they nevertheless master. Learning tricks. Given sufficient inducement, many of the cleverer mammals will learn to do very sensible things, and no one is wise enough to say that they never understand what they are doing. Yet it is certain that trained animals often exhibit pieces of behavior which are not nearly so clever as they look. The elephant at the Bellevue Gardens in Manchester used to collect pennies from benevolent visitors. When it got a penny in its trunk, it put it in the slot of an automatic machine which delivered up a biscuit. When a visitor gave the elephant a halfpenny, it used to throw it back with disgust. At first sight, this seemed almost wise, and there was no doubt some intelligent appreciation of the situation. But it was largely a matter of habituation, the outcome of careful and prolonged training. The elephant was laboriously taught to put the penny in the slot and to discriminate between the useful pennies and the useless halfpennies. It was not nearly so clever as it looked. Using their wits. In the beautiful zoological park in Edinburgh, the polar bear was wont to sit on a rocky peninsula of a water-filled quarry. The visitors threw in buns, some of which floated on the surface. It was often easy for the polar bear to collect half a dozen by plunging into the pool. But it had discovered a more interesting way. At the edge of the peninsula it scooped the water gently with its huge paw, and made a current which brought the buns ashore. This was a simple piece of behavior, but it has the smack of intelligence, of putting two and two together in a novel way. It suggests the power of making what is called a perceptual inference. On the occasion of a great flood in a meadow, it was observed that a number of mares brought their foals to the top of a knoll, and stood round about them, protecting them against the rising water. A dog has been known to show what was at any rate a plastic appreciation of a varying situation in swimming across a tidal river. It changed its starting point, they say, according to the flow or ebb of the tide. Arctic foxes and some other wild animals show great cleverness in dealing with traps, and the manipulative intelligence of elephants is worthy of all our admiration. Part 7. Why is there not more intelligence? When we allow for dexterity and power of association, when we recognize a certain amount of instinctive capacity, and a capacity for profiting by experience in an intelligent way, we must admit a certain degree of disappointment when we take a survey of the behavior of mammals, especially of those with very fine brains, from which we should naturally expect great things. Why is there not more frequent exhibition of intelligence in the stricter sense? The answer is that most mammals have become in the course of time very well adapted to the ordinary conditions of their life, and tend to leave well alone. They have got their repertory of efficient answers to the ordinary questions of everyday life, and why should they experiment? In the course of the struggle for existence, what has been established is efficiency in normal circumstances, and therefore even the higher animals tend to be no cleverer than is necessary. So, while many mammals are extraordinarily efficient, they tend to be a little dull. Their mental equipment is adequate for the everyday conditions of their life, but it is not on sufficiently generous lines to admit of, let us say, an interest in nature or adventurous experiment. Mammals always tend to play for safety. We hasten, however, to insert here some very interesting saving clauses. Experimentation in play. A glimpse of what mammals are capable of, where it is necessary, may be obtained by watching those that are playful, such as lambs and kids, foals and calves, young foxes and others. For these young creatures let themselves go irresponsibly. They are still unstereotyped. They test what they and their fellows can do. The experimental character of much of animal play is very marked. It is now recognized by biologists that play among animals is the young form of work, and that the playing period, often so conspicuous, is vitally important as an apprenticeship to the serious business of life and as an opportunity for learning the alphabet of nature. But the playing period is much more. It is one of the few opportunities animals have of making experiments without too serious responsibilities. Play is nature's device for allowing elbow room for new departures, behavior variations, which may form part of the raw materials of progress. Play, we repeat, gives us a glimpse of the possibilities of the mammal mind. Other glimpses of intelligence. A squirrel is just as clever as it needs to be, and no more. And of some vanishing mammals, like the beaver, not even this can be said. Humdrum non-plastic efficiency is apt to mean stagnation. Now we have just seen that in the play of young mammals there is an indication of unexhausted possibilities, and we get the same impression when we think of three other facts. A. In those mammals, like dog and horse, which have entered into active cooperative relations with man, we see that the mind of the mammal is capable of much more than the average would lead us to think. When man's sheltering is too complete and the domesticated creature is passive in his grip, the intelligence deteriorates. B. When we study mammals, like the otter, which live a versatile life in very complex and difficult environment, we get an inspiring picture of the play of wits. C. Thirdly, when we pass to monkeys, where the forelimb has become a free hand, where the brain shows a relatively great improvement, where words are much used, we cannot fail to recognize the emergence of something new, a restless inquisitiveness, a desire to investigate the world, an unsatisfied tendency to experiment. We are approaching the dawn of reason. The Mind of Monkeys. Part 8. There is a long gamut between the bushy-tailed, almost squirrel-like marmosets and the big-brained chimpanzee. There is a great variety of attainment at different levels in the simian tribe. Keen senses. To begin at the beginning, it is certain that monkeys have a first-class sensory equipment, especially as regards sight, hearing, and touch. The axes of the two eyes are directed forwards as in man, and a large section of the field of vision is common to both eyes. In other words, monkeys have a more complete stereoscopic vision than the rest of the mammals enjoy. They look more and smell less. They can distinguish different colors, apart from different degrees of brightness in the colored objects. They are quick to discriminate differences in the shapes of things, e.g., boxes similar in size but different in shape, for, if the prize is always put in a box of the same shape, they soon learn, by association, to select the profitable one. They learn to discriminate cards with short words or with signs printed on them, coming down when the yes card is shown, remaining on their perch when the card says no. Bred to a forest life where alertness is life or death quality, they are quick to respond to a sudden movement or to pick out some new feature in their surroundings. And what is true of vision holds also for hearing. Power of manipulation. Another quality which separates monkeys very markedly from the ordinary mammals is their manipulative expertness, the coordination of hand and eye. This great gift follows from the fact that among monkeys the foreleg has been emancipated. It has ceased to be indispensable as an organ of support. It has become a climbing, grasping, lifting, handling organ. The forelimb has become a free hand, and everyone who knows monkeys at all is aware of the zest with which they use their tool. They enjoy pulling things to pieces, a kind of dissection, or screwing the handle off a brush and screwing it on again. Activity for activity's sake. Professor Thorndike hits the nail on the head when he lays stress on the intensity of activity in monkeys, activity both of body and mind. They are pent-up reservoirs of energy, which almost any influence will tap. Watch a cat or a dog, Professor Thorndike says. It does comparatively few things and is content for long periods to do nothing. It will be splendidly active in response to some stimulus, such as food, or a friend, or a fight. But if nothing appeals to its special make-up, which is very utilitarian in its interests, it will do nothing. Quote, "Watch a monkey, and you cannot enumerate the things he does, cannot discover the stimuli to which he reacts, cannot conceive the raison d'être of his pursuits. Everything appeals to him. He likes to be active for the sake of activity." End quote. This applies to mental activity as well, and the quality is one of extraordinary interest, for it shows the experimenting mood at a higher turn of the spiral than in any other creature, save man. It points forward to the scientific spirit. We cannot indeed believe in the sudden beginning of any quality, and we recall the experimenting of playing mammals, such as kids and kittens, or of inquisitive adults like Kipling's mongoose, Rikki-Tikki-Tavi, which made it his business in life to find out about things. But in monkeys the habit of restless experimenting rises to a higher pitch. They appear to be curious about the world. The psychologist whom we have quoted tells of a monkey which happened to hit a projecting wire so as to make it vibrate. He went on repeating the performance hundreds of times during the next few days. Of course, he got nothing out of it save fun, but it was grist to his mental mill. Quote, "The fact of mental life is to monkeys its own reward." End quote. The monkey's brain is, quote, "tender all over, functioning throughout, set off in action by anything and everything." End quote. Sheer quickness. Correlated with the quality of restless inquisitiveness and delight in activity for its own sake, there is the quality of quickness. We mean not merely the locomotor agility that marks most monkeys, but the quickness of perception and plan. It is the sort of quality that life among the branches will engender, where it is so often a case of neck or nothing. It is the quality which we describe as being on the spot, though the phrase has slipped from its original moorings. Speaking of his bonnet monkeys, an Indian macaque, second cousin to the kind that lives on the rock of Gibraltar, Professor S.J. Holmes writes, "For keenness of perception, rapidity of action, facility in forming good practical judgment about ways and means of escaping pursuit and of attaining various other ends, Lizzie had a few rivals in the animal world. Her perceptions and decisions were so much more rapid than my own that she would frequently transfer her attention, decide upon a line of action, and carry it into effect before I was aware of what she was about. Until I came to guard against her nimble and unexpected manoeuvres, she succeeded in getting possession of many apples and peanuts which I had not intended to give her, except upon the successful performance of some task." Quick to learn. Quite fundamental to any understanding of animal behaviour is the distinction so clearly drawn by Sir Ray Lankester between the little brain type, rich in inborn or instinctive capacities, but relatively slow to learn, and the big brain type, with a relatively poor endowment of specialized instincts, but with great educability. The little brain type finds its own climax in ants and bees; the big brain type in horses and dogs, elephants and monkeys. And of all animals, monkeys are the quickest to learn, if we use the word learn to mean the formation of useful associations between this and that, between a given sense presentation and a particular piece of behaviour. The case of Sally. Some of us remember Sally, the chimpanzee at the zoo, with which Dr. Romanes used to experiment. She was taught to give her teacher the number of straws he asked for, and she soon learned to do so up to 5. If she had handed a number not asked for, her offer was refused. If she gave the proper number, she got a piece of fruit. If she was asked for 5 straws, she picked them up individually and placed them in her mouth, and when she had gathered 5, she presented them together in her hand. Attempts to teach her to give 6 to 10 straws were not very successful. For Sally, above 6 meant many, and besides, her limits of patience were probably less than her range of computation. This was hinted at by the highly interesting circumstances that, when dealing with numbers above 5, she very frequently doubled over a straw so as to make it present 2 ends, and thus appear as 2 straws. The doubling of the straw looked like an intelligent device to save time, and it was persistently resorted to in spite of the fact that her teacher always refused to accept a double straw as equivalent to 2 straws. Here we get a glimpse of something beyond the mere association of a sound 5 and that number of straws. The case of Lizzie. The front of the cage in which Professor Holmes kept Lizzie was made of vertical bars, which allowed her to reach out with her arm. On a board with an upright nail as handle there was placed an apple, out of Lizzie's reach. She reacted immediately for the nail, pulled the board in, and got the apple. There was no employment of the method of trial and error. There was direct, appropriate action following the perception of her relation to board, nail, and apple. Of course, her ancestors may have been adepts at drawing a fruit-laden branch within their reach, but the simple experiment was very instructive. All the more instructive because in many other cases the experiments indicate a gradual sifting out of useless movements, and an eventful retention of the one that pays. When Lizzie was given a Vaseline bottle containing a peanut and closed with a cork, she at once pulled the cork with her teeth, obeying the instinct to bite at new objects, but she never learned to turn the bottle upside down and let the nut drop out. She often got the nut, and after some education she got it more quickly than she did at first, but there was no indication that she ever perceived the fit and proper way of getting what she wanted. Quote, "In the course of her intent efforts, her mind seemed so absorbed with the object of desire that it was never focused on the means of attaining that object. There was no deliberation, and no discrimination between the important and the unimportant elements in her behavior. The gradually increasing facility of her performances depended on the apparently unconscious elimination of useless movements." End quote. This may be called learning, but it is learning at a very low level. It is far from learning by ideas. It is hardly even learning by experiment. It is not more than learning by experience. It is not more than fumbling at learning. Trial and error. A higher note is struck in the behavior of some more highly endowed monkeys. In many experiments, chiefly in the way of getting into boxes difficult to open, there is evidence, 1. Of attentive persistent experiment, 2. Of the rapid elimination of ineffective movements, and 3. Of remembering the solution when it was discovered. Kinnaman taught 2 macaques the Hampton Court maze, a feat which probably means a memory of movements, and we get an interesting glimpse in the observation that they began to smack their lips audibly when they reached the latter part of their course, and began to feel, dare one say, "We are right this time." In getting into puzzle boxes and into combination boxes, where the barriers must be overcome in a definite order, monkeys learn by the trial and error method much more quickly than cats and dogs do, and a very suggestive fact emphasized by Professor Thorndike is, quote, "a process of sudden acquisition by a rapid, often apparently instantaneous abandonment of the unsuccessful movements and selection of the appropriate one, which reveals in suddenness the selections made by human beings in similar performances." End quote. A higher note still was sounded by one of Thorndike's monkeys, which opened a puzzle box at once, 8 months after his previous experience with it. For here was some sort of a registration of a solution. Imitation. 2 chimpanzees in the Dublin Zoo were often to be seen washing the 2 shelves of their cupboard and wringing the wet cloth in the approved fashion. It was like a caricature of a washerwoman, and someone said, "What mimics they are!" Now we do not know whether that was or was not the case with the chimpanzees, but the majority of the experiments that have been made do not lead us to attach to imitation so much importance as is usually given to it by the popular interpreter. There are instances where a monkey that had given up a puzzle in despair returned to it when it had seen its neighbor succeed, but most of the experiments suggested that the creature has to find out for itself. Even with such a simple problem as drawing food near with a stick, it often seems of little use to show the monkeys how it is done. Placing a bit of food outside the monkey's cage, Professor Holmes poked it about with a stick, so as to give her a suggestion of how the stick might be employed to move the food within reach, but although the act was repeated many times, Lizzie never showed the least inclination to use the stick to her advantage. Perhaps the idea of a tool is beyond the bonnet monkey. Yet here again we must be cautious, for Professor L.T. Hobhouse had a monkey of the same macaque genus, which learned in the course of time to use a crooked stick with great effect. The case of Peter. Perhaps the cleverest monkey as yet studied was a performing chimpanzee called Peter, which has been generally described by Dr. Leitner Whitmer. Peter could skate and cycle, thread needles and untie knots, smoke a cigarette and string beads, screw in nails and unlock locks. But what Peter was thinking about all the time it was hard to guess, and there is very little evidence to suggest that his rapid power of putting two and two together ever rose above a sort of concrete mental experimenting, which Dr. Romanes used to call perceptual inference. Without supposing that there are hard and fast boundary lines, we cannot avoid the general conclusion that, while monkeys are often intelligent, they seldom, if ever, show even hints of reason, i.e., of working or playing with general ideas. That remains man's prerogative. The bustle of the mind. In mammals like otters, foxes, stoats, hares, and elephants, what a complex of tides and currents there must be in the brain-mind! We may think of a stream with currents at different levels. Lowest, there are the basal appetites of hunger and sex, often with eddies rising to the surface. Then there are the primary emotions, such as fear of hereditary enemies and maternal affection for offspring. Above these are instinctive aptitudes, inborn powers of doing clever things without having to learn how. But in mammals these are often expressed along with, or as it were through, the controlled life of intelligent activity, where there is more clear-cut perceptual influence. Higher still are the records or memories of individual experience and the registration of individual habits, while on the surface it is the in-streaming multitude of messages from the outside world, like raindrops and hailstones on the stream, some of them penetrating deeply, being, as we say, full of meaning. The mind of the higher animal is in some respects like a child's mind, in having little in the way of clear-cut ideas, in showing no reason in the strict sense, and in its extraordinary educability, but it differs from the child's mind entirely in the sure effectiveness of a certain repertory of responses. It is efficient to a degree. Quote, "Until at last arose the man." Man's brain is more complicated than that of the higher apes, gorilla, orang, and chimpanzee, and it is relatively larger. But the improvements in structure do not seem in themselves sufficient to account for man's great advance in intelligence. The rill of inner life has become a swift stream, sometimes a rushing torrent. Besides perceptual inference or intelligence, a sort of picture logic, which some animals likewise have, there is conceptual inference, or reason, an internal experimenting with general ideas. Even the cleverest animals, it would seem, do not get much beyond playing with particulars. Man plays an internal game of chess with universals. Intelligent behavior may go a long way with mental images. Rational conduct demands general ideas. It may be, however, that percepts and concepts differ rather in degree than in kind, and that the passage from one to the other meant a higher power of forming associations. A clever dog has probably a generalized percept of man, as distinguished from a memory image of the particular man it has known, but man alone has the concept man, or mankind, or humanity. Experimenting with concepts or general ideas is what we call reason. Here, of course, we get into deep waters, and perhaps it is wisest not to attempt too much. So we shall content ourselves here with pointing out that man's advance in intelligence, and from intelligence to reason, is closely wrapped up with his power of speech. What animals began, a small vocabulary, he has carried to high perfection. But what is distinctive is not the vocabulary so much as the habit of making sentences, of expressing judgments in a way which admitted of communication between mind and mind. The multiplication of words meant much. The use of words as symbols of general ideas meant even more, for it meant the possibility of playing the internal game of thinking. But perhaps the most important advance of all was the means of comparing notes with neighbors, of corroborating individual experience by social intercourse. With words also, it became easier to enregister outside himself the gains of the past. It is not without significance that the Greek logos, which may be translated the word, may also be translated mind. Part 9. Looking backwards. When we take a survey of animal behavior, we see a long inclined plane. The outer world provokes simple creatures to answer back. Simple creatures act experimentally on their surroundings. From the beginning, this twofold process has been going on, receiving stimuli from the environment and acting upon the environment, and according to the efficiency of the reactions and actions living creatures have been sifted for millions of years. One main line of advance has been opening new gateways of knowledge. The senses, which are far more than 5 in number. The other main line of advance has been in most general terms, experimenting or testing, probing and proving, trying one key after another till a door is unlocked. There is progress in multiplying the gateways of knowledge and making them more discriminating, and there is progress in making the modes of experimenting more wide awake, more controlled, and more resolute. But behind both of these is the characteristically vital power of enregistering within the organism the lessons of the past. In the life of the individual, these enregistrations are illustrated by memories and habituations and habits. In the life of the race, they are illustrated by reflex actions and instinctive capacities. Body and mind. We must not shirk the very difficult question of the relation between the bodily and the mental side of behavior. A. Some great thinkers have taught that the mind is a reality by itself, which plays upon the instrument of the brain and body. As the instrument gets worn and dusty, the playing is not so good as it once was, but the player is still himself. This theory of the essential independence of the mind is a very beautiful one, but those who like it when applied to themselves are not always so fond of it when it is applied to other intelligent creatures, like rooks and elephants. It may be, however, that there is a gradual emancipation of the mind which has gone furthest in man, and is still progressing. B. Some other thinkers have taught that the inner life of thought and feeling is only, as it were, an echo of the really important activity, that of the body and brain. Ideas are just foam bells on the hurrying streams and circling eddies of matter and energy that make up our physiological life. To most of us this theory is impossible, because we are quite sure that ideas and feelings and purposes, which cannot be translated into matter and motion, are the clearest realities in our experience, and that they count for good and ill all through our life. They are more than the tickings of the clock, they make the wheels go round. C. there are others who think that the most scientific position is simply to recognize both the bodily and the mental activities as equally important, and so closely interwoven that they cannot be separated. Perhaps they are just the outer and the inner aspects of one reality, the life of the creature. Perhaps they are like the concave and convex curves of a dome, like the two sides of a shield. Perhaps the life of the organism is always a unity, at one time appearing more conspicuously as mind-body, at another time as body-mind. The most important fact is that neither aspect can be left out. By no jugglery with words can we get mind out of matter and motion. And since we are in ourselves quite sure of our mind, we are probably safe in saying that in the beginning was mind. This is in accordance with Aristotle's saying that there is nothing in the end which was not also in kind present in the beginning, whatever we mean by beginning. In conclusion, what has led to the truly wonderful result which we admire in a creature like a dog or an otter, a horse or a hare? In general we may say just two main processes: 1. Testing all things, and 2. Holding fast that which is good. New departures occur, and these are tested for what they are worth. Idiosyncrasies crop up, and they are sifted. New cards come mysteriously from within into the creature's hand, and they're played, for better or for worse. So by new variations and their sifting, by experimenting and in registering the results, the mind has gradually evolved, and will continue to evolve. End of Part 12.
Section 13 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Jude Cater. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 13. Part 8. Foundations of the Universe. The World of Atoms. Most people have heard of the Oriental race which puzzled over the foundations of the universe and decided that it must be supported on the back of a giant elephant. But the elephant? They put it on the back of a monstrous tortoise, and there they let the matter end. If every animal in nature had been called upon, they would have been no nearer a foundation. Most ancient peoples, indeed, made no effort to find a foundation. The universe was a very compact little structure, mainly composed of the earth and the great canopy over the earth, which they call the sky. They left it, as a whole, floating in nothing. And in this the ancients were wiser than they knew. Things do not fall down unless they are pulled down by that mysterious force which we call gravitation. The earth, it is true, is pulled by the sun, and would fall into it, but the earth escapes this fiery fate by circulating at great speed round the sun. The stars pull each other, but it has already been explained that they meet this by traveling rapidly in gigantic orbits. Yet we do, in a new sense of the word, need foundations of the universe. Our mind craves for some explanation of the matter out of which the universe is made. For this explanation, we turn to modern physics and chemistry. Both these sciences study, under different aspects, matter and energy, and between them they have put together a conception of the fundamental nature of things, which marks an epoch in the history of human thought. 1. The bricks of the cosmos. More than 2,000 years ago, the first men of science, the Greeks of the cities of Asia Minor, speculated on the nature of matter. You can grind a piece of stone into dust. You can divide a spoonful of water into as many drops as you like. Apparently, you can go on dividing as long as you have got apparatus fine enough for the work. But there must be a limit, these Greeks said, and so they supposed that all matter was ultimately composed of minute particles which were indivisible. That is the meaning of the Greek word, atom. Like so many other ideas of these brilliant early Greek thinkers, the atom was a sound conception. We know today that matter is composed of atoms, but science was then so young that the way in which the Greeks applied the idea was not very profound. A liquid or a gas, they said, consisted of round, smooth atoms which would not cling together. Then there were atoms with rough surfaces, hooky surfaces, and these stuck together and formed solids. The atoms of iron or marble, for instance, were so very hooky that, once they got together, a strong man could not tear them apart. The Greeks thought that the explanation of the universe was that an infinite number of these atoms had been moving and mixing in an infinite space during an infinite time, and had at last hit by chance on the particular combination, which is our universe. This was too simple and superficial. The idea of atoms was cast aside, only to be advanced again in various ways. It was the famous Manchester chemist John Dalton who restored it in the early years of the 19th century. He first definitely formulated the atomic theory as a scientific hypothesis. The whole physical and chemical science of that century was now based upon the atom, and it is quite a mistake to suppose that recent discoveries have discredited atomism. An atom is the smallest particle of a chemical element. No one has ever seen an atom. Even the wonderful new microscope which has just been invented cannot possibly show us particles of matter which are 1,000,000 times smaller than the breadth of a hair, for that is the size of atoms. We can weigh them and measure them, though they are invisible, and we know that all matter is composed of them. It is a new discovery that atoms are not indivisible. They consist themselves of still smaller particles, as we shall see. But the atoms exist all the same, and we may still say that they are the bricks of which the material universe is built. But if we had some magical glass by means of which we could see into the structure of material things, we should not see the atoms put evenly together as bricks are in a wall. As a rule, two or more atoms first come together to form a larger particle, which we call a molecule. Single atoms do not, as a rule, exist apart from other atoms. If a molecule is broken up, the individual atoms seek to unite with other atoms of another kind, or amongst themselves. For example, 3 atoms of oxygen form what we call ozone. 2 atoms of hydrogen uniting with 1 atom of oxygen form water. It is molecules that form the mass of matter. A molecule, as it has been expressed, is a little building of which atoms are the bricks. In this way we get a useful first view of the material things we handle. In a liquid, the molecules of the liquid cling together loosely. They remain together as a body, but they roll over and away from each other. There is a cohesion between them, but it is less powerful than in a solid. Put some water in a kettle over the lighted gas, and presently the tiny molecules of water will rush through the spout in a cloud of steam and scatter over the kitchen. The heat has broken their bond of association and turned the water into something like a gas, though we know that the particles will come together again, as they cool, and form once more drops of water. In a gas, the molecules have full individual liberty. They are in a state of violent movement, and they form no union with each other. If we want to force them to enter into the loose sort of association which molecules have in a liquid, we have to slow down their individual movements by applying severe cold. That is how a modern man of science liquefies gases. No power that we have will liquefy air at its ordinary temperature. In very severe cold, on the other hand, the air will spontaneously become liquid. Someday, when the fires of the sun have sunk very low, the temperature of the earth will be less than negative 200 degrees centigrade. That is to say, more than 200 degrees centigrade below freezing point. It will sink to the temperature of the moon. Our atmosphere will then be an ocean of liquid air 35 feet deep, lying upon the solidly frozen masses of our water oceans. In a solid, the molecules cling firmly to each other. We need a force equal to 25 tons to tear asunder the molecules in a bar of iron an inch thick. Yet the structure is not solid in the popular sense of the word. If you put a piece of solid gold in a little pool of mercury, the gold will take in the mercury between its molecules as if it were porous like a sponge. The hardest solid is more like a lattice work than what we mean by solid, though the molecules are not fixed like the bars of a lattice work, but are in violent motion. They vibrate about equilibrium positions. If we could see right into the heart of a bit of the hardest steel, we should see billions of separate molecules at some distance from each other, all moving rapidly to and fro. This molecular movement can, in a measure, be made visible. It was noticed by a microscopist named Brown that, in a solution containing very fine suspended particles, the particles were in constant movement. Under a powerful microscope, these particles are seen to be violently agitated. They are each independently darting hither and thither, somewhat like a lot of billiard balls on a billiard table, colliding and bounding about in all directions. Thousands of times a second these encounters occur, and this lively commotion is always going on. This incessant colliding of one molecule with another is the normal condition of affairs. Not one of them is at rest. The reason for this has been worked out, and it is now known that these particles move about because they are being incessantly bombarded by molecules of the liquid. The molecules cannot, of course, be seen, but the fact of their incessant movement is revealed to the eye by the behavior of the visible suspended particles. This incessant movement in the world of molecules is called the Brownian movement, and is a striking proof of the reality of molecular motions. 2. The wonder world of atoms. The exploration of this wonder world of atoms and molecules by the physicists and chemists of today is one of the most impressive triumphs of modern science. Quite apart from radium and electrons and other sensational discoveries of recent years, the study of ordinary matter is hardly inferior, either in interest or audacity, to the work of the astronomer. And there is the same foundation in both cases, marvelous apparatus, and trains of mathematical reasoning that would have astonished Euclid or Archimedes. Extraordinary, therefore, as are some of the facts and figures we are now going to give in connection with the minuteness of atoms and molecules, let us bear in mind that we owe them to the most solid and severe processes of human thought. Yet the principle can, in most cases, be made so clear that the reader will not be asked to take much on trust. It is, for instance, a matter of common knowledge that gold is soft enough to be beaten into gold leaf. It is a matter of common sense, one hopes, that if you beat a measured cube of gold into a leaf 6 inches square, the mathematician can tell the thickness of that leaf without measuring it. As a matter of fact, a single grain of gold has been beaten into a leaf 75 inches square. Now the mathematician can easily find that when a single grain of gold is beaten out to that size, the leaf must be 1/367,000th of an inch thick, or about 1,000 times thinner than the paper on which these words are printed. Yet the leaf must be several molecules thick. The finest gold leaf is, in fact, too thick for our purpose, and we turn with a new interest to that toy of our boyhood, the soap bubble. If you carefully examine one of these delicate films of soapy water, you notice certain dark spots or patches on them. These are their thinnest parts, and by two quite independent methods, one using electricity and the other light, we have found that at these spots the bubble is less than the 3/1,000,000th of an inch thick. But the molecules in the film cling together so firmly that they must be at least 20 or 30 deep in the thinnest part. A molecule, therefore, must be far less than the 3/1,000,000th of an inch thick. We found next that a film of oil on the surface of water may be even thinner than a soap bubble. Professor Perrin, the great French authority on atoms, got films of oil down to the 50/1,000,000th of an inch in thickness. He poured a measured drop of oil upon water. Then he found the exact limits of the area of the oil sheet by blowing upon the water a fine powder which spread to the edge of the film and clearly outlined it. The rest is safe and simple calculation, as in the case of a beaten grain of gold. Now this film of oil must be at least 2 molecules deep, so a single molecule of oil is considerably less than 100/1,000,000th of an inch in diameter. Innumerable methods have been tried, and the result is always the same. A single grain of indigo, for instance, will color a ton of water. This obviously means that the grain contains billions of molecules which spread through the water. A grain of musk will scent a room, pour molecules into every part of it, for several years, yet not lose 1/1,000,000th of its mass in a year. There are hundreds of ways of showing the minuteness of the ultimate particles of matter, and some of these enable us to give definite figures. On a careful comparison of the best methods, we can say that the average molecule of matter is less than the 1/125,000,000th of an inch in diameter. In a single cubic centimeter of air, a globule about the size of a small marble, there are 30,000,000,000,000,000,000,000 molecules. And since the molecule is, as we saw, a group or cluster of atoms, the atom itself is smaller. Atoms, for reasons which we shall see later, differ very greatly from each other in size and weight. It is enough to say that some of them are so small that it would take 400,000,000 of them in a line to cover an inch of space, and that it takes at least a quintillion atoms of gold to weigh a single gram. 5,000,000 atoms of helium could be placed in a line across the diameter of a full stop. The energy of atoms. And this is only the beginning of the wonders that were done with ordinary matter, quite apart from radium and its revelations, to which we will come presently. Most people have heard of atomic energy and the extraordinary things that might be accomplished if we could harness this energy and turn it to human use. A deeper and more wonderful source of this energy has been discovered in the last 20 years, but it is well to realize that the atoms themselves have stupendous energy. The atoms of matter are vibrating or gyrating with extraordinary vigor. The piece of cold iron you hold in your hand, the bit of brick you pick up, or the penny you take from your pocket, is a colossal reservoir of energy, since it consists of trillions of moving atoms. To realize the total energy, of course, we should have to witness a transformation such as we do in atoms of radioactive elements, about which we shall have something to say presently. If we put a grain of indigo in a glass of water, or a grain of musk in a perfectly still room, we soon realize that molecules travel. Similarly, the fact that gases spread until they fill every empty available space shows definitely that they consist of small particles traveling at great speed. The physicist brings his refined methods to bear on these things, and he measures the energy and velocity of these infinitely minute molecules. He tells us that molecules of oxygen, at the temperature of melting ice, travel at the rate of about 500 yards a second, more than 1/4 of a mile a second. Molecules of hydrogen travel at 4 times that speed, or 3 times the speed with which a bullet leaves a rifle. Each molecule of air, which seems so still in the house on a summer's day, is really traveling faster than a rifle bullet does at the beginning of its journey. It collides with another molecule every 20,000th of an inch of its journey. It is turned from its course 5 billion times in every second by collisions. If we could stop the molecules of hydrogen gas and utilize their energy, as we utilize the energy of steam or the energy of water at Niagara, we should find enough in every gram of gas, about 2/1000ths of a pound, to raise 1/3 of a ton to a height of 40 inches. I have used for comparison the speed of a rifle bullet, and in an earlier generation people would have thought it impossible even to estimate this. It is, of course, easy. We put 2 screens in the path of the bullet, one near the rifle and the other some distance away. We connect them electrically and use a fine time-recording machine, and the bullet itself registers the time it takes to travel from the first to the second screen. Now, this is a very simple and superficial work in comparison with the system of exact and minute measurements which the physicist and chemist use. In one of his interesting works, Mr. Charles R. Gibson gives a photograph of 2 exactly equal pieces of paper in the opposite pans of a fine balance. A single word has been written in pencil on one of these papers, and that little scraping of lead has enough to bring down the scale. The spectroscope will detect a quantity of matter 4 million times smaller than even this, and the electroscope is 1,000,000 times still more sensitive than the spectroscope. We have a heat measuring instrument, the bolometer, which makes the best thermometer seem early Victorian. It records the 1,000,000th of a degree of temperature. It is such instruments multiplied by the score which enable us to do the fine work recorded in these pages. 3. The discovery of X-rays and radium. The discovery of Sir William Crookes. But these wonders of the atom are only a prelude to the more romantic and far-reaching discoveries of the new physics, the wonders of the electron. Another, and the most important phase of our exploration of the material universe, opened with the discovery of radium in 1898. In the discovery of radioactive elements, a new property of matter was discovered. What followed on the discovery of radium and of the X-rays we shall see. As Sir Ernest Rutherford, one of our greatest authorities, recently said, the new physics has dissipated the last doubt about the reality of atoms and molecules. The closer examination of matter which we have been able to make shows positively that it is composed of atoms. But we must not take the word now in its original Greek meaning, an indivisible thing. The atoms are not indivisible. They can be broken up. They are composed of still smaller particles. The discovery that the atom was composed of smaller particles was the welcome realization of a dream that had haunted the imagination of the 19th century. Chemists said that there were about 80 different kinds of atoms, different kinds of matter, but no one was satisfied with the multiplicity. Science is always aiming at simplicity and unity. It may be that science has now taken a long step in the direction of explaining the fundamental unity of all matter. The chemist was unable to break up these elements into something simpler, so he called their atoms indivisible in that sense. But one man of science after another expressed the hope that he would yet discover some fundamental matter of which the various atoms were composed. One primordial substance from which all the varying forms of matter have been evolved or built up. Prout suggested this at the very beginning of the century, when atoms were rediscovered by Dalton. Father Secchi, the famous Jesuit astronomer, said that all the atoms were probably evolved from ether, and this was a very favored speculation. Sir William Crookes talked of prothol as the fundamental substance. Others thought hydrogen was the stuff out of which all the other atoms were composed. The work which finally resulted in the discovery of radium began with some beautiful experiments of Professor, later Sir William, Crookes in the 80s. It had been noticed in 1869 that a strange coloring was caused when an electric charge was sent through a vacuum tube. The walls of the glass tube began to glow with a greenish phosphorescence. A vacuum tube is one from which nearly all the air has been pumped, although we can never completely empty the tube. Crookes used such ingenious methods that he reduced the gas in his tubes until it was 20 million times thinner than the atmosphere. He then sent an electrical discharge through, and got very remarkable results. The negative pole of the electric current, the cathode, gave off rays which faintly lit the molecules of the thin gas in the tube, and caused a pretty fluorescence on the glass walls of the tube. What were these rays? Crookes at first thought they corresponded to a new or fourth state of matter. Hitherto we had only been familiar with matter in the three conditions of solid, liquid, and gaseous. Now Crookes really had the great secret under his eyes. But about 20 years elapsed before the true nature of these rays was finally and independently established by various experiments. The experiments proved that the rays consisted of a stream of negatively charged particles traveling with enormous velocities from 10,000 to 100,000 miles a second. In addition, it was found that the mass of each particle was exceedingly small, about 1/1800th of the mass of a hydrogen atom, the lightest atom known to science. These particles, or electrons as they are now called, were being liberated from the atom. The atoms of matter were breaking down in Crookes' tubes. At that time, however, it was premature to think of such a thing, and Crookes preferred to say that the particles of the gas were electrified and hurled against the walls of the tube. He said that it was ordinary matter in a new state, radiant matter. Another distinguished man of science, Leonard, found that, when he fitted a plate of aluminum in the glass wall of the tube, the mysterious rays passed through this as if it were a window. They must be waves in the ether, he said. 4. The discovery of X-rays. So the story went on from year to year. We shall see in a moment to what it led. Meanwhile, the next great step was when, in 1895, Röntgen discovered the X-rays, which are now known to everybody. He was following up the work of Leonard, and one day he covered a Crookes tube with some black stuff. To his astonishment, a prepared chemical screen which was near the tube began to glow. The rays had gone through the black stuff, and on further experiment he found that they would go through stone, living flesh, and all sorts of opaque substances. In a short time the world was astonished to learn that we could photograph the skeleton in a living man's body, locate a penny in the interior of a child that had swallowed one, or take an impression of a coin through a slab of stone. And what are these X-rays? They are not a form of matter. They are not material particles. X-rays were found to be a new variety of light with a remarkable power of penetration. We have seen what the spectroscope reveals about the varying nature of light wavelengths. Light waves are set up by vibrations in ether, and as we shall see, these ether disturbances are all of the same kind. They only differ as regards wavelengths. The X-rays which Röntgen discovered, then, are light, but a variety of light previously unknown to us. They are ether waves of very short length. X-rays have proved of great value in many directions, as all the world knows, but that we need not discuss at this point. Let us see what followed Röntgen's discovery. Footnote: we refer throughout to the ether because, although modern theories dispense largely with this conception, the theories of physics are so inextricably interwoven with it that it is necessary, in an elementary exposition, to assume its existence. The modern view will be explained later in the article on Einstein's theory. End footnote. While the world wondered at these marvels, the men of science were eagerly following up the new clue to the mystery of matter which was exercising the mind of Crookes and other investigators. In 1896, Becquerel brought us to the threshold of the great discovery. Certain substances are phosphorescent. They become luminous after they have been exposed to sunlight for some time, and Becquerel was trying to find if any of these substances give rise to X-rays. One day, he chose a salt of the metal uranium. He was going to see if, after exposing it to sunlight, he could photograph a cross with it through an opaque substance. He wrapped it up and laid it aside to wait for the sun, but he found the uranium salt did not wait for the sun. Some strong radiation from it went through the opaque covering and made an impression of the cross upon the plate underneath. Light, or darkness, was immaterial. The mysterious rays streamed night and day from the salt. This was something new. Here was a substance which appeared to be producing X-rays. The rays emitted by uranium would penetrate the same opaque substances as the X-rays discovered by Röntgen. Discovery of radium. Now, at the same time as many other investigators, Professor Curie and his Polish wife took up the search. They decided to find out whether the emission came from the uranium itself or from something associated with it, and for this purpose they made a chemical analysis of great quantities of minerals. They found a certain kind of pitchblende which was very active, and they analyzed tons of it, concentrating always on the radiant element in it. After a time, as they successively worked out the non-radiant matter, the stuff began to glow. In the end, they extracted from 8 tons of pitchblende about half a teaspoonful of something that was 1,000,000 times more radiant than uranium. There was only one name for it: radium. That was the starting point of the new development of physics and chemistry. From every laboratory in the world came a cry for radium salts, as pure radium was too precious, and hundreds of brilliant workers fastened on the new element. The inquiry was broadened, and as year followed year, one substance after another was found to possess the power of emitting rays, that is, to be radioactive. We know today that nearly every form of matter can be stimulated to radioactivity, which, as we shall see, means that its atoms break up into smaller and wonderfully energetic particles which we call electrons. This discovery of electrons has brought about a complete change in our ideas in many directions. So instead of atoms being indivisible, they are actually dividing themselves spontaneously and giving off throughout the universe tiny fragments of their substance. We shall explain presently what was later discovered about the electron. Meanwhile, we can say that every glowing metal is pouring out a stream of these electrons. Every arc lamp is discharging them. Every clap of thunder means a shower of them. Every star is flooding space with them. We are witnessing the spontaneous breaking up of atoms which had been thought to be indivisible. The sun not only pours out streams of electrons from its own atoms, but the ultraviolet light which it sends to the earth is one of the most powerful agencies for releasing electrons from the surface atoms of matter on the earth. It is fortunate for us that our atmosphere absorbs most of this ultraviolet or invisible light of the sun, a kind of light which will be explained presently. It has been suggested that, if we received the full flood of it from the sun, our metals would disintegrate under its influence, and this steel civilization of ours would be impossible. But here we are anticipating. We are going beyond radium to the wonderful discoveries which were made by the chemists and physicists of the world who concentrated upon it. The work of Professor and Madame Curie was merely the final clue to guide the great search. How it was followed up, how we penetrated into the very heart of the minute atom and discovered new and portentous mines of energy, and how we were able to understand not only matter, but electricity and light, will be told in the next chapter. The discovery of the electron and how it affected a revolution in ideas. What the discovery of radium implied was only gradually released. Radium captivated the imagination of the world. It was a boon to medicine, but to the man of science it was at first a most puzzling and most attractive phenomenon. It was felt that some great secret of nature was dimly unveiled in its wonderful manifestations, and there now concentrated upon it as gifted a body of men, conspicuous amongst them Sir J. Thomson, Sir Ernest Rutherford, Sir W. Ramsay, and Professor Soddy, as any age could boast, with an apparatus of research as far beyond that of any other age as the Aquitania is beyond a Roman galley. Within 5 years the secret was fairly mastered. Not only were all kinds of matter reduced to a common basis, but the forces of the universe were brought into a unity and understood as they had never been understood before. 5. The discovery of the electron. Physicists did not take long to discover that the radiation from radium was very like the radiation in a Crookes tube. It was quickly recognized, moreover, that both in the tube and in radium and other metals, the atoms of matter were somehow breaking down. However, the first step was to recognize that there were 3 distinct and different rays that were given off by such metals as radium and uranium. Sir Ernest Rutherford christened them, after the first 3 letters of the Greek alphabet, the alpha, the beta, and gamma rays. We are concerned chiefly with the second group, and purpose here to deal with that group only. Footnote: the alpha rays were presently recognized as atoms of helium gas shot out at a rate of 12,000 miles a second. The gamma rays are waves, like the X-rays, not material particles. They appear to be a type of X-rays. They possess the remarkable power of penetrating opaque substances. They will pass through a foot of solid iron, for example. The beta rays, as they were first called, have proved to be one of the most interesting discoveries that science ever made. They proved what Crookes had surmised about the radiations he discovered in his vacuum tube. But it was not a 4th state of matter that had been found, but a new property of matter, a property common to all atoms of matter. The beta rays were later christened electrons. They are particles of disembodied electricity, here spontaneously liberated from the atoms of matter. Only when the electron was isolated from the atom was it recognized for the first time as a separate entity. Electrons, therefore, are a constituent of the atoms of matter, and we have discovered that they can be released from the atom by a variety of agencies. Electrons are to be found everywhere, forming part of every atom. An electron, Sir William Bragg says, can only maintain a separate existence if it is traveling at an immense rate, from 1/300th of the velocity of light upwards, that is to say, at least 600 miles a second or thereabouts. Otherwise the electron sticks to the first atom it meets. These amazing particles may travel with the enormous velocity of from 10,000 to more than 100,000 miles a second. It was first learned that they are of an electrical nature, because they are bent out of their normal path if a magnet is brought near them. And this fact led to a further discovery, to one of those sensational estimates which the general public is apt to believe to be founded on the most abstruse speculations. The physicist set up a little chemical screen for the beta rays to hit, and he so arranged his tube that only a narrow sheaf of the rays poured onto the screen. He then drew this sheaf of rays out of its course with a magnet, and he accurately measured the shift of the luminous spot on the screen where the rays impinged on it. But when he knows the exact intensity of his magnetic field, which he can control as he likes, and the amount of deviation it causes, and the mass of the moving particles, he can tell the speed of the moving particles which he thus diverts. These particles were being hurled out of the atoms of radium, or from the negative pole in a vacuum tube, at a speed which, in good conditions, reached nearly the velocity of light. That is, nearly 186,000 miles a second. Their speed has, of course, been confirmed by numbers of experiments, and another series of experiments enabled physicists to determine the size of the particles. Only one of these need be described, to give the reader an idea of how men of science arrived at their more startling results. Fog, as most people know, is thick in our great cities because the water vapor gathers on the particles of dust and smoke that are in the atmosphere. This fact was used as the basis of some beautiful experiments. Artificial fogs were created in little glass tubes by introducing dust in various proportions for supersaturated vapor to gather on. In the end, it was possible to cause tiny drops of rain, each with a particle of dust at its core, to fall upon a silver mirror and be counted. It was a method of counting the quite invisible particles of dust in the tube, and the method was now successfully applied to the new rays. Yet another method was to direct a slender stream of the particles upon a chemical screen. The screen glowed under the cannonade of particles, and a powerful lens resolved the glow into distinct sparks, which could be counted. In short, a series of the most remarkable and beautiful experiments, checked in all the great laboratories of the world, settled the nature of these so-called rays. They were streams of particles more than 1,000 times smaller than the smallest known atom. The mass of each particle is, according to the latest and finest measurements, 1/1,845th of that of an atom of hydrogen. The physicist has not been able to find any character except electricity in them, and the name electrons has been generally adopted. The key to many mysteries. The electron is an atom of disembodied electricity. It occupies an exceedingly small volume, and its mass is entirely electrical. These electrons are the key to half the mysteries of matter. Electrons in rapid motion, as we shall see, explain what we mean by an electric current, not so long ago regarded as one of the most mysterious manifestations in nature. What a wonder, then, we have here, says Professor R.K. Duncan. An innocent-looking little pinch of salt, and yet possessed of special properties utterly beyond even the fanciful imaginings of men of past time. For nowhere do we find in the records of thought even the hint of the possibility of things which we now regard as established fact. This pinch of salt projects from its surface bodies, that is, electrons, possessing the inconceivable velocity of over 100,000 miles a second, a velocity sufficient to carry them, if unimpeded, 5 times around the earth in a second, and possessing with this velocity masses 1,000 times smaller than the smallest atom known to science. Furthermore, they are charged with negative electricity. They pass straight through bodies considered opaque with a sublime indifference to the properties of the body, with the exception of its mere density. They cause bodies which they strike to shine out in the dark. They affect a photographic plate. They render the air a conductor of electricity. They cause clouds and moist air. They cause chemical action and have a peculiar physiological action. Who today shall predict the ultimate service to humanity of the beta rays from radium? End of section 13. Section 14 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. EBooks.org. Recording by Jude Cater. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 14. Part 8, Foundations of the Universe. Continued. 6. The Electron Theory, or the New View of Matter. The Structure of the Atom. There is general agreement amongst all chemists, physicists, and mathematicians upon the conclusions which we have so far given. We know that the atoms of matter are constantly, either spontaneously or under stimulation, giving off electrons or breaking up into electrons, and they therefore contain electrons. Thus, we have now complete proof of the independent existence of atoms and also of electrons. When, however, the man of science tries to tell us how electrons compose atoms, he passes from facts to speculation, and very difficult speculation. Take the letter O as it is printed on this page. In a little bubble of hydrogen gas no larger than that letter, there are trillions of atoms, and they are not packed together, but are circulating as freely as dancers in a ballroom. We are asking the physicist to take one of these minute atoms and tell us how the still smaller electrons are arranged in it. Naturally, he can only make mental pictures, guesses, or hypotheses, which he tries to fit to the facts, and discards when they will not fit. At present, after nearly 20 years of critical discussion, there are two chief theories of the structure of the atom. At first, Sir J. Thomson imagined the electrons circulating in shells, like the layers of an onion, round the nucleus of the atom. This did not suit, and Sir E. Rutherford and others worked out a theory that the electrons circulated round a nucleus rather like the planets of our solar system revolving round the central sun. Is there a nucleus, then, round which the electrons revolve? The electron, as we saw, is a disembodied atom of electricity. We should say of negative electricity. Let us picture these electrons all moving round in orbits with great velocity. Now it is suggested that there is a nucleus of positive electricity attracting or pulling the revolving electrons to it, and so forming an equilibrium. Otherwise, the electrons would fly off in all directions. This nucleus has recently been named the proton. We have thus two electricities in the atom, the positive equaling the nucleus, the negative equaling the electron. Of recent years, Dr. Langmuir has put out a theory that the electrons do not revolve round the nucleus, but remain in a state of violent agitation of some sort at fixed distances from the nucleus. But we will confine ourselves here to the facts, and leave the contending theories to scientific men. It is now pretty generally accepted that an atom of matter consists of a number of electrons, or charges of negative electricity, held together by a charge of positive electricity. It is not disputed that these electrons are in a state of violent motion or strain, and that, therefore, a vast energy is locked up in the atoms of matter. To that we will return later. Here, rather, we will notice another remarkable discovery which helps us to understand the nature of matter. A brilliant young man of science who was killed in the war, Mr. Moseley, some years ago showed that, when the atoms of different substances are arranged in order of their weight, they are also arranged in order of increasing complexity of structure. That is to say, the heavier the atom, the more electrons it contains. There is a gradual building up of atoms containing more and more electrons from the lightest atom to the heaviest. Here it is enough to say that as he took element after element, from the lightest, hydrogen, to the heaviest, uranium, he found a strangely regular relation between them. If hydrogen were represented by Figure 1, helium by 2, lithium 3, and so on up to uranium, then uranium should have the figure 92. This makes it probable that there are in nature 92 elements. We have found 87, and that the number Mr. Moseley found is the number of electrons in the atom of each element. That is to say, the number is arranged in order of the atomic numbers of the various elements. 7. The new view of matter. Up to the point we have reached, then, we see what the new view of matter is. Every atom of matter, of whatever kind throughout the whole universe, is built up of electrons in conjunction with a nucleus. From the smallest atom of all, the atom of hydrogen, which consists of one electron rotating round a positively charged nucleus, to a heavy, complicated atom such as the atom of gold, constituted of many electrons in a complex nucleus, we have only to do with positive and negative units of electricity. The electron and its nucleus are particles of electricity. All matter, therefore, is nothing but a manifestation of electricity. The atoms of matter, as we saw, combine and form molecules. Atoms and molecules are the bricks of which nature has built up everything: ourselves, the earth, the stars, the whole universe. But more than bricks are required to build a house. There are other fundamental existences, such as the various forms of energy, which give rise to several complex problems. And we have also to remember that there are more than 80 distinct elements, each with its own definite type of atom. We shall deal with energy later. Meanwhile, it remains to be said that although we have discovered a great deal about the electron and the constitution of matter, and that while physicists of our own day seem to see a possibility of explaining positive and negative electricity, the nature of them both is unknown. There exists the theory that the particles of positive and negative electricity, which make up the atoms of matter, are points or centers of disturbances of some kind in a universal ether, and that all the various forms of energy are, in some fundamental way, aspects of the same primary entity which constitutes matter itself. But the discovery of the property of radioactivity has raised many other interesting questions besides that which we have just dealt with. In radioactive elements, such as uranium, for example, the element is breaking down. In what we call radioactivity, we have a manifestation of the spontaneous change of elements. What is really taking place is a transmutation of one element into another, from a heavier to a lighter. The element uranium spontaneously becomes radium, and radium passes through a number of other stages until it, in turn, becomes lead. Each descending element is of lighter atomic weight than its predecessor. The changing process, of course, is a very slow one. It may be that all matter is radioactive, or can be made so. This raises the question whether all the matter in the universe may not undergo disintegration. There is, however, another side of the question which the discovery of radioactivity has brought to light, and which has effected a revolution in our views. We have seen that in radioactive substances the elements are breaking down. Is there a process of building up at work? If the more complicated atoms are breaking down into simpler forms, may there not be a converse process, a building up from simpler elements to more complicated elements? It is probably the case that both processes are at work. There are some 80-odd chemical elements on the Earth today. Are they all the outcome of an inorganic evolution, element giving rise to element, going back and back to some primeval stuff from which they were all originally derived infinitely long ago? Is there an evolution in the inorganic world which may be going on, parallel to the world of evolution of living things? Or is organic evolution a continuation of inorganic evolution? We have seen what evidence there is of this inorganic evolution in the case of the stars. We cannot go deeply into the matter here, nor has the time come for any direct statement that can be based on the findings of modern investigation. Taking it all together, the evidence is steadily accumulating, and there are authorities who maintain that already the evidence of inorganic evolution is convincing enough. The heavier atoms would appear to behave as though they were evolved from the lighter. The more complex forms, it is supposed, have evolved from the simpler forms. Moseley's discovery, to which reference has been made, points to the conclusion that the elements are built up one from another. 8. Other new views. We may here refer to another new conception to which the discovery of radioactivity has given rise. Lord Kelvin, who estimated the age of the Earth at 20 million years, reached this estimate by considering the Earth as a body which is gradually cooling down, losing its primitive heat like a loaf taken from the oven, at a rate which could be calculated, and that the heat radiated by the sun was due to contraction. Uranium and radioactivity were not known to Kelvin, and their discovery has upset both his arguments. Radioactive substances, which are perpetually giving out heat, introduce an entirely new factor. We cannot now assume that the Earth is necessarily cooling down. It may even, for all we know, be getting hotter. At the 1921 meeting of the British Association, Professor Rayleigh stated that further knowledge had extended the probable period during which there had been life on this globe to about 1,000 million years, and that the total age of the Earth to some small multiple of that. The Earth, he considers, is not cooling, but contains an internal source of heat from the disintegration of uranium in the outer crust. On the whole, the estimate obtained would seem to be in agreement with the geological estimates. The question, of course, cannot, in the present state of our knowledge, be settled within fixed limits that meet with general agreement. As we have said, there are other fundamental existences which give rise to more complex problems. The three great fundamental entities in the physical universe are matter, ether, and energy. So far as we know, outside these there is nothing. We have dealt with matter. There remain ether and energy. We shall see that just as no particle of matter, however small, may be created or destroyed, and just as there is no such thing as empty space, ether pervades everything, so there is no such thing as rest. Every particle that goes to make up our solid Earth is in a state of perpetual, unremitting vibration. Energy is the universal commodity on which all life depends. Separate and distinct as these three fundamental entities, matter, ether, and energy, may appear, it may be that, after all, they are only different and mysterious phases of an essential oneness of the universe. 9. The Future. Let us, in concluding this chapter, give just one illustration of the way in which all this new knowledge may prove to be as valuable practically as it is wonderful intellectually. We saw that electrons are shot out of atoms at a speed that may approach 160,000 miles a second. Sir Oliver Lodge has written recently that a 70th of a grain of radium discharges, at a speed 1,000 times that of a rifle bullet, 30 million electrons a second. Professor Le Bon has calculated that it would take 1,340,000 barrels of powder to give a bullet the speed of one of these electrons. He shows that the smallest French copper coin, smaller than a farthing, contains an energy equal to 80 million horsepower. A few pounds of matter contain more energy than we could extract from millions of tons of coal. Even in the atoms of hydrogen, at a temperature which we could produce in an electric furnace, the electrons spin round at a rate of nearly 100 trillion revolutions a second. Every man asks at once, will science ever tap this energy? If it does, no more smoke, no mining, no transit, no bulky fuel. The energy of an atom is, of course, only liberated when an atom passes from one state to another. The stored-up energy is fortunately fast bound by the electrons being held together as has been described. If it were not so, the Earth would explode and become a gaseous nebula. It is believed that someday we shall be able to release, harness, and utilize atomic energy. I am of opinion, says Sir William Bragg, that atom energy will supply our future need. 1,000 years may pass before we can harness the atom, or tomorrow might see us with the reins in our hands. That is the peculiarity of physics. Research and accidental discovery go hand in hand. Half a brick contains as much energy as a small coal field. The difficulties are tremendous, but, as Sir Oliver Lodge reminds us, there was just as much skepticism at one time about the utilization of steam or electricity. Is it to be supposed, he asks, that there can be no fresh invention, that all the discoveries have been made? More than one man of science encourages us to hope. Here are some remarkable words written by Professor Soddy, one of the highest authorities on radioactive matter, in our chief scientific weekly, Nature, November 6, 1919. The prospects of the successful accomplishment of artificial transmutation brighten almost daily. The ancients seem to have had something more than an inkling that the accomplishment of the transmutation would confer upon men powers hitherto the prerogative of the gods. But now we know definitely that the material aspect of transmutation would be of small importance in comparison with the control over the inexhaustible stores of internal atomic energy to which its successful accomplishment would inevitably lead. It has become a problem, no longer redolent of the evil associations of the age of alchemy, but one big with the promise of a veritable physical renaissance of the whole world. If that promise is ever realized, the economic and social face of the world will be transformed. Before passing on to the consideration of ether, light, and energy, let us see what new light the discovery of the electron has thrown on the nature and manipulation of electricity. What is electricity? The nature of electricity. There is at least one manifestation in nature, and so late as 20 years ago it seemed to be one of the most mysterious manifestations of all, which has been in great measure explained by the new discoveries. Already, at the beginning of this century, we spoke of our age of electricity, yet there were few things in nature about which we knew less. The electric current rang our bells, drove our trains, lit our rooms, but none knew what the current was. There was a vague idea that it was a sort of fluid that flowed along copper wires as water flows in a pipe. We now suppose that it is a rapid movement of electrons from atom to atom, in the wire, or wherever the current is. Let us try to grasp the principle of the new view of electricity and see how it applies to all the varied electrical phenomena in the world about us. As we saw, the nucleus of an atom of matter consists of positive electricity which holds together a number of electrons, or charges of negative electricity. This certainly tells us to some extent what electricity is and how it is related to matter, but it leaves us with the usual difficulty about fundamental realities. But we now know that electricity, like matter, is atomic in structure. A charge of electricity is made up of a small number of units or charges of a definite, constant amount. It has been suggested that the two kinds of electricity, that is, positive and negative, are right-handed and left-handed vortices, or whirlpools in ether, or rings in ether, but there are very serious difficulties, and we leave this to the future. Footnote: the words positive and negative electricity belong to the days when it was regarded as a fluid. A body overcharged with the fluid was called positive. An undercharged body was called negative. A positively electrified body is now one whose atoms have lost some of their outlying electrons, so that the positive charge of electricity predominates. The negatively electrified body is one with more than the normal number of electrons. 10. What an electric current is. The discovery of these two kinds of electricity has, however, enabled us to understand very fairly what goes on in electrical phenomena. The outlying electrons, as we saw, may pass from atom to atom, and this, on a large scale, is the meaning of the electric current. In other words, we believe an electric current to be a flow of electrons. Let us take, to begin with, a simple electrical cell in which a feeble current is generated, such a cell as there is in every house to serve its electric bells. In the original form, this simple sort of battery consisted of a plate of zinc and a plate of copper immersed in a chemical. Long before anything was known about electrons, it was known that, if you put zinc and copper together, you produce a mild current of electricity. We know now what this means. Zinc is a metal, the atoms of which are particularly disposed to part with some of their outlying electrons. Why, we do not know, but the fact is the basis of these small batteries. Electrons from the atoms of zinc pass to the atoms of copper, and their passage is a current. Each atom gives up an electron to its neighbor. It was further found long ago that if the zinc and copper were immersed in certain chemicals, which slowly dissolve the zinc, and the two metals were connected by a copper wire, the current was stronger. In modern language, there is a brisker flow of electrons. The reason is that the atoms of zinc which are stolen by the chemical leave their detachable electrons behind them, and the zinc has, therefore, more electrons to pass on to the copper. Such cells are now made of zinc and carbon, immersed in sal ammoniac, but the principle is the same. The flow of electricity is a flow of electrons, though we ought to repeat that they do not flow in a body, as molecules of water do. You may have seen boys place a row of bricks, each standing on one end, in such order that the first, if it is pushed, will knock over the second the third, and so on to the last. There is a flow of movement all along the line, but each brick moves only a short distance. So an electron merely passes to the next atom, which sends on an electron to the third atom, and so on. In this case, however, the movement from atom to atom is so rapid that the ripple of movement, if we may call it so, may pass along at an enormous speed. We have seen how swiftly electrons travel. But how is this turned into power enough even to ring a bell? The actual mechanical apparatus by which the energy of the electron current is turned into sound, or heat, or light will be described in a technical section later in this work. We are concerned here only with the principle, which is clear. While zinc is very apt to part with electrons, copper is just as obliging in facilitating their passage onward. Electrons will travel in this way in most metals, but copper is one of the best conductors. So we lengthen the copper wire between the zinc and the carbon until it goes as far as the front door and the bell, which are included in the circuit. When you press the button at the door, two wires are brought together and the current of electrons rushes round the circuit, and at the bell its energy is diverted into the mechanical apparatus which rings the bell. Copper is a good conductor, 6 times as good as iron, and is therefore so common in electrical industries. Some other substances are just as stubborn as copper is yielding, and we call them insulators, because they resist the current instead of letting it flow. Their atoms do not easily part with electrons. Glass, vulcanite, and porcelain are very good insulators for this reason. What the dynamo does. But even several cells together do not produce the currents needed in modern industry, and the flow is produced in a different manner. As the invisible electrons pass along a wire, they produce what we call a magnetic field around the wire. They produce a disturbance in the surrounding ether. To be exact, it is through the ether surrounding the wire that the energy originated by the electrons is transmitted. To set electrons moving on a large scale, we use a dynamo. By means of the dynamo, it is possible to transform mechanical energy into electrical energy. The modern dynamo, as Professor Soddy puts it, may be looked upon as an electron pump. We cannot go into the subject deeply here. We would only say that a large coil of copper wire is caused to turn round rapidly between the poles of a powerful magnet. That is the essential construction of the dynamo, which is used for generating strong currents. We shall see in a moment how magnetism differs from electricity, and will say here only that round the poles of a large magnet there is a field of intense disturbance which will start a flow of electrons in any copper that is introduced into it. On account of the speed given to the coil of wire, its atoms enter suddenly this magnetic field, and they give off crowds of electrons in a flash. It is found that a similar disturbance is caused, though the flow is in the opposite direction, when a coil of wire leaves the magnetic field. And as the coil is revolving very rapidly, we get a powerful current of electricity that runs in alternate directions, an alternating current. Electricians have apparatus for converting it into continuous current where this is necessary. A current, therefore, means a steady flow of electrons from atom to atom. Sometimes, however, a number of electrons rush violently and explosively from one body to another, as in the electric spark or the occasional flash from an electric tram or train. The grandest and most spectacular display of this phenomenon is the thunderstorm. As we saw earlier, a portentous furnace like the sun is constantly pouring floods of electrons from its atoms into space. The Earth intercepts great numbers of these electrons. In the upper regions of the air, the stream of solar electrons has the effect of separating positively electrified atoms from negatively electrified ones, and the water vapor, which is constantly rising from the surface of the sea, gathers more freely round the positively electrified atoms and brings them down, as rain, to the earth. Thus the upper air loses a proportion of positive electricity, or becomes negatively electrified. In the thunderstorm we get both kinds of clouds, some with large excesses of electrons, and some deficient in electrons, and the tension grows until at last it is relieved by a sudden and violent discharge of electrons from one cloud to another, or to the earth, an electric spark on a prodigious scale. 11. Magnetism. We have seen that an electric current is really a flow of electrons. Now, an electric current exhibits a magnetic effect. The surrounding space is endowed with energy which we call electromagnetic energy. A piece of magnetized iron attracting other pieces of iron to it is the popular idea of a magnet. If we arrange a wire to pass vertically through a piece of cardboard and then sprinkle iron filings on the cardboard, we shall find that, on passing an electric current through the wire, the iron filings arrange themselves in circles round it. The magnetic force due to the electric current seems to exist in circles round the wire, an ether disturbance being set up. Even a single electron, when in movement, creates a magnetic field, as it is called, round its path. There is no movement of electrons without this attendant field of energy, and their motion is not stopped until that field of energy disappears from the ether. The modern theory of magnetism supposes that all magnetism is produced in this way. All magnetism is supposed to arise from the small whirling motions of the electrons contained in the ultimate atoms of matter. We cannot here go into details of the theory nor explain why, for instance, iron behaves so differently from other substances. But it is sufficient to say here also, the electron theory provides the key. This theory is not yet definitely proved, but it furnishes a sufficient theoretical basis for future research. The Earth itself is a gigantic magnet, a fact which makes the compass possible, and it is well known that the Earth's magnetism is affected by those great outbreaks on the Sun called sunspots. Now it has been recently shown that a sunspot is a vast whirlpool of electrons, and that it exerts a strong magnetic action. There is doubtless a connection between these outbreaks of electronic activity and the consequent changes in the Earth's magnetism. The precise mechanism of the connection, however, is still a matter that is being investigated. Ether and waves. Ether and waves. The whole material universe is supposed to be embedded in a vast medium called the ether. It is true that the notion of the ether has been abandoned by some modern physicists, but whether or not it is ultimately dispensed with, the conception of the ether has entered so deeply into the scientific mind that the science of physics cannot be understood unless we know something about the properties attributed to the ether. The ether was invented to explain the phenomena of light, and to account for the flow of energy across empty space. Light takes time to travel. We see the sun at any moment by the light that left it 8 minutes before. It has taken that 8 minutes for the light from our sun to travel that 93 million miles odd which separates it from our Earth. Besides the fact that the light takes time to travel, it can be shown that light travels in the form of waves. We know that sound travels in waves. Sound consists of waves in the air, or water or wood or whatever medium we hear it through. If an electric bell be put in a glass jar and the air pumped out of the jar, the sound of the bell becomes feebler and feebler until, when enough air has been taken out, we do not hear the bell at all. Sound cannot travel in a vacuum. We continue to see the bell, however, so that evidently light can travel in a vacuum. The invisible medium through which the waves of light travel is the ether, and this ether permeates all space and all matter. Between us and the stars stretch vast regions empty of all matter. But we see the stars. Their light reaches us, even though it may take centuries to do so. We conceive, then, that it is the universal ether which conveys that light. All the energy which has reached the earth from the sun, and which, stored for ages in our coal fields, is now used to propel our trains and steamships, to heat and light our cities, to perform all the multifarious tasks of modern life, was conveyed by the ether. Without that universal carrier of energy, we should have nothing but a stagnant, lifeless world. We have said that light consists of waves. The ether may be considered as resembling, in some respects, a jelly. It can transmit vibrations. The waves of light are really excessively small ripples, measuring from crest to crest. The distance from crest to crest of the ripples in a pond is sometimes no more than an inch or two. This distance is enormously great compared to the longest of the wavelengths that constitute light. We say the longest, for the waves of light differ in length. The color depends upon the length of the light. Red light has the longest waves and violet the shortest. The longest waves, the waves of deep red light, are 7/250,000ths of an inch in length. This is nearly twice the length of deep violet light waves, which are 1/67,000th of an inch. But light waves, the waves that affect the eye, are not the only waves carried by the ether. Waves too short to affect the eye can affect the photographic plate, and we can discover in this way the existence of waves only half the length of the deep violet waves. Still shorter waves can be discovered until we come to those excessively minute rays, the X-rays. Below the limits of visibility. But we can extend our investigations in the other direction. We find that the ether carries many waves longer than light waves. Special photographic emulsions can reveal the existence of waves 5 times longer than violet light waves. Extending below the limits of visibility are waves we detect as heat waves. Radiant heat, like the heat from a fire, is also a form of wave motion in the ether. But the waves our senses recognize as heat are longer than light waves. There are longer waves still, but our senses do not recognize them. But we can detect them by our instruments. These are the waves used in wireless telegraphy, and their length may be, in some cases, measured in miles. These waves are the so-called electromagnetic waves. Light, radiant heat, and electromagnetic waves are all of the same nature. They differ only as regards to their wavelengths. Light, visible and invisible. If light, then, consists of waves transmitted through the ether, what gives rise to the waves? Whatever sets up such wonderfully rapid series of waves must be something with an enormous vibration. We come back to the electron. All atoms of matter, as we have seen, are made up of electrons revolving in a regular orbit round a nucleus. These electrons may be affected by outside influences. They may be agitated and their speed or vibration increased. Electrons and light. The particles even of a piece of cold iron are in a state of vibration. No nerves of ours are able to feel and register the waves they emit, but your cold poker is really radiating or sending out a series of wave movements on every side. After what we saw about the nature of matter, this will surprise none. Put your poker in the fire for a time. The particles of the glowing coal, which are violently agitated, communicate some of their energy to the particles of iron in the poker. They move to and fro more rapidly, and the waves which they create are now able to affect your nerves and cause a sensation of heat. Put the poker in the fire again, until its temperature rises to 500 degrees centigrade. It begins to glow with a dull red. Its particles are now moving very violently, and the waves they send out are so short and rapid that they can be picked up by the eye. We have visible light. They would still not affect a photographic plate. Heat the iron further, and the crowds of electrons now send out waves of various lengths which blend into white light. What is happening is the agitated electrons flying round in their orbits at a speed of trillions of times a second. Make the iron blue hot, and it pours out, in addition to light, the invisible waves which alter the film on the photographic plate. And beyond these there is a long range of still shorter waves, culminating in the X-rays, which will pass between the atoms of flesh or stone. Nearly 250 years ago, it was proved that light traveled at least 600,000 times faster than sound. Jupiter, as we saw, has moons which circle round it. They pass behind the body of the planet and reappear at the other side. But it was noticed that, when Jupiter is at its greatest distance from us, the reappearance of the moon from behind it is 16 minutes and 36 seconds later than when the planet is nearest to us. Plainly, this was because light took so long to cover the additional distance. The distance was then imperfectly known, and the speed of light was underrated. We now know the distance, and we can easily get the velocity of light. No doubt that it seems far more wonderful to discover this within the walls of a laboratory, but it was done as long ago as 1850. A cogged wheel is so mounted that a ray of light passes between two of the teeth and is reflected back from a mirror. Now, slight as is the fraction of a second which light takes to travel that distance, it is possible to give such speed to the wheel that the next tooth catches the ray of light on its return and cuts it off. The speed is increased still further until the ray of light returns to the eye of the observer through the notch next to the one by which it had passed to the mirror. The speed of the wheel was known, and it was thus possible again to gather the velocity of light. If the shortest waves are 1/67,000th of an inch in length, and light travels at 186,000 miles a second, any person can work out that about 800 trillion waves enter the eye in a second when we see violet. Sorting out light waves. The waves sent out on every side by the energetic electrons become faintly visible to us when they reach about 1/35,000th of an inch. As they become shorter and more rapid, as the electrons increase their speed, we get in succession the colors red, orange, yellow, green, blue, indigo, and violet. Each distinct sensation of color means a wave of different length. When they are all mingled together, as in the light of the sun, we get white light. When this white light passes through glass, the speed of the waves is lessened, and, if the ray of light falls obliquely on a triangular piece of glass, the waves of different lengths part company as they travel through it, and the light is spread out in a band of rainbow color. The waves are sorted out according to their lengths in the obstacle race through the glass. Anyone may see this for himself by holding up a wedge-shaped piece of crystal between the sunlight and the eye. The prism separates the sunlight into its constituent colors, and these various colors will be seen quite readily. Or the thing may be realized in another way. If the 7 colors are painted on a wheel and the wheel rapidly revolved on a pivot, the wheel will appear a dull white. The several colors will not be seen. But omit one of the colors, then the wheel, when revolved, will not appear white, but will give the impression of one color corresponding to what the union of 6 colors gives. Another experiment will show that some bodies held up between the eye and a white light will not permit all the rays to pass through, but will intercept some. A body that intercepts all the 7 rays except red will give the impression of red, or if all the rays except violet, then violet will be the color seen. End of section 14.
Section 15 of the Outline of Science by J. Arthur Thompson. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by James Christopher, jxchristopher@yahoo.com. The Outline of Science, Volume 1, by J. Arthur Thompson, Section 15.
Part 8, Foundations of the Universe, continued. The Fate of the World. Professor Soddy has given an interesting picture of what might happen when the sun's light and heat is no longer what it is. The human eye has adapted itself through the ages to the peculiarities of the sun's light, so as to make the most of that wavelength of which there is most. Let us indulge for a moment in these gloomy prognostications, as to the consequences to this earth of the cooling of the sun with the lapse of ages, which used to be in vogue, but which radioactivity has so rudely shaken. Picture the fate of the world when the sun has become a dull red-hot ball, or even when it has cooled so far that it would no longer emit light to us. That does not at all mean that the world would be in inky darkness, and that the sun would not emit light to the people then inhabiting this world, if any had survived and could keep themselves from freezing. To such, if the eyes continued to adapt itself to the changing conditions, our blues and violets would be ultraviolet and invisible. But our dark heat would be light, and hot bodies would be luminous to them which would be dark to us. 12. What the blue sky means. We saw in a previous chapter how the spectroscope splits up light waves into their colors. But nature is constantly splitting the light into its different length waves, its colors. The rainbow, where dense moisture in the air acts as a spectroscope, is the most familiar example. A piece of mother of pearl, or even a film of oil on the street or on water, has the same effect, owing to the fine inequalities in its surface. The atmosphere all day long is sorting out the waves. The blue sky overhead means that the fine particles in the upper atmosphere catch the shorter waves, the blue waves, and scatter them. We can make a tube full of blue sky in the laboratory at any time. The beautiful pink flush on the Alps at sunrise, the red glory that lingers in the west at sunset, mean that, as the sun's rays struggle through denser masses of air when it's low on the horizon, the long red waves are shifted out from the other shafts. Then there is that varied face of nature which, by absorbing some waves and refracting others, weaves its own beautiful robe of color. Here and there is a black patch which absorbs all the light. White surfaces reflect the whole of it. What is reflected depends on the period of vibration of the electrons in that particular kind of matter. Generally, as the electrons receive the flood of trillions of waves, they absorb either the long or the medium or the short, and they give us a wonderful color scheme of nature. In some cases, the electrons continue to radiate long after the sunlight has ceased to fall upon them. We get from them black or invisible light, and we can take photographs by it. Other bodies, like glass, vibrate in unison with the period of the light waves and let them stream through. Light without heat. There are substances, phosphorescent things we call them, which give out a mysterious cold light of their own. It is one of the problems of science, and one of profound practical interest. If we could produce light without heat, our gas bill would shrink amazingly. So much energy is wasted in the production of heat waves and ultraviolet waves which we do not want, that 90% or more of the power used in illumination is wasted. Would that the glowworm or even the dead herring would yield its secret. Phosphorus is the one thing we know as yet that suits the purpose, and it smells. Indeed, our artificial light is not only extravagant in cost, but often poor in color. The unwary person often buys a garment by artificial light, and is disgusted next morning to find in it a color which is not wanted. The color disclosed by the sun was not in the waves of the artificial light. Beyond the waves of violet light are the still shorter and more rapid waves, the ultraviolet waves, which are precious to the photographer. As every amateur knows, his plate may be safely exposed to light that comes through a red or an orange screen. Such a screen means no thoroughfare for the blue and beyond blue waves, and it is these which arrange the little grains of silver in the plate. It is the same waves which supply the energy to the little green grains of matter, chlorophyll, in the plant, preparing our food and timber for us, as will be seen later. The tree struggles upward and spreads out its leaves fan-wise to the blue sky to receive them. Our coal measures, the mighty dead forest of long ago, are vast stores of sunlight which we are prodigally using up. The X-rays are the extreme end, the highest octave of the series of waves. Their power of penetration implies that they are excessively minute, but even these have not held their secret from the modern physicist. From a series of beautiful experiments in which they were made to pass among the atoms of a crystal we learn their length. It is about 1/10,000,000th of a millimeter. A millimeter is about 1/25th of an inch. One of the most recent discoveries made during a recent eclipse of the sun is that light is subject to gravitation. A ray of light from a star is bent out of its straight path when it passes near the mass of the sun. Professor Eddington tells us that we have as much right to speak of a pound of light as of a pound of sugar. Professor Eddington even calculates that the earth receives 160 tons of light from the sun every year. Energy, how all life depends on it. As we have seen in an earlier chapter, one of the fundamental entities of the universe is matter. A second, not less important, is called energy. Energy is indispensable if the world is to continue to exist, since all phenomena, including life, depend on it. Just as it is humanly impossible to create or destroy a particle of matter, so it is impossible to create or destroy energy. This statement will be more readily understood when we have considered what energy is. Energy, like matter, is indestructible, and just as matter exists in various forms, so does energy. And we may add, just as we are ignorant of what the negative and positive particles of electricity which constitute matter really are, so we are ignorant of the true nature of energy. At the same time, energy is not so completely mysterious as it once was. It is another of nature's mysteries which the advance of modern science has in some measure unveiled. It was only during the 19th century that energy came to be known as something as distinct and permanent as matter itself. Forms of energy. The existence of various forms of energy have been known, of course, for ages. There was the energy of falling stones, the energy produced by burning wood or coal or any other substance. But the essential identity of these forms of energy had not been suspected. The conception of energy as something which, like matter, was constant in amount, which could not be created or destroyed, was one of the great scientific acquisitions of the past century. It is not possible to enter deeply into this subject here. It is sufficient if we briefly outline its salient aspects. Energy is recognized in two forms, kinetic and potential. The form of energy which is most apparent to us is the energy of motion. For example, a rolling stone, running water, a falling body, and so on. We call the energy of motion kinetic energy. Potential energy is the energy a body has in virtue of its position. It is in its capacity, in other words, to acquire kinetic energy, as in the case of a stone resting on the edge of a cliff. Energy may assume different forms. One kind of energy may be converted directly or indirectly into some other form. The energy of burning coal, for example, is converted into heat, and from heat energy we have mechanical energy, such as that manifested by the steam engine. In this way we can transfer energy from one body to another. There is the energy of the great waterfalls of Niagara, for instance, which are used to supply the energy of huge electric power stations. What heat is. An important fact about energy is that all energy tends to take the form of heat energy. The impact of a falling stone generates heat. A waterfall is hotter at the bottom than at the top. The falling particles of water, on striking the ground, generate heat. And most chemical changes are attended by heat changes. Energy may remain latent indefinitely in a lump of wood, but in combustion it is liberated and we have heat as a result. The atom of radium or of any other radioactive substance as it disintegrates generates heat. Every hour radium generates sufficient heat to raise the temperature of its own weight of water from the freezing point to the boiling point. And what is heat? Heat is molecular motion. The molecules of every substance, as we have seen on a previous page, are in a state of constant motion. And the more vigorous the motion, the hotter the body. As wood or coal burns, the invisible molecules of these substances are violently agitated, and give rise to ether waves which our senses interpret as light and heat. In this constant movement of the molecules, then, we have a manifestation of the energy of motion and of heat. That energy which disappears in one form reappears in another, as has been found to be universally true. It was Joule who, by churning water, first showed that a measurable quantity of mechanical energy could be transformed into a measurable quantity of heat energy. By causing an apparatus to stir water vigorously, that apparatus being driven by falling weights or a rotating flywheel, or by any other mechanical means, the water became heated. A certain amount of mechanical energy had been used up and a certain amount of heat had appeared. The relation between these two things was found to be invariable. Every physical change in nature involves a transformation of energy, but the total quantity of energy in the universe remains unaltered. This is the great doctrine of the conservation of energy. 13. Substitutes for coal. Consider the source of nearly all the energy which is used in modern civilization, coal. The great forests of the Carboniferous epoch now exist as beds of coal. By the burning of coal, a chemical transformation, the heat energy is produced on which at present our whole civilization depends. Whence is the energy locked up in the coal derived? From the sun. For millions of years, the energy of the sun's rays had gone to form the vast vegetation of the Carboniferous era and had been transformed, by various subtle processes, into the potential energy that slumbers in those immense fossilized forests. The exhaustion of our coal deposits would mean, so far as our knowledge extends at present, the end of the world's civilization. There are other known sources of energy, it is true. There is the energy of falling water. The great falls of Niagara are used to supply the energy of huge electric power stations. Perhaps, also, something could be done to utilize the energy of the tides, another instance of the energy of moving water. And attempts have been made to utilize directly the energy of the sun's rays. But all these sources of energy are small compared with the energy of coal. A suggestion was made at a recent British Association meeting that deep borings might be sunk in order to utilize the internal heat of the earth. But this is not, perhaps, a very practical proposal. By far the most effective substitute for coal would be found in the interior energy of the atom, a source of energy which, as we have seen, is practically illimitable. If the immense electrical energy in the interior of the atom can ever be liberated and controlled, then our steadily decreasing coal supply will no longer be the bugbear it is now to all thoughtful men. The stored up energy of the great coal field can be used up, but we cannot replace it or create fresh supplies. As we have seen, energy cannot be destroyed, but it can become unavailable. Let us consider what this important fact means. 14. Dissipation of energy. Energy may become dissipated. Where does it go, since if it is indestructible, it must still exist? It is easier to ask the question than to give a final answer, and it is not possible in this outline, where an advanced knowledge of physics is not assumed on the part of the reader, to go fully into the somewhat difficult theories put forward by physicists and chemists. We may raise the temperature, say, of iron until it is white hot. If we stop the process, the temperature of the iron will gradually settle down to the temperature of surrounding bodies. As it does so, where does its previous energy go? In some measure, it may pass to other bodies in contact with the piece of iron, but ultimately the heat becomes radiated away in space where we cannot follow it. It has been added to the vast reservoir of unavailable heat energy of uniform temperature. It is sufficient here to say that if all bodies had uniform temperature, we should experience no such thing as heat, because heat only travels from one body to another, having the effect of cooling the one and warming the other. In time, the two bodies acquire the same temperature. The sum total of the heat in any body is measured in terms of the kinetic energy of its moving molecules. There must come a time, so far as we can see at present, when, even if all the heat energy of the universe is not radiated away into empty infinite space, yet a uniform temperature will prevail. If one body is hotter than another, it radiates heat into that body until both are at the same temperature. Each body may still possess a considerable quantity of heat energy which it has absorbed, but that energy, so far as reactions between those two bodies are concerned, is now unavailable. The same principle applies whatever number of bodies we consider. Before heat energy can be utilized, we must have bodies with different temperature. If the whole universe were at the same uniform temperature, then, although it might possess an enormous amount of heat energy, this energy would be unavailable. What a uniform temperature would mean. And what does this imply? It implies a great deal, for if all the energy in the world became unavailable, the universe as it is now would cease to be. It is possible that, by the constant interchange of heat radiations, the whole universe is tending to some uniform temperature, in which case, although all molecular motion would not have ceased, it would have become unavailable. In this sense, it may be said that the universe is running down. If all the molecules of a substance were brought to a standstill, that substance would be at the absolute zero of temperature. There could be nothing colder. The temperature at which all molecular motion would cease is known. It is negative 273 degrees Celsius. No body could possibly attain a lower temperature than this. A lower temperature could not exist. Unless there exists in nature some process, of which we know nothing at present, whereby energy is renewed, our solar system must one day sink to this absolute zero of temperature. The sun, the earth, and every other body in the universe is steadily radiating heat. And this radiation cannot go on forever, because heat continually tends to diffuse and to equalize temperature. But we can see, theoretically, that there is a way of evading this law. If the chaotic molecular motions which constitute heat could be regulated, then the heat energy of a body could be utilized directly. Some authorities think that some of the processes which go on in the living body do not involve any waste energy, that the chemical energy of food is transformed directly into work without any of it being dissipated as useless heat energy. It may be, therefore, that man will finally discover some way of escape from the natural law that, while energy cannot be destroyed, it has a tendency to become unavailable. The primary reservoir of energy is the atom. It is the energy of the atom of elements in the sun, the stars, the earth, from which nature draws for all her supply of energy. Shall we ever discover how we can replenish the dwindling resources of energy, or find out how we can call into being at the present unavailable energy which is stored up in the uniform temperature? It looks as though our successors could witness an interesting race between the progress of science on the one hand and the depletion of natural resources on the other. The natural rate of flow of energy from its primary atomic reservoirs to the sea of waste heat energy of uniform temperature allows life to proceed at a complete pace sternly regulated by the inexorable laws of supply and demand, which the biologists have recognized in their field as the struggle for existence. Matter and Energy by Professor Soddy. It is certain that energy is an actual entity just as much as matter, and that it cannot be created or destroyed. Matter and ether are receptacles or vehicles of energy. As we have said, what these entities really are in themselves we do not know. It may be that all forms of energy are in some fundamental way aspects of the same primary entity which constitutes matter. How all matter is constituted of particles of electricity we have already seen. The question to which we await an answer is, what is electricity? 15. Matter, ether, and Einstein. The supreme synthesis, the crown of all this progressive conquest of nature, would be to discover that the particles of positive and negative electricity, which make up the atoms of matter, are points or centers of disturbances of some kind in a universal ether, and that all our energies, light, magnetism, gravitation, etc., are waves or strains of some kind set up in the ether by these clusters of electrons. It is a fascinating, tantalizing dream. Larmor suggested in 1900 that the electron is a tiny whirlpool, or vortex in ether, and as such a vortex may turn in either of two opposite ways. we seem to see a possibility of explaining positive and negative electricity. But the difficulties have proved very serious, and the nature of the electron is unknown. A recent view is that it is a ring of negative electricity rotating about its axis at high speed, though that does not carry us very far. The unit of positive electricity is even less known. We must be content to know the general lines on which thought is moving toward the final unification. We say unification, but it would be a grave error to think that ether is the only possible basis for such unity, or to make it an essential part of one's philosophy of the universe. Ether was never more than an imagined entity to which we ascribed the most extraordinary properties, and which seemed then to promise considerable aid. It was conceived as an elastic solid of very great density, stretching from end to end of the universe, transmitting waves from star to star at a rate of 186,000 miles a second. Yet it was believed that the most solid matter passed through it as though it did not exist. Some years ago, a delicate experiment was tried for the purpose of detecting the ether. Since the earth, in traveling round the sun, must move through the ether, if the ether exists, there ought to be a stream of ether flowing through every laboratory, just as the motion of a ship through a still atmosphere will make a wind. In 1887, Michelson and Morley tried to detect this. Theoretically, a ray of light in the direction of the stream ought to travel at a different rate from a ray of light against the stream or across it. They found no difference, and scores of other experiments have failed. This does not prove that there is no ether, as there is reason to suppose that our instruments would appear to shrink in precisely the same proportion as the alteration of the light, but the fact remains that we have no proof of the existence of ether. J. H. Jean says that nature acts as if no such thing existed. Even the phenomena of light and magnetism, he says, do not imply ether, and he thinks that the hypothesis may be abandoned. The primary reason, of course, for giving up on the notion of ether is that, as Einstein has shown, there is no way of detecting its existence. If there is an ether, then, since the earth is moving through it, there should be some way of detecting this motion. The experiment has been tried, as we have said, but although the method used was very sensitive, no motion was discovered. It is Einstein who, by revolutionizing our conceptions of space and time, showed that no such motions could ever be discovered, whatever means were employed, and that the usual notion of the ether must be abandoned. We shall explain this theory more fully in a later section. Influence of the tides, origin of the moon, the earth slowing down. 16. Until comparatively recent times, until, in fact, the full dawn of modern science, the tides ranked among the greatest of nature's mysteries. And, indeed, what agency could be invoked to explain this mysteriously regular flux and reflux of the waters of the ocean? It is not surprising that the steady, rhythmical rise and fall suggested to some imaginative minds the breathing of a mighty animal. And even when man first became aware of the fact that this regular movement was somehow associated with the moon, was he much nearer an explanation? What bond could exist between the movements of that distant world and the diurnal variation of the waters of the earth? It is reported that an ancient astronomer, despairing of ever resolving the mystery, drowned himself in the sea.
The earth pulled by the moon.
But it was part of the merit of Newton's mighty theory of gravitation that it furnished an explanation even of this age-old mystery. We can see, in broad outlines at any rate, that the theory of universal attraction can be applied to this case. For the moon, Newton taught us, pulls every particle of matter throughout the earth. If we imagine that part of the earth's surface which comprises the Pacific Ocean, for instance, to be turned towards the moon, we can see that the moon's pull, acting on the loose and mobile water, would tend to heap it up into a sort of mound. The whole earth is pulled by the moon, but the water is more free to obey this pull than is the solid earth. Those small tides are also caused in the earth's solid crust. It can be shown also that a corresponding hump would tend to be produced on the other side of the earth, owing, in this case, to the tendency of the water, being more loosely connected, to lag behind the solid earth. If the earth's surface were entirely fluid, the rotation of the earth would give the impression that these two humps were continually traveling round the world, once every day. At any given part of the earth's surface, therefore, there would be two humps daily, i.e., 2 periods of high water. Such is the simplest possible outline of the gravitational theory of the tides. The actually observed phenomena are vastly more complicated, and the complete theory bears little resemblance to the simple forms we have just outlined. Everyone who lives in the neighborhood of a port knows, for instance, that high water seldom coincides with the time when the moon crosses the meridian. It may be several hours early or late. High water at London Bridge, for instance, occurs about 1½ hours after the moon has passed the meridian, while at Dublin high water occurs about 1½ hours before the moon crosses the meridian. The actually observed phenomena, then, are far from simple. They have, nevertheless, been very completely worked out, and the times of high water for every part of the world can now be prophesied for a considerable time ahead.
The action of sun and moon.
It would be beyond our scope to attempt to explain the complete theory, but we may mention one obvious factor which must be taken into account. Since the moon, by its gravitational attraction, produces tides, we should expect that the sun, whose gravitational attraction is so much stronger, should also produce tides, and, we would suppose, at first sight more powerful tides than the moon. But while it is true that the sun produces tides, it is not true that they are more powerful than those produced by the moon. The sun's tide-producing power is, as a matter of fact, less than half that of the moon. The reason of this is that distance plays an enormous role in the production of tides. The mass of the sun is 26 million times that of the moon. On the other hand, it is 386 times as far as the moon. This greater distance more than counterbalances its greater mass, and the result, as we have said, is that the moon is more than twice as powerful. Sometimes the sun and moon act together, and we have what are called spring tides. Sometimes they act against one another, and we have neap tides. These effects are further complicated by a number of other factors, and the tides, at various places, vary enormously. Thus, at St. Helens, the sea rises and falls about 3 feet, whereas in the Bay of Fundy it rises and falls more than 50 feet. But here again the reasons are complicated. 17. Origin of the moon. But there is another aspect of the tides which is of vastly greater interest and importance than the theory we have just been discussing. In the hands of Sir George H. Darwin, the son of Charles Darwin, the tides have been made to throw light on the evolution of our solar system. In particular, they have illustrated the origin and development of the system formed by our earth and moon. It is quite certain that, long ages ago, the earth was rotating immensely faster than it is now, and that the moon was so near as to be actually in contact with the earth. In that remote age the moon was just on the point of separating from the earth, of being thrown off by the earth. Earth and the moon were once one body, but the high rate of rotation caused this body to split into 2 pieces. One piece became the earth we know now, and the other became the moon. Such is the conclusion to which we are led by an examination of the tides. In the first place, let us consider the energy produced by the tides. We see evidence of this energy all around the world's coastlines. Estuaries are scooped out, great rocks are gradually reduced to rubble. Innumerable tons of matter are continually being set in movement. Whence is this energy derived? Energy, like matter, cannot be created from nothing. What, then, is the source which makes this colossal expenditure possible? The earth slowing down. The answer is simple, but startling. The source of tidal energy is the rotation of the earth. The massive bulk of the earth, turning every 24 hours on its axis, is like a giant flywheel. In virtue of its rotation, it possesses an enormous store of energy. But even the heaviest and swiftest flywheel, if it is doing work, or even if it is only working against the friction of its bearings, cannot dispense energy forever. It must gradually slow down. There is no escape from this reasoning. It is the rotation of the earth which supplies the energy of the tides, and, as a consequence, the tides must be slowing down the earth. The tides act as a kind of brake on the earth's rotation. These masses of water, held back by the moon, exert a kind of dragging effect on the rotating earth. Doubtless this effect, measured by our ordinary standards, is very small. It is, however, continuous, and in the course of the millions of years dealt with in astronomy, this small but constant effect may produce very considerable results. But there is another effect which can be shown to be a necessary mathematical consequence of tidal action. It is the moon's actions on the earth which produce the tides, but they also react on the moon. The tides are slowing down the earth, and they are also driving the moon farther and farther away. This result, strange as it may seem, does not permit of doubt, for it is the result of an indubitable dynamical principle, which cannot be made clear without a mathematical discussion. Some interesting consequences follow. Since the earth is slowing down, it follows that it was once rotating faster. There was a period, a long time ago, when one day comprised only 20 hours. Going farther back still, we come to a day of 10 hours, until, inconceivable ages ago, the earth must have been rotating on its axis in a period of from 3 to 4 hours. At this point, let us stop and inquire what was happening to the moon. We have seen that at present the moon is getting farther and farther away. It follows, therefore, that when the day was shorter, the moon was nearer. As we go farther back in time, we find the moon nearer and nearer to an earth rotating faster and faster. When we reach the period we have already mentioned, the period when the earth completed a revolution in 3 or 4 hours, we find that the moon was so near as to be almost grazing the earth. This fact is very remarkable. Everybody knows that there is a critical velocity for a rotating flywheel. a velocity beyond which the flywheel would fly into pieces because the centrifugal force developed is so great as to overcome the cohesion of the molecules of the flywheel. We have already likened our earth to a flywheel, and we have traced its history back to the point where it was rotating with immense velocity. We have also seen that, at that moment, the moon was barely separated from the earth. The conclusion is irresistible. In an age more remote the earth did fly in pieces, and one of those pieces is the moon. Such, in brief outline, is the tidal theory of the origin of the Earth-Moon system. The day becoming longer. At the beginning, when the moon split off from the earth, it obviously must have shared the earth's rotation. It flew round the earth in the same time that the earth rotated. That is to say, the month and the day were of equal length. As the moon began to get farther from the earth, the month, because the moon took longer to rotate round the earth, began to get correspondingly longer. The day was also becoming longer because the earth was slowing down, taking longer to rotate on its axis, but the month increased at a greater rate than the day. Presently the month became equal in 2 days, then to 3, and so on. It has been calculated that this process went on until there were 29 days in the month. After that number of days in the month began to decrease until it reached its present value or magnitude, and will continue to decrease until once more the month and the day are equal. In that age the earth will be rotating very slowly. The braking actions of the tides will cause the earth always to keep the same face to the moon. It will rotate on its axis in the same time that the moon turns round the earth. If nothing but the earth and moon were involved, this state of affairs would be final. But there is also the effect of the solar tides to be considered. The moon makes the day equal to the month, but the sun has a tendency, by still further slowing down the earth's rotation on its axis, to make the day equal to the year. It would do this, of course, by making the earth take as long to turn on its axis as to go round the sun. It cannot succeed in this owing to the action of the moon, but it can succeed in making the day rather longer than the month. Surprising as it may seem, we already have an illustration of this possibility in the satellites of Mars. The Martian day is about 1/2 hour longer than ours. But when the 2 minute satellites of Mars were discovered, it was noticed that the inner one of the 2 revolved around Mars in about 7 hours 40 minutes. In 1 Martian day, therefore, one of the moons of Mars makes more than 3 complete revolutions round that planet, so that to an inhabitant of Mars there would be more than 3 months in a day. End of Section 15. End of The Outline of Science, Volume 1, by J. Arthur Thomson. Recorded by James Christopher, jxchristopher@yahoo.com, in Phoenix, Arizona, June 2008.